In this demo, we'll look at Google Cloud Platform services. Google Cloud Platform provides a huge number of services. Some of the more common services include computing and hosting, storage, networking, as well as big data. Let's look at computing and hosting first. First, Managed Application Platform. This is offered as Google App Engine, and it's a platform as a service offering. It's a somewhat hands-off approach in which you allow Google to manage hosting, scaling, and monitoring services. So for example, if traffic to your e-commerce website sees a dramatic upturn, Google will automatically scale the system for you. And container-based computing. This is focused on application code rather than deployment and hosting. Google Kubernetes Engine is referred to as containers as a service and is very mature and one of the most powerful container orchestration platforms. Virtual machines are offered as a service called Google Compute Engine, and this is considered to be a type of infrastructure as a service. With this type of service, you are responsible for configuration, administration, and monitoring tasks. In other words, Google will make sure that reliable resources are always available and up to date, but it's on you to manage and provision them. Now let's look at storage services. Cloud SQL, which is a database service based on structured query language, or SQL, and it offers either MySQL or PostgreSQL databases. Google Cloud Platform offers two types of NoSQL data storage. One is Cloud Data Store, and Cloud Bigtable is the other. Cloud Spanner is a fully managed, highly available relational database service for mission-critical application. Cloud Storage offers large capacity, consistent, and scalable data storage. And Compute Engine offers persistent disks, and this is available as the primary storage for your instances with both standard persistent disks as well as solid-state drives. Now let's look at networking services. Compute Engine provides networking services for virtual machine instances to use. You can load balance traffic across multiple instances, and there's Cloud DNS as well, which allows you to create and manage domain name system records. And Google Cloud Interconnect is an advanced connectivity service which allows you to connect your existing network to Google Cloud Platform networking resources. And finally, big data services. First, BigQuery. This is a data analysis service. The data analysis services include custom schema creation, so you can organize your data as you wish. For example, you may have a schema structure in mind using specific data sets and tables. It offers the convenience of large dataset querying using SQL-like commands, so the learning curve is more manageable. It provides for loading, querying, and other operations via jobs, and supports managing and protecting data with controllable and manageable permissions. Cloud Dataflow is a managed service that includes software development kits, or SDKs, for batch and streaming data processing modes, and Cloud Dataflow is also applicable for extract, transform, load, or ETL operations. Then there's Cloud PubSub. This is an asynchronous messaging service. It allows an application to send messages as JSON structures, and on the receiving end is a publishing unit referred to as a topic. These topics are global resources, and what that means is that other applications and projects owned by your organization can subscribe to the topic, thereby receiving those messages in the body of HTTP requests or responses. In this video, we'll look into the benefits of Google Cloud Platform. Some of the main benefits of Google Cloud Platform include that it's a future-proof infrastructure, powerful data and analytics is offered, it provides serverless computing, customer-friendly pricing, data center innovation, as well as advanced security. Let's have a closer look at these. Future-proof infrastructure includes factors like live migration. And that means that you can move Google Compute Engine's instances to nearby hosts, even while they are active and under high load. Google Cloud Platform offers pricing innovations like per-second billing and discounts for sustained use. The platform allows you to configure a wide combination of memory and virtual CPU, helping to avoid over-provisioning when sizing hardware for a particular workload. Fast Archive Restore provides high throughput for right-now restoration of data. Google's load balancer is the same system that supplies load balancing to Google products like Gmail and Google Maps over a global distributed platform. It's super fast and capable of tolerating extreme spikes in traffic. You can take advantage of the Google security model built and maintained by some of the top application, information, and network security experts. This is the same infrastructure that secures Google applications like Gmail and G Suite. Google maintains a global network footprint, boasting over 100 points of presence spanning over 30 countries. Now let's look at powerful data and analytics as a benefit. You can build distributed services for fast results on the platform. BigQuery, Cloud Datalab, and Cloud Dataproc, these are the same services that Google uses. So queries that traditionally take hours or days can now be performed in a fraction of the time. Google Cloud Platform offers powerful applications and tools for working with big data with data processing tools like Cloud Dataflow, Cloud PubSub, BigQuery, and Cloud Datalab, making it easier to use extreme volumes of data to deliver results. Again, these are the same products that Google itself uses. And Google Cloud Machine Learning provides access to powerful deep learning systems that Google uses for services like Google Translate and Google Photos, as well as voice search. With respect to serverless computing, there are no upfront provisioning costs. So resources are allocated dynamically as needed. You simply bring your code and data. It's full management of servers and eliminates the repetitive tasks and potential errors that are inherent in tasks like scaling clusters and applying security patches. With automatic scaling and dynamic provisioning of resources, you pay only for what you use. Let's consider a couple of use cases for serverless computing. Take, for example, web backend. You employ Google's App Engine with the highly scalable NoSQL Cloud Data Store database for a full-scale, powerful backend infrastructure. For Internet of Things or IoT device messaging, combine the real-time geo-redundant Cloud PubSub messaging service with Cloud Dataflow's serverless stream and batch data processing. When considering extract, transform, and load, or ETL, we can combine Cloud Dataflow again for stream and batch data processing with BigQuery for serverless data warehousing. Now, one of the other benefits, customer-friendly pricing. As pointed out earlier, you do not have to commit to a specific deployment size, so no upfront costs are involved. You pay as you go, and with per-second pricing, that means that you pay for services as you require them. So you don't have to maintain a mountain of hardware and have that hardware sitting there idle. And you stop paying when you stop using a service with no termination fees. Google Cloud Platform offers, as another benefit, data center innovations. For example, high-performance virtual machines for fast and consistent performance. Google's global network provides fast networking, performance, strong redundancy, and high availability. Live migration technology means that maintenance of virtual machines is transparent, never requiring downtime for scheduled maintenance. Google maintains very high security compliance and standards, providing some of the most secure infrastructure on Earth. And Google builds its data centers with energy efficiency top of mind. In fact, Google is the first major internet services organization to obtain ISO 50001 certification, and Google has reportedly been carbon neutral for over a decade. Now consider security. Google's security model is an end-to-end process. Google uses practices and controls to secure data access, and when retired, hard disks that contain customer information undergo a data destruction process. With only a few exceptions, customer data stored at rest is always encrypted on Google Cloud Platform. The encryption is automatic and transparent, so no customer intervention or action is required. Google's secure global network helps to improve security of in-transit data, and the combination of cloud interconnect and managed VPN means that you can create encrypted channels from an on-prem private IP environment to Google's network. In addition to that, Cloud Security Scanner assists App Engine developers to identify common vulnerabilities. Google Cloud Platform also allows the configuration of user permissions at the project level for full control of who has access to what resources and at what level. Using tools like Google Cloud Logging and Google Cloud Monitoring simplifies the collection and analysis of request logs, as well as the monitoring of infrastructure services availability. In this video, we'll compare Google Cloud Platform with other major cloud services suppliers. When you're talking about cloud services suppliers, there are really three main suppliers. That's Amazon Web Services, Google Cloud Platform, and Microsoft Azure. The major differences from platform to platform include pricing. And one thing that you should keep in mind when considering pricing is this: how to calculate costing. For example, the pricing for Amazon's EC2 and Azure's Virtual Machines Scalable Computing Service can get pretty complicated, while Google's Scalable Computing Service is perhaps a little less flexible, but the pricing way more straightforward. Another major difference lies in how these vendors name and group the services that they offer. So let's have a look at that. So compute offering. With respect to scalable computing on demand, Amazon Web Services has its Elastic Compute or Cloud or EC2, while Google Cloud Platform offers Compute Engine, and Azure has virtual machines and virtual machine scale sets. For web and mobile apps, we have AWS Elastic Beanstalk and GCP, and I'll refer to Google Cloud Platform hereafter as GCP. GCP's App Engine, and Azure offers web apps and cloud services. For software container management, Amazon Web Services has ECS, and ECS is Amazon's EC2 container service, while EKS is Amazon Elastic Container Service for Kubernetes. Google Cloud Platform provides the Google Kubernetes engine. And I'm quite familiar with that, having a lot of personal experience with GKE, and I can tell you it is very powerful, very flexible, and fantastic. Azure offers AKS, which is Azure Container Service, and Azure Container Instances. For storage offerings, we have object storage. So Amazon Web Services offers Simple Storage Service, or S3. GCP has cloud storage, while Azure has blob storage. As far as archiving, or as it's known, cold storage is concerned, AWS offers Glacier and Data Archive. GCP has cloud storage nearline, and Azure offers backup and archive. With respect to content delivery networks, AWS offers CloudFront, GCP offers Cloud CDN, and Azure has its content delivery network. Now let's look at analytics offerings. For big data, AWS offers EMR and Athena, while GCP offers BigQuery, Cloud Dataflow, Dataproc, Datalab, and PubSub. Azure has HG Insight and Data Lake Analytics. For BI, or business intelligence, AWS offers QuickSight, GCP offers Data Studio, while Azure has Power BI. Now you might be thinking, well, Power BI, isn't that an installable application? Yes, it is an installable application. There are applications that are installable on the desktop or on servers even, but they connect to cloud resources very readily and easily. So that's why I'm including those here. With respect to machine learning, AWS has Amazon Machine Learning, or AML. Google has Cloud Machine Learning, and Azure offers Azure Machine Learning. Now let's consider briefly locations offerings. So really, you should try to choose your data center close to users because it reduces latency and provides better user experience. I mean, that goes without saying. If you're involved in any capacity in networking and administration, you already know that. So here's the thing. AWS has the most global coverage, but unfortunately, there's no coverage in Africa at this point. Google Cloud Platform has good coverage in the US, but not so good in Europe and Asia. And there is none in South America or Africa at this time. But knowing Google, I'm pretty sure that they are in the process of planning those right now. And as far as Azure goes, really they have the second best global coverage behind AWS. But again, there is no coverage in Africa. In this demo, we'll walk through the steps of creating a Google Cloud Platform account. To start, open a browser and navigate to cloud.google.com. You'll see a couple of links on the page indicating try it free, one in the banner and one in the middle of the page. So let's click on this one. And now if you have an account and you've already signed in, you'll be taken to this page, which will allow you to specify, first of all, that you want to have email updates about features and that you agree to the terms of service. If you don't have an account or you haven't signed in already with your Gmail account, then you'll be asked to sign up for a new account. So assuming you already have an account, you can look here and select whether you want to sign up for those features or not. I'll say yes. So we'll sign up for email regarding new features. So you should always review this if possible. So I'll click on Google Cloud Platform Free Trial Terms of Service with my middle mouse button to open it in a new tab. You can see that here. You can right-click to save it somewhere, or you can read it and then go back when you're done and click yes to accept the terms. And you can see here on the right-hand side, it gives you details about the account. So for example, you have access to all Cloud Platform products. There are certain quotas, however, so just keep that in mind. You have a $300 credit for free, and that's awesome. And you have no auto charge after the free trial ends. So they ask for the credit card to make sure we're not a robot, but we won't be charged unless we manually upgrade to a paid account once the 12 months or the $300 credit has been burned through, right? So let's click on agree and continue. And now on this next page, we have to specify whether it's a business account or an individual account. I'm going to click the pencil icon here, hit the drop down and select individual account. And then you enter your individual account information like your address, your location information, how you're going to pay, and the payment details. So what I'm going to do now is I'm going to pause the video. I'm going to enter my personal information, my credit card information. And when I'm done, I'll click Start My Free Trial. And I should be taken to a welcome screen on Google Cloud Platform at that point. Okay, so I'm going to pause the video, enter that information, and when I'm done, I'll resume. Okay, I have entered all my personal information, including my payment information, and now you can see that it's creating my first project by default. And this can take a couple of moments, so again, I'm going to pause the video. Then when it's done, I'll resume. Okay, so here I am. I've logged in now to the Google Cloud Platform with my new 12-month free trial and $300 worth of credit. So I'll click on Got It. Now I can see that I've logged in. You can tour the console and you can explore Google Cloud Platform from here. In this demo, we'll navigate the Google Cloud Platform console. Once you're logged in, by default, you'll be on the dashboard page. And understand this, that Google Cloud Platform resources are fundamental components comprising all Google Cloud services. Resources are organized hierarchically with projects at the top level in the hierarchy. They contain all the other lower level resources, for example, App Engine instances, big data resources, or cloud storage buckets. So I've selected my first project here, and this was the project that was created automatically when I signed up for my trial account. So you should have something similar if you signed up for a trial account. Google Cloud Services themselves are accessible in the left-hand navigation menu. So if you click on this burger menu, you'll see products and services. So for example, these are organized by the product area. So you'll see under compute, there's compute resources, storage resources, networking, stack driver tools, big data, and so on. One of the other things you'll notice right away is section pinning. For any service that you want to have immediate access to at the top of this navigation menu, you can pin the section to the top of the navigation menu by hovering over the section item and clicking the pin icon. Let's say that we want to pin the App Engine section here. So we'll hover over top of that and click the pin icon, and now that will be at the top. Okay, so let's click Home to go back to the Home dashboard. Now this dashboard provides a high-level overview of whichever Google Cloud Platform project you've selected. So here again, I've got my first project selected, right? And here you'll find common, important, and key metrics, billing information, news, and so on. You can also customize the dashboard by clicking Customize in the banner. I'll click Customize. Now, you can hide cards, you can show them, you can reorder them on the page. Each card also has custom options accessible from the Overflow menu when hovering over a card. So, for example, if I want to turn this one off, I want to move billing over here to the middle, all right, and click Done. And when I'm taken back, here's billing, and my other tile is now gone. So let's say I want to bring that tile back. I'll click On again, click Done, and I've customized it. Okay, now click on the Activity tab beside the Dashboard tab. And here, all activities that have taken place across your Google Cloud Platform resources are available. This is actually an activity stream, and depending on your role, and here I'm at the top level, I am the owner, you can see exactly what others are doing in any project. Now you won't see a lot here because this is a brand new account, we just created it. But you can also use filters to drill down and find whatever you're looking for. So for example, you could select whatever projects are available. You could specify a particular user. You can select what kind of category to look for. Under resource type, you can select different resource types. And under date, you can select a specific time frame. You can also search across Cloud Console using the search bar. So if you click in the search bar, you can have instant search access to all your Google Cloud Platform products and resources. So for example, here, let's do a search on BigQuery. Well, there's BigQuery right there. So it returns that. So if I click on BigQuery, then I'm taken to the BigQuery console. I'm going to close this tab though, and I'll go back to my Activity tab. Okay, Google Cloud Identity and Access Management are available from the main menu. So I'll click on the burger menu again here, and I'll click on IAM and Admin. Now this allows you to create and manage permissions for Google Cloud Platform resources. You can add and manage users, create custom roles and assign roles, add service accounts, and grant users, service accounts, and roles fine-grained permissions to resources as required. You can also access the command line from your browser by clicking the Activate the Google Cloud Shell icon up here in the toolbar. So what happens here is now you have access to all Google Cloud Platform resources directly from this command line in the browser. So not only can you access and manage projects and resources using Cloud Shell, but you also know that the Cloud SDK G-Cloud command line tool and other utilities are always available. They're always up to date and fully authenticated from within here. So it's very convenient. Now, one last thing, clicking on the burger menu again and click on support. And this brings you to the support page. And actually, I'm going to close the Cloud Shell at this point since we're done with that. Here you have an overview page with details and documentation about support. In this demo, we'll walk through the steps of creating a project. Projects are at the top level of the resource hierarchy in Google Cloud Platform. And by default, when you sign up for an account, you're going to be provided your first project. It'll be created automatically. If you want to add one later on or manage them, you can do so from the top menu here. So I'm going to click on the down arrow beside my first project, and you can see here that I can click to manage resources within the project. I can click the plus icon here to create a project. So let's go ahead and do that. Now you give your project a name. And with a free account, just be aware that you have 12 projects in total within your quota. Okay, so let's call this project GCDE. Okay, and now we see that we're automatically given a project ID of GCD-197015. You can click to edit that. So for example, if you want to edit it, just click to edit. But you see it has to be between 6 and 30 characters. So let's type GCDE-100. Well, it has to be available as well across the Google Cloud. And it's not here. So let's type another 0, Google Cloud 1000. So that's available. Let's go ahead and create that. So we'll click Create. And that creates our project. You can see the status in the notifications here that there's some activity going on and it's creating a project. Now, if I go over to Activity at this point, to open my activity stream, I'll find at this point, I don't see any activity with respect to that project yet. Let's go back to Dashboard and back to Activity. And now under Projects, we'll click the down arrow and we can see the GCDE project here. We'll select that one as well and click OK. So now we're looking at all projects. Okay, and you can see the information about that project being created. Let's go up here and select a project. We'll select this project, which we just created, by clicking on it. Go back to the dashboard. And there's our project information on the dashboard. So now we're ready to start adding in resources and working with those resources within this new project. In this demo, we'll take a first look at Google Cloud Platform's BigQuery tool. Okay, so I've logged into my Google Cloud Platform account. I've got my GCDE project as current project. What I'm going to do is click on the burger menu to expand, and you'll see that I've got BigQuery pinned now to the top of my menu. Otherwise, you have to scroll down and find it under Big Data, and then click on BigQuery and it opens in a new tab. You'll see already used queries here as well, and you can filter those queries, or you go and start a new query, and that's what we're going to do. So what we're going to do is we're going to do a query against one of these publicly available data sets. So we'll use this one, samples, and this is the table that we're going to query on, natality. You can see the columns and the type of data and the constraints of that data, as well as a description. Okay, so let's go ahead and we'll click on Compose Query, and a new query editor opens. Now I'll go over to my text editor where I have specified a query here. So I'm going to copy this query. So I'll highlight it, right click, select copy, back over to BigQuery, and I'll paste that in the query editor by right clicking inside it and selecting paste. And now under the query editor, you'll see this validator. And this validator icon will either be green or red. And you can see that it's red right now. And it's red because there's a problem. So if I click on Open Validator here, then you'll see invalid table name. That's strange. And then in brackets, we see another note here. Try using standard SQL. And we also have a reference page that we can open up. We don't need to do that though, because let's go back over to the text editor and see what's going on here. This is what we forgot to bring along. It's not a comment. This is actually a prefix. And you can set the SQL dialect variant to use either legacy SQL or standard SQL based on the prefix that you're using and by the default. The default is legacy SQL, and that's why it doesn't recognize the table name. So the other thing to recall here, so these are the two variants, legacy SQL and standard SQL, but don't forget to include the pound sign. Okay, you need that. Let's copy standard SQL. We'll highlight it, right click, select copy, over to BigQuery, and to create a new line, then we'll press Control V to paste that in. And now you can see the validator turned green, so we're good to go. So we can close this validator. It says this query will process 3.49 gigabytes when run. So let's close the validator and let's run the query. Okay, so there's our result set. Now we can either download a CSV, JSON, save it as a table, save to Google Sheets. We have some other options here. Now here's the problem though. I don't want any states to have a null value, right? So what I'm going to do is I'm going to improve this SQL query. What I'll do is I'll press enter to open a new line here, and I'll type where state, and I'll capitalize is not null. Okay, and you can see the validator did turn green. So now we should run this query and see that we will have no states that are listing a null value, right? So we can scroll through these and we won't find a null value. So now we can either save to Google Sheets or save as table to view it. If we click on Save as Table, we're presented with the Copy Table dialog. And if we specify a destination data set, so for example, my result, and click OK, we'll see an error, not found, data set, GCDE 1000, not found, GCDE-1000 my result not found. And that's because that data set doesn't exist. So what we need to do is we need to go over here to our project and click the down arrow here. And in the context menu, we'll click Create New Data Set. Let's call this data set My Results. For data location, we'll click the drop-down list and we'll select US. We'll have the data expiration set at never. Let's click OK so we can see that data set here. So now, if we click on Save as Table, we can see that it's got that destination data set selected by default. It's the only one that we have. There's destination table under the data set. So if you click OK, we'll see, if we expand My Results, we've got a table here called Results, and there is our results table. Now let's go back to this query one more time. Run this query again, and here's our result set. And now if we want to save to Google Sheets, we'll click on Save to Google Sheets, saving the results to Google Sheets. Now we see that it's done. We can click to view in Google Sheets. Now you may be asked which account you want to save it to if you have more than one Gmail account. But for me, I've already done this a couple of times, so it's not asking me which account I want to save it to. So I'm going to click to view, and there's my result set. And notice that no states are null. Okay, so that is a quick look at Google Cloud Platform's BigQuery tool. In this exercise, you'll practice what you learned about Google Cloud Platform data products and services. You will describe the global distribution structure of Google Cloud Platform resources and be prepared to discuss zones and regions. List the categories of the most commonly used Google Cloud Platform services. Identify the benefits associated with using the Google Cloud Platform. List the main suppliers of business cloud services and the major differences between them. And list the Google Cloud Platform data and analytics products and services. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Okay, task 1, global distribution structure. You should understand that resources on the Google Cloud Platform are located around the world in global data centers. And this global distribution provides redundancy as well as reduced latency. You should understand also that resources reside in regions or zones. And a region is a particular geographical location where resources run, and each region contains one or more zones. Along the same lines, regional resources can be consumed by any resources within that region, including any zone within that region, while you should understand that zonal resources are available only to resources within the same zone. Okay, step 2, or task 2, was to list the categories of common Google Cloud Platform services. And those categories include computing and hosting, storage, networking, and big data. Now, identify the benefits associated with the Google Cloud Platform. One of the benefits is future-proof infrastructure. You also have powerful data and analytics, serverless computing, customer-friendly pricing, data center innovation, and security. Now, list the main suppliers of business cloud services and the major differences between them. Well, the 3 main suppliers of those cloud services are, first, there's Amazon Web Services, or AWS, then Google Cloud Platform, or GCP, and Microsoft Azure. So those are the main 3 suppliers of business cloud services. And the major differences are the cost or the pricing. And recall that I also mentioned that there are complexities with respect to costing and pricing that have to be taken into account as well. In addition to that, the other major difference is the naming and grouping of the services provided by each of the main vendors. Now, list the Google Cloud Platform data and analytics products and services. So first off, we have distributed services for fast results, and this includes BigQuery, Cloud Datalab, and Cloud Dataproc. Then we have applications and tools for working with big data, including Cloud Dataflow, PubSub, BigQuery, as well as Cloud Datalab. And finally, machine intelligence. And this is provided by way of Google Cloud Machine Learning. In this video, we'll explore the highly scalable virtual machine management provided by Google Compute Engine. Google Compute Engine has predefined machine types from micro instances to instances with 96 virtual CPUs and 624 gigabytes of memory. The tier of available configurations include standard, high memory, and high CPU. With Compute Engine, you can create virtual machines with the configuration that's customized for your particular workloads. Again, from 1 to 64 virtual CPUs and up to 6.5 gigabytes of memory available for each CPU. This flexibility means that you can potentially save money because you don't have to overcommit to a hard-sized, basically oversized virtual machine. No, instead you can customize to optimize your virtual CPUs and memory. By offering custom machine types and predefined machine types, this flexibility means that you can create infrastructure that is customized for your organization's particular workload requirements. Compute Engine is very scalable, and there is no commitment, meaning that you aren't locked into whatever configuration you initially choose. So, for example, Compute Engine offers a start-stop feature that allows you to move your workload to smaller or larger custom machine type instances or to a predefined machine type. In this video, we'll consider the various cloud storage options available on Google Cloud Platform. Google Cloud Storage offers a number of different storage and database options. Which you choose depends on the application, the data type, and the workload profile. Types of data supported include structured, unstructured, transactional, as well as relational data. So let's have a look at the different options. First, persistent disk. This is fully managed block storage suitable for virtual machines and containers, so for Compute Engine and Kubernetes Engine instances. It's also recommended for snapshots for data backup. Typical workloads include disks for virtual machines, read-only data sharing across multiple virtual machines, as well as quick and durable backups of virtual machines. Google Cloud Storage is a scalable, fully managed, reliable, and cost-efficient object and blob store. It's recommended for images, pictures, videos, objects, and blobs, as well as unstructured data. Common workloads include streaming and storage of multimedia, as well as custom data analytics pipelines, and archives, backups, and disaster recovery. Next is Cloud Bigtable. Cloud Bigtable is a scalable, fully managed, NoSQL, wide column database, and this is suitable for both real-time access and analytics workloads. Cloud Bigtable is indicated for low latency read-write access, high throughput of analytics, as well as native time series support. Typical workloads include Internet of Things, streaming data, finance, ad tech, which is marketing, as well as monitoring, geospatial data sets and graphs, and personalization. Cloud Data Store is a fully managed NoSQL document database for web and mobile applications. It's recommended for semi-structured application data, as well as hierarchical data, and durable key value data. Typical workloads include user profiles, product catalogs for e-commerce, and game state, for example. Google Cloud SQL is a fully managed MySQL and PostgreSQL database service, and it's built on the strength and reliability of Google's infrastructure, of course. It's recommended for web frameworks, as well as structured data and online transaction processing workloads. Common workloads include websites and blogs, content management systems and business intelligence applications, ERP, CRM, and e-commerce applications, as well as geospatial applications. Google Cloud Spanner is a mission-critical relational database service with strong transactional consistency at global scale. It's recommended for mission-critical applications, as well as high-throughput transactions, and for scale and consistency requirements. Typical workloads include ad tech and financial services, as well as global supply chain and retail. Google BigQuery is a scalable, fully managed enterprise data warehouse with SQL and very fast response times. Consequently, it's recommended for OLAP workloads, big data examination, investigation and processing, as well as reporting using business intelligence tools. Typical workloads include large data analytical reporting, data science, and advanced analyses, as well as processing big data using SQL. And Google Drive This is a collaborative space for storing, sharing, and editing files, including Google Docs. It's recommended for interaction with docs and files by end users, collaboration, as well as file synchronization between cloud and local devices. Typical workloads include global file access via web, apps, and synced clients, coworker collaboration on documents, as well as backing up photos and other forms of media. Google Cloud storage options include a separate line for mobile. And for example, we have cloud storage for Firebase, which is a mobile and web access service to cloud storage with serverless third-party authentication and authorization. Firebase Real-Time Database is a real-time, NoSQL JSON database for web and mobile applications. Firebase Hosting is production-ready web and mobile content hosting for developers, and Cloud Firestore for Firebase is a NoSQL document database. Cloud Firestore for Firebase serves to simplify storing, querying, and syncing data for web apps and mobile apps, especially at global scale. In this demo, we'll create and start a Compute Engine virtual machine image using Cloud Platform Console. Okay, to get started, click on the burger menu for Products and Services, scroll down and under Compute, point to Compute Engine, and select VM Instances. Okay, if necessary, choose your project. I've got my project already selected here, but if you want to, you can select whatever project and then click Open. Then click Create. Okay, on the Create an Instance page first, we'll specify a name for the instance. I'll call this instance My Instance. And for the zone, I'll select US West 1-A. Now, for machine type, we can specify whatever type of machine we want. So we can customize, or we can specify one of the predefined machine types here. We'll just leave the default 1 virtual CPU and 3.75 gigs of memory. We can also deploy a container image to this VM instance, but we won't do that for this demo. Scrolling down under Boot Disk, we'll click Change. Okay, and this allows us to select the operating system image or application images if we want, custom images, snapshots, as well as existing disks. So we'll just go to OS Images. We'll leave the default Debian GNU Linux 9. And now for boot disk type, right now it's standard persistent disk. If I click the down arrow, I also have the option of SSD persistent disk. That's what I'm going to choose there. And for size, I'm going to choose 100 gigs. So I'll specify 100, and then I'll click Select. Now we have a couple of options under Identity and API Access. We'll leave the defaults, but just so you can see, you have this option, which is the default service account, or an App Engine default service account that you can select from as well. And for access scopes, you can specify default access, which is what we'll leave, full access to all cloud APIs, or set access for each API. We'll leave the default. You can also specify to allow HTTP or HTTPS traffic. And now, if you expand management, disks, networking, and SSH keys by clicking the down arrow here, this allows you to specify additional disks. If you click on disks, you'll see here that you have the option to delete the boot disk when the instance is deleted, which we'll leave checked. And we'll leave encryption at automatic. And if you want to add additional disks, this is where you would click Add Item. So you would click Add Item. You can specify a name, so create disk, then the mode, and then you specify what to do when deleting the instance. Okay, so we'll leave the defaults. We won't add an additional disk, but now you can see how to do that. And now we're ready to create the machine, so let's click Create. Now what this does is this will create the instance and start it up. And then under the Connect column here, we'll see an SSH option. If you click the down arrow here, you can see you can open in a browser window on a custom port, view the gcloud command, or use another SSH client. We'll just click to open in a browser window. Now it's transferring the SSH keys to the virtual machine. Okay, and there we are. We're connected to this virtual machine. So now if I type ls-al, I should see a listing of the files on this machine. And to close it, just type exit and press enter. In this video, we'll explore Google Cloud Shell. Google Cloud Shell is a shell environment for the Google Cloud Platform. You can use it to manage projects and resources, and there's no need to install the Google Cloud SDK. It comes pre-installed. It can also be used with the gcloud command line tool and any other utilities. The Cloud Shell is a temporary compute engine VM instance. When you activate Cloud Shell, it provisions a G1 small compute engine instance on a per user, per session basis. The environment persists while the session is active. It also comes with a code editor, which is a beta version based on Orion, the open source development platform. You can also use Cloud Shell to browse file directories, view, and edit files. Cloud Shell features include command line access, so you access the virtual machine instance in a terminal window, and it supports opening multiple shell connections to the same instance. That way you can work in one to, say, start a web server, and then work in another shell to perform some other operations. You can also use Cloud Shell to launch tutorials, open the code editor, and download files or upload files. It comes with 5 gigs of persistent disk storage, and it's mounted as the home directory on that virtual machine instance. And this is on a per user basis across multiple projects. With respect to authorization, it's built in for access to projects and resources that are hosted on the Cloud Platform. Because you are already logged in to Cloud Platform, it uses those credentials. So there's no need for additional authorization. So you have access to platform resources, but the thing is, what access you have to those resources depends on the role that's been assigned to the Google Cloud Platform user that you've logged in with. Cloud Shell also comes pre-installed with language support for Java, Go, Python, Node.js, PHP, Ruby, as well as .NET. Cloud Shell comes with a number of pre-installed tools. So for example, we have Linux shell interpreters and utilities like Bash and SH for your shell interpreters, and it comes with the standard Debian system utilities. For text editors, you've got Emacs, Vim, and Nano. For source control, Cloud Shell supports Git and Mercurial. For Google SDKs and tools, you've got the Google App Engine SDK, the Google Cloud SDK, as well as GSUtil for cloud storage. It also comes pre-installed with some build and package tools, for example, Gradle, Make, and Maven, as well as NPM, NVM, and pip. Additional tools include the gRPC compiler, the MySQL client, Docker, and IPython. Cloud Shell also provides a web preview function that allows you to run web apps on the virtual machine instance and preview them from the Cloud Console. The web applications must listen for HTTP requests on ports within a range of 8080 to 8084. And those ports are only available to the secure Cloud Shell proxy service, and that restricts access over HTTPS to your user account only. In this demo, we'll activate and use Google Cloud Shell. Okay, so I've logged into my Google Cloud Platform account, and you can see I've selected this project. To activate Google Cloud Shell, you just click on the Activate Google Cloud Shell icon in the toolbar, and that opens underneath the current window, or within the current window, that is. And now, to pop that out into its own tab, which I like to do because I like to see the full output for my commands, so I'll just click on the Open in New Window icon, at the top of my Cloud Shell. Okay, so now it's activated and it's in its own tab. Now I can open additional tabs by clicking the Add Cloud Shell Session, and that will open a second session right there. So I'll just close that. We won't need that for this demo. But now, by default, the thing is, the current active project is the project you have currently selected. Now, to list your config defaults, you just type gcloud config list. And there are all my defaults. Now I'll just type clear and press enter. Now to set any defaults, you use gcloud config set. So let's say, for example, that I want to set the project. Well, I type gcloud config set project, and my project is actually this project here. And even though that's the current one, I'm just going to reselect it here, and then I'll click beside that command, press Control V to paste it in, and press enter, and it will come back and say that the property was updated. Okay, so let's clear that. So now let's say that we want to set up my default compute zone. So gcloud config set compute /zone, and we'll say that I want to set it up as US-West1-A. Okay, so now that property is updated. So now if I do another gcloud config list, I'll see now that I've got my compute zone configured here, and my project, the default, is right here. Okay, so now let's clear this by typing CLEAR and pressing enter. Now you can also see what components that come pre-installed, and you can also see the current Cloud SDK version you're using as well as the latest available version by typing gcloud components list. And there you can see that the current Cloud SDK version is 194.0.0, but there is a more recent version, 195.0.0. And here are all the components that are installed. And you can see under the status column which ones are installed, which ones aren't installed, and which ones have updates available. You also have a name column, an ID column, and a size. Now, if I want to update, then first I'm just going to clear this by typing clear and pressing enter. And now I'm going to type gcloud components update. Okay, and you can see the message there, and it gives us a helpful hint. So the thing is, we have to do a sudo here. So let's up arrow, and that's another feature. It comes installed, the shell environment that is, comes installed with standard Debian system utilities. So up arrow and down arrow, for example, to scroll through the list of most recent commands. So now we'll type sudo gcloud components update. And it asks us if we want to continue. We'll type Y and press enter. And now this will take a couple of minutes. So what I'm going to do at this point is I'm going to pause the video, and when it's done updating, I'll resume. Okay, it's not done installing yet, but I wanted to resume anyway so that you could see how it's progressing through. First, it created the update staging area. Now it's uninstalling and installing updates as required with my gcloud components update command. Okay, now we're just about finished. It's creating the backup and activating the new installation. Okay, so now we can see that the update is now complete. So let's clear this by typing clear and pressing enter. And now we'll up arrow to get the gcloud components list command back here. And let's press enter now and see what we've got. So we've got the current Cloud SDK version of 195.0.0. We've got the available version, so we're up to date. So everything has been updated. So let's clear this again by typing clear and pressing enter. And now, since the shell environment again supports the standard Debian system utilities, well, that means that we can, for example, create an alias for a command. So let's type alias C equals clear. So now if I type C, that's like issuing a clear command. That also means that you can configure variables and so on by placing those directly in the .profile file in the tilde or $home directory, and that's where we're at right now. So if I type pwd, this is my home directory. If I type echo $home, again, same thing. So if I go tail to list the last 10 lines of .profile, you'll see here that I have in my profile, I've set up some environment variables. And I've also set up an alias command here. So in actuality, anytime that I launch the shell, I will have that alias set up on this machine. Those environment variables will also be populated with the values that you see there. Okay, so that's Cloud Shell. In this video, we'll create and start a VM instance in Cloud Shell. Okay, I'm logged into my Google Cloud Platform account, and I've activated Cloud Shell. You can see that open here in its own tab. Now let's go over to the README. There's a prerequisite for this demo, and that is to enable Compute Engine API. Now I've already got that enabled, but to enable that, just go over to Cloud Platform Console. You can either click the burger menu to open up the APIs and services, or you can click Go to APIs Overview here on the dashboard, and that will list the APIs for you. So you can click Enable APIs and Services. And so, for example, if we want to list Compute Engine, so there's the Google Compute Engine API. Now, like I said, I've already got that enabled, so if I click on it, you'll see that it's already been enabled. We'll say API enabled here. Okay, so that's how you enable it. Now, one other little trick. So let's go back to the README first. So before we get to the gcloud beta compute instance create command, you can see that I've listed a couple of defaults here. Now, yours are going to be different than mine. This project has got to be unique across Google Cloud Platform. So your project will be named differently. I've also just decided to set my default compute zone to US West 1-A. So for example, if I highlight these two commands, right click, select copy, and go over to Cloud Shell here, I'll click inside, press Control V to paste those commands in. The second command needs me to press enter to run, and you can see that now I've got my defaults updated. So I'll type clear and press enter. Now back over here again. Now this command, yes, very long command, and I have word wrap on so that we can see everything. Otherwise I'd have all kinds of line breaks in here, and I just wanted to be able to show the entire command. Now you can see that there are a number of different options set here. Some of them aren't strictly necessary, and how I got this command is by going over here to Cloud Platform. Let's click the burger menu. And under Compute, we'll point to Compute Engine. We'll click VM Instances. And now you can see I've got this VM instance running. So if I click here to open that VM instance, then I can see all the options for that VM instance here. And I can also see the equivalent REST for this machine. But when you're first creating one, you can actually see the values in the format for gcloud command or for the shell command. Also, if you click edit here, you can edit this VM. Okay, so let's go back to the instance details. We'll click on the instance and we'll delete this because we're going to recreate one anyway. So now while that's deleting, just click on Create Instance, and you can see I'm just going to leave the default name instance 1 here. I'm going to leave all the defaults. I'm going to leave everything defaulted there. And now you can see at the bottom the equivalent REST or command line. So if I click on command line here, well, look at, there is my command line command right there. So if I highlight everything, right click and select copy, I can copy that and paste it directly into Cloud Shell, or I can click here to run it directly in Cloud Shell. Let's just close that that's not the machine we want to create. The machine we're creating is in a different zone. It's got a different name. It's got a different boot disk. It's larger, and it's got SSDs as far as the local persistent storage goes. So let's go back over here again to the README. Now I've highlighted this entire command. I'm now going to right-click, select copy. Let's go back over to Cloud Shell. We'll click inside Cloud Shell, press Control-V to paste that entire command in. And you can see the basis for this command is gcloud beta compute. Now I've inserted the project there. Instances create and the name of the instance. I'm also specifying the zone here. So strictly, I didn't really need to have my zone set up there. I also didn't need to specify my project here. So I suppose I could have reduced this command in length by not issuing a project or a zone, since I've already got the defaults set up. However, we're going to leave this as is. You can see the machine type here is N1-standard-1. I've also got the image project is Debian Cloud. Boot disk size is 100, and that's gigs. The boot disk type is persistent, and it's SSD. And the boot disk device name is my instance. So let's press enter and start creating this virtual machine instance. Now if I go back over here to Cloud Platform Console and I refresh, you can see that it's showing my instance is already created. Let's go back over to Cloud Shell and see, yes indeed, it completed, and it gives us the results here, including the name, the zone, machine type, whether it's preemptible or not, the internal as well as external IP, and the status is running. So just to prove that it's running, let's go back over here. Let's click the down arrow beside SSH. We'll click on Open in Browser Window. You can see that that pop-up is blocked. If I just click on it again, it'll open anyway. And now this is going to open in a secure shell connection in this browser window. So you can see it's transferring the SSH keys to the virtual machine. And there it is, ls-al to list all the files in my home directory. Okay, and now to shut this down or to exit the secure shell, let's type exit and press enter. Okay, and now we can also delete this from the command line. It's always a good idea to delete resources you're not using. And for this particular step, we're going to issue a gcloud beta compute instances delete and the name of that instance. So let's highlight this entire command. We'll right click, select copy, back over to Cloud Shell. Let's clear this. I've created an alias to clear, and that alias is C. So if I type C and press enter, it's just like typing clear. And now I'll press Control-V to paste that gcloud beta compute instances delete command into Cloud Shell. I'll press enter. Now it'll ask me if I want to continue. I'll type Y and press enter. And now while that's working, let's go back over here to Cloud Platform Console and the VM Instances page, and let's refresh this. And you can see it says here, if I hover over it, the instance is being stopped. So first it stops it, then it deletes it. Let's go back over to Cloud Shell. And now you can see that it has been deleted. Okay, so if I refresh this again, it shows no more VM instance. All right, so we've successfully created and started a virtual machine instance from Cloud Shell and then deleted it. In this demo, we'll create a cloud storage bucket using the gsutil tool in Google Cloud Shell. gsutil is a Python application that allows you to access cloud storage from the command line. You can use gsutil to do a number of things with cloud storage buckets and also perform object management tasks like creating and deleting buckets, uploading, downloading, and deleting objects, listing buckets and objects, moving, copying, and renaming objects, as well as editing object and bucket access control lists. So before we get started, I just want to show that I've logged into my Google Cloud Platform here, and I've already activated Cloud Shell. So let's go over to the README for this demo. And you can see there's one prerequisite to enable Cloud Storage API. Now, if you want to set defaults, this is how you do it. I've already set my defaults, so I won't run these commands in the Google Cloud Shell. But note this, that you need Python 2.7. Now, this is already installed in Google Cloud Shell, but if you're using Cloud SDK on your local machine, you'll need to install Python 2.7. So to see if you have GSUtil tool installed, type gcloud components list. So let's go back over gcloud components list. And there you see the list of applications and tools installed. And you can see that the cloud storage command line tool is indeed installed. All right, so let's clear this by typing C and pressing enter. C is just an alias for clear, and I set that in my .profile file. Back over to the README. Now, GSUtil includes a help page. So just type GSUtil help if you want to see a list of available commands. So let's go back over here. So GSUtil help, and that lists all the commands and options with GSUtil. Let's clear this by typing C and pressing enter one more time. Now here is the syntax that you're going to use to create a bucket using GSUtil. Just GSUtil MB for make bucket, optional project name, and -C is the storage class. That's optional. It'll just use the default storage class. And -L is the bucket location. And then you specify the URL for that cloud storage bucket. All right. So let's try this. Let's try GSUtil MB // my bucket. So I'll highlight that command, right click, select copy, and let's go back over to Cloud Shell. Click inside the shell, press Control V to paste that command, and let's see what happens. Okay, and you can see service exception 409, bucket, my bucket already exists. So I'll clear this by typing C and pressing enter. Back over to the README, and you can see the note here. So note what happens to the first command. So it should throw an error, and it did, because the bucket name that we're using is pretty generic. And obviously somebody else across cloud storage has already used that. And that's the thing. The name of your bucket has to be unique across cloud storage. So this one might work, however. Let's try this one. My bucket 10,001. So let's right click after highlighting, select copy, over to Cloud Shell, Control V to paste that in, and press enter. And lo and behold, it's created. Okay, we'll type C and press enter again to clear that. Back over to the README. Now to see the buckets that you have in cloud storage, just type GSUtil ls for list. And you can even use GSUtil cp to copy local files to the bucket. And first, what we're going to do is we're going to use the touch command. That's a standard Debian command to create a file, touch sample.png. So we're going to create a fake image in our home directory. Then we're going to use GSUtil cp to copy that up to the new bucket that we just created. So let's go ahead and we'll actually copy both of these commands. So we'll highlight, right click, select copy, over to Cloud Shell, click inside, press Control V. Now you can see that the first command already executed successfully. Let's just erase this first and just double check. So ls, and there you can see the sample.png file. Let's go back to the README and we'll copy that command over again. So we're going to copy that sample.png file up to the bucket. So back over to Cloud Shell, we'll type C and press enter to clear that, and Control V to paste that command in. So GSUtil cp, the name of the file, and that's a file local to this machine, and gs : / my bucket 10,001. Okay, it says object completed over one object. So now let's go over to Cloud Platform Console. We'll click on the burger menu here, and we'll click on storage to bring up storage browser. And there you can see our new bucket. Now if we drill down into the bucket, we'll see that there's the sample.png file that we copied up. Okay, now it's always a good idea to clean up after yourself, right? You don't want to incur any charges if you don't have to. So to do so, what we can do is we can use this command, right? gsutil rb for remove bucket, or gsutil rm-r to remove the bucket and anything underneath it. So let's copy these commands. We'll highlight both, right click, select copy, over to Cloud Shell, click, and then press Control V to paste those commands in. And now the first command is going to fail, and you can see it did. Not empty exception. The bucket's not empty. So in order to use RB for remove bucket, it must be empty. However, this command, gsutil rm-r, will remove all the contents and the bucket. So let's press enter to run that command. Okay, and we can see that the operation completed. Let's go back over here to the console, and what we'll do is we will go back to buckets, and we'll see now that we've got no buckets. So we successfully cleaned up after ourselves. In this video, we'll explore Google Cloud Platform concepts in big data analytics. Modern applications typically generate large amounts of data from many different sources. Devices or sensors can capture raw data in unprecedented volumes, and this data is perfect for analysis. This analysis can provide insight into an organization's operating environment and business. BigQuery is a serverless, highly scalable enterprise data warehouse on Google Cloud Platform. It's fully managed, so no infrastructure to manage, eliminating the need for a database administrator, so an organization can focus on analyzing the data using SQL. It enables real-time capture and analysis of data by creating a logical data warehouse. And with BigQuery, you can set up your data warehouse in minutes and start querying against huge amounts of data. Cloud Dataflow is a unified programming model and managed service from Google Cloud Platform using Apache Beam SDK. Apache Beam SDK supports powerful operations that resemble MapReduce operations, powerful data windowing, and very fine correctness control against streaming or batch data. It's used for a wide range of data processing patterns, including against streaming and batch computations and analytics, as well as extract, transform, load operations. Since it's fully managed, it lets you focus on operational tasks like capacity planning, resource management, and performance optimization. Cloud Dataproc is a fully managed and fast cloud service that is used to run Apache Spark and Hadoop clusters. You can take advantage of Apache Big Data ecosystem using tools, libraries, and documentation for Spark, Hive, Hadoop, and even Pig. Features include the fact that it's fully managed, and that means that you've got a managed deployment, logging, as well as monitoring. This means an organization can focus on the data, not the cluster, and clusters are scalable, speedy, and robust. With Cloud Dataproc, clusters can also utilize Google Cloud Platform's flexible virtual machine infrastructure, including custom machine types, as well as preemptible virtual machines. So this provides for perfect sizing and scaling. Since it's on Google Cloud Platform, Cloud Dataproc integrates with several other Cloud Platform services like Cloud Storage, BigQuery, Bigtable, Stackdriver logging and monitoring, and this results in a comprehensive, powerful data platform. Versioning lets you switch versions of big data tools like Spark, Hadoop, as well as others, and you can operate clusters with multiple master nodes and set jobs to restart on failure, ensuring high availability. In this video, we'll explore Google's Cloud SQL service. Google's Cloud SQL is a fully managed database service that simplifies the creation, maintenance, management, and administration of relational databases on cloud platform. Cloud SQL works with MySQL or PostgreSQL databases. Cloud SQL offers fully managed MySQL Community Edition database instances in the cloud, and these are available in the US, EU, or Asia. Cloud SQL supports both first and second generation MySQL instances, and data encryption is provided on Google's internal networks, as well as for databases, temporary files, and backups. You can use the Cloud Platform Console to create and manage instances. The service also supports instance cloning. Cloud SQL for MySQL also supports secure external connections using Cloud SQL Proxy or SSL. It also provides automatic failover for data replication between multiple zones, and you can import and export databases either with MySQL dump, or you can import and export CSV files. Cloud SQL for MySQL offers on-demand backups and automated point-in-time recovery, as well as Stackdriver integration for logging and monitoring. Cloud SQL for PostgreSQL is a beta service from Google supporting PostgreSQL 9.6 database instances in the cloud, and these again are available in US, EU, or Asia. It supports custom machine types and up to 416 gigs of RAM and 32 CPUs, as well as up to 10 terabytes of storage, and that can also be increased if required. Similar to Cloud SQL for MySQL, you can use Cloud Platform Console to create and manage instances, and data encryption is provided on Google's internal networks and for databases, temporary files, and backups. Cloud SQL for PostgreSQL supports secure external connections using the Cloud SQL Proxy or SSL. You can use SQL dump to import and export databases, and Cloud SQL offers PostgreSQL client-server protocol and standard PostgreSQL connectors support. Cloud SQL for PostgreSQL offers on-demand and automated backups, as well as Stackdriver integration for logging and monitoring. In this demo, we'll create and interact with a MySQL database using Cloud SQL. Okay, so I'm logged into my Google Cloud Platform account. I'm going to click on the burger menu, and I'm going to scroll down, and I'll click on SQL under Storage. Okay, now what I'm going to do is I'm going to unmaximize this window, and I'm going to show this window and my README at the same time. So here I am on the Cloud SQL page, and I'm going to click Create Instance. I'm going to leave MySQL selected, and I'll click Next, and I'm going to click Choose Second Generation. And now we'll enter the instance information. So we'll call this MySQL instance. And now we have to set a root password. So you can either show it or hide it. I'll hide it, and I'll enter my password. You can leave the rest of the configuration at the defaults, but you can also click to show more configuration options, and you can drill right down into labels, maintenance schedule, database flags, authorized networks, and so on. But we'll hide those configuration options. We don't need those. And we'll click on Create. Now it'll return us to the instances page, and you'll see now that it's initializing the instance. Okay, so our instance has now initialized and started, and we can connect to it using the MySQL client in Cloud Shell. So over here in the README for this demo, this is where we're at right here. We have two choices. We can either start or activate a Cloud Shell manually and optionally set some default configurations, or we can connect to it using the instance details page. To do that, click on the instance, and on the instance details page, scroll down, and we'll click Connect using Cloud Shell. I'm just going to pull this up a little bit so we have more room. Okay, so the connection string was populated in Cloud Shell automatically. So we'll just press Enter to connect as root. And this is where we're at. We're going to enter the root password. And you just have to wait a couple of minutes until it's done whitelisting the IP for this connection. And you saw that notification saying done. So it made a modification to the instance whitelisting the IP for this connection. And now we enter the password. So click in the shell and enter the password that you used and press Enter. So now we're at the MySQL prompt. So first what we'll do is we'll create a database called blog. So I'll highlight this command, right click, select copy, click inside shell at the MySQL prompt and press Ctrl V and then press Enter. And we can see that it was successful. Now we'll insert some sample blog data into our new database. So first what we have to do is we have to specify to use blog. Then we create the table blogs, and it's got a couple of columns, blogger name, content, and an entry ID, and that's the primary key you can see here. Okay, so let's highlight these two commands. We'll right click, select copy, over to shell, click inside, press Ctrl V. The first command completed, so we'll press Enter to execute that second command. And now we'll insert some data. So let's copy these two insert commands. We'll highlight, right click, select copy, click inside the shell, press Ctrl V. Okay, so we should have some data. So let's type select star from blogs. Don't forget the semicolon. Press Enter. And there you see is our data. Now to exit, you just type exit, press Enter. And it's always a good idea to clean up after yourself. So what I'm going to do is I'm going to close the Cloud Shell. I'm going to go back to our instance. Now we'll scroll up to the top of the instance details page. Click the ellipsis and we'll select delete. Now we have to type the instance name, MySQL instance, and click delete. And we're done. In this demo, we'll create and interact with a PostgreSQL database with Cloud SQL. Okay, I'm logged into Google Cloud Platform. I'm going to click on the burger menu here at the top, and I will scroll down, and under Storage, I'll click SQL, and that brings us to the Instances page, and I'll click Create Instance. Now, I'm also going to unmaximize this window. I'm going to have it on this side, and I'll leave the README open on this side as we follow through. Okay, so here on the Create an Instance page, I'm going to click to select the PostgreSQL beta option and click Next. And now we enter our instance information. So this is what we're going to enter for our instance ID, my PSQL instance. So I'm just going to highlight that, right click, select copy, and I'll paste that right in here. Now I'll hide the password and I'll enter the password for the Postgres user. And the rest of the values we can leave at their defaults. You can also specify more options here. So click on Show Configuration Options and you can see that you can specify machine type, auto backups, authorized networks, and so on. We'll hide these options, we don't need them, and we'll click Create. And now it'll return us to the Instances page, and you'll see that our instance is now initializing. This can take 3 or 4 minutes, so at this point I'm going to pause the video, and then when it's done initializing and it's started, I'll resume. Okay, our PostgreSQL instance has initialized and started. And now at this point, we can connect to it using the PSQL client in Cloud Shell. So this is where we're at right now. We have a couple of options. We can either manually activate a Google Cloud Shell, and we can optionally specify some configuration settings, or we can connect directly to it by clicking Connect using Cloud Shell from the Instance Details page. This is the easiest way, so let's go ahead and do this. You're doing the same thing. Basically, we're just not manually activating Cloud Shell and setting our options. So we'll click the My PSQL instance, and on the Instance Details page, scroll down and click on Connect using Cloud Shell. Now at this point, what's going to happen is this string is going to be populated in the Cloud Shell here, and we'll just press Enter. I'm going to move this up a little bit to give us more room. Okay, so now you can see that connect string here. We're connecting as the Postgres user. So I'll just click inside Cloud Shell and press Enter. Now it's going to whitelist our IP. So it's altering the settings in the instance that we've created. So it can take a couple of minutes, a few seconds. Usually doesn't take all that long actually. But that's what it's doing. It's whitelisting the IP for this incoming connection. Now once it's done, you'll see a notification there saying it's done. So shortly thereafter, what we'll see is a request to enter the Postgres password. And at that point, you just enter the password that you specified for the Postgres user, and you're connected. Okay, so now it's asking for the password. So I'll click inside Cloud Shell. I'll enter the password that I specified, and now we're at the PSQL prompt. Okay, so the first thing that we need to do is create a database named blog. So I'll highlight this command, right-click, select copy, over here to Cloud Shell at the PSQL prompt, and press Control-V to paste that in. So now with that database created, let's connect to it. So this is how we do that with a / connect blog. So I'm going to press Control-C this time. After highlighting that command, over to Cloud Shell, Control-V to paste that in. Now we have to enter the Postgres password again. Okay, now we're connected to that database, and you can see the prompt has changed to blog because that's the database that we're connected to at this point. Okay, so now we can create a table named blogs. It has 3 columns: blogger name, content, and entry ID, and that's the primary key. Then we're going to insert some data into our new table, 2 rows of data as a matter of fact. So let's first create that table. Let's highlight this command, press Control-C, over here to Cloud Shell, Control-V, and press Enter. Okay, now if you want to see the tables that you have and the database, just press / and L and press Enter. Okay, so here's our blog database, and press Q to quit that. Okay, so now let's enter some data. So let's highlight these 2 commands. We'll right-click, select copy, click inside Cloud Shell, press Control-V. 1 row is inserted, the second row is inserted. So now we should just be able to select from blogs. So let's go ahead and do that. So select * from blogs, don't forget the semicolon, and press Enter. And there are our 2 rows. Now to quit from the PSQL prompt, just press / Q, press Enter, and now we're out to our Cloud Shell prompt. So I'm going to press C and press Enter, and actually I'm going to close Cloud Shell because we're done. However, it's always a good idea to clean up after yourself because you don't want to incur any additional charges. So here, still on the Instance Details page, scrolling up, and I'll click on the ellipsis here to open the options that I have, and I'll select Delete. Now I have to type the name of the instance, so it's my PSQL instance, and click Delete, and done. So we've successfully created that instance, created a database and a table within it. We inserted a couple rows of data, displayed them, and now we've cleaned up after ourselves. So we're done. In this exercise, you'll practice what you learned about Google Cloud Platform storage, compute, and analytics. You will list Google Compute Engine features, list the types of data supported in cloud storage, and work with Cloud SQL. You'll create a MySQL instance, connect to the instance, and create a database, create a table in that database, insert some data into that table, and display the data inserted, and finally remove the instance from Cloud Platform. Now pause the video and perform the exercise, and when you return, we'll go over these exercise tasks. Okay, task 1, list compute engine features. So first, compute engine feature is that you can use predefined and custom machine types. You can use those compute engines to do batch processing. The compute engine aligns with compliance and security certifications like ISO certifications. They use local solid-state drives for persistent storage. Maintenance is transparent. They're highly scalable and come with global load balancing. And the high-performance virtual machines boot quickly and use persistent disk storage. And they offer worldwide data centers over Google's fiber network. Okay, second task, list the types of data supported in cloud storage. So you have structured, unstructured, transactional, and relational data. All four are supported in cloud storage. Now we need to go and work with Cloud SQL. So I'm going to go over to my workstation and we'll do that. Okay, here I am on my work machine. I've logged into my Google Cloud Platform account and I've opened the Cloud SQL Instances page. So first step is to click Create Instance. We're going to leave MySQL option selected and click Next. We'll choose the second generation MySQL instance. Now we have to enter an instance ID. Now, if you have been practicing with these, you may have a problem if you try to use one of the previously used names. Sometimes it doesn't like it if you use it shortly after you've created an instance and deleted it. So what I'm going to do is I'm going to name this MySQL instance. We'll try that. And we'll set a root password. The rest of the options we'll leave at their default values. And now if we click Create, we'll see it says here the instance ID isn't available because it was used recently, right? So we'll just append the number 1 to the end of that instance name. And let's click Create now. And now the instance is being created. Okay, so the instance has initialized and started. Let's click to enter the instance details page. And we'll scroll down and click Connect using Cloud Shell. And we'll see the connect string populated inside the shell. So let's click inside the shell, press Enter to connect. Now this takes a few seconds, maybe a minute or two at the most, to whitelist the IP for this incoming connection. Then we'll enter the root password, and then we'll be at the MySQL prompt where we can create the database called blog. Okay, now enter the password you specified. Press Enter, and we're connected. So now let's create the database called blog. So we'll highlight this command, Control-C to copy over to Cloud Shell, Control-V to paste that in, create that database. Now we'll specify to use that database, and then we'll create a table called blogs with 3 columns in it. So I'm going to highlight those 2 commands, Control-C, over to Cloud Shell, Control-V, press Enter to run the create table command. Done. Okay, so now let's insert a couple of rows. So I'll highlight these 2 commands, press Control-C, over to Cloud Shell, Control-V, Press enter to run the second insert. And now we can just select from blogs. So select star from blogs, highlight the command, press Control C over to Cloud Shell, and at the SQL prompt, Control V, and there's our data. Now we'll exit by typing exit and pressing enter. And actually we'll close Cloud Shell. And now we'll click the ellipsis and select delete. Enter the name of the instance, MySQL instance 1, and click delete. Okay, and that's it. So we've created the instance, created a database in it, created a table, inserted some data, displayed that data, and cleaned up after ourselves by deleting the instance.
In this video, I'm going to use Hadoop in the Google Cloud Platform. I'm going to use the Google Cloud Platform to manage an Apache Hadoop cluster. I'm already logged into the Google Cloud Platform, so I'm going to create a new cluster. I'll go to Dataproc and Clusters. I'll click on Create Cluster. I'll leave the name the same. I can pick my region. I'll just say Global. I'll leave my zone the same. I'll select Standard, one master, and workers. I'll select one virtual CPU. For my worker nodes, I'll select one virtual CPU. I'll leave everything else the same, and I'll click Create. So my cluster is being created. I'm going to look at the cluster. I can see an overview. It has information on the CPU utilization, the disk bytes, disk operations, network bytes, and network packets. I'll look at my jobs. I'll look at my instances and my configuration. I'll go back to VM instances and I'll click on SSH. I'm connecting to the virtual machine. I want to upload a file, so I'll click on Upload. I have a file called Shakespeare.txt. If you open this file, you'll see that it has all the works of William Shakespeare. We're going to use this file for our word count test. So I'm going to upload this file. So the file is uploading. I'll click on Close, and I'll take a look at my directory. So you can see my file has been uploaded. I'm going to make a new directory in the DFS. So I'm going to type Hadoop, DFS, mkdir, tmp/in. I'm going to copy the Shakespeare file to this new folder. So I'm going to type Hadoop, DFS, put Shakespeare.txt, tmp/in. So the file has been copied. To make sure it's there, I'll type Hadoop, DFS, ls, tmp/in, and you can see that the file is there. I'm going to paste in the code for doing the word count. It's going to take the Shakespeare file that's in the in folder, and it'll put the results in temp output. So my job's going to run. It's going to do the mapping first and then the reduce. So my job finished running. We'll take a look at the output. So I'll type hdfs dfs cat tmp/output. I'll try that again. I need to put a star. And you can see the word counts. In this video, I'm going to work with the Google Cloud Service for running an Apache Spark cluster. And I will run some sample code in Apache Spark. I'm already logged into the Google Cloud Platform, so I'm going to create a new cluster. I'll go to Dataproc and Clusters. I'll click on Create Cluster. I'll leave the name the same. I can pick my region. I'll just say Global. I'll leave my zone the same. I'll select Standard, one master, and workers. I'll select one virtual CPU. For my worker nodes, I'll select one virtual CPU. I'll leave everything else the same, and I'll click Create. So my cluster is being created. I'm going to look at the cluster. I can see an overview. It has information on the CPU utilization, the disk bytes, disk operations, network bytes, and network packets. I'll look at my jobs. I'll look at my instances and my configuration. I'll go back to VM instances and I'll click on SSH. So I'm connecting to my cluster using SSH. I'm going to start a Spark shell. So I'll type Spark shell. I'm going to run a hello world example. So I'll paste in some code. So this ran a hello world Python script and it did a count on it. And the result was 7. I'm going to close SSH. So the last thing I want to do is delete my cluster. So I'll click on delete. I'll click on OK. And my cluster is deleting. I want to delete this cluster as soon as I'm done with it, since I'm being charged as long as it's running. I'll click on refresh, make sure it's gone. I'll check my jobs, see if I have any jobs running. And I'll click on clusters. I'll go back to the dashboard just to make sure everything else is running correctly. And from the dashboard, you can see that there are no resources in the project. In this video, I'm going to use SparkML for machine learning. I'm already logged into the Google Cloud Platform, so I'm going to create a new cluster. I'll go to Dataproc and Clusters. I'll click on Create Cluster. I'll leave the name the same. I can pick my region. I'll just say Global. I'll leave my zone the same. I'll select Standard, 1 master, and workers. I'll select 1 virtual CPU. For my worker nodes, I'll select 1 virtual CPU. I'll leave everything else the same, and I'll click Create. So my cluster is being created. I'm going to look at the cluster. I can see an overview. It has information on the CPU utilization, the disk bytes, disk operations, network bytes, and network packets. I'll look at my jobs. I'll look at my instances and my configuration. I'll go back to VM instances. I need to create a new sample dataset, so I'm going to go to BigQuery. I'll open this in a new tab. I'm going to create a new dataset, so I'm going to click on Create New Dataset. I'm going to call this new dataset natality_regression. Data location will be US. It's never going to expire. I'm going to look at BigQuery public data samples. There's a dataset here called natality. I'm going to copy this dataset. I'm going to select natality regression, and for the destination table, I'm going to type regression_input, and I'll click OK. I'll go look at my dataset, and I have my table called regression input. We can see the schema, we can see the details. It's a rather good sized table that contains almost 22 gigabytes of data and 137 million rows. I'll click on preview. It'll show you the first 15 rows. I'll go back to the VM. I'm going to run SSH, and I will run PySpark. I'm going to type in PySpark to start the application. I'm going to run a Python script that's going to run a linear regression using the Apache Spark ML. So I'm going to paste in the script. So my job's still running. It'll probably take a little while. So right now, all the data in the regression input table is being copied into JSON objects. This data will be used to determine our coefficients, our intercept, and our R-squared values for our data model. Our job is finished running, and now you can see the data model summary. In this video, I'm going to describe best practices in big data analysis. Some of the best naming practices include using unique bucket names. The bucket namespace is globally and publicly visible. Every bucket name must be unique across the entire cloud storage namespace. If you need lots of buckets, you could use GUIDs or an equivalent name for bucket names. One more option would be to use domain name buckets and manage the bucket names as subdomains. For security reasons, you should not use user IDs, email addresses, project names, or any personally identifiable information. You should also not put personally identifiable information in your object names because object names appear in website addresses. Bucket names should conform to a standard DNS naming convention because a bucket name can appear in a DNS record as a part of CNAME Direct. In cloud storage, forward slashes have no special meaning because there is no native directory support. Because of this, you can create deeply nested directory-like structures using slash delimiters. Some of the best practices for traffic considerations includes traffic estimation. This is an estimation of the amount of traffic that would be sent to the cloud storage. You should think about the operations per second, the bandwidth, and the cache control. You also need to understand the performance level that customers will expect from your application. This will help you decide the storage option and the region when creating new buckets. When you design your application, you should try to minimize spikes in traffic. If clients of your application are doing updates, spread them out throughout the day. To ensure that cloud storage auto-scaling always provides the best performance, you should ramp up your request rate gradually. If you get an error when making a request, use exponential backoff to avoid problems due to large traffic bursts. So if you make a request from the system and it fails, you should increase the waiting time between retries up to a maximum backoff time. Some storage best practices include high rate and high availability. Data that will be served at a high rate with high availability should use the multi-regional storage or regional storage. You should keep your compliance requirements in mind when choosing a location for your user data. Are there any legal requirements around the locations that your users will be providing data? For example, for US data, you might choose a US bucket. Some security best practices include to protect and securely store credentials. Credentials should never be shared, and each user should have a distinct credential. For your transport layer security, you should always use HTTPS to transport your data when you can. This will ensure your credentials, as well as your data, are protected as you transport data over the network. Whenever somebody leaves your project or no longer works for you, you should revoke their access and credentials. When creating buckets, you should choose bucket names and object names that are difficult to guess. And you should avoid use of sensitive information as part of the bucket or object name. When assigning access control, you should use groups. This solution will scale better, and it also provides a very efficient way to update the access control for a large number of objects. The Cloud Storage Access Control System allows the ability to specify that objects are publicly readable. You will need to make sure that you really want this object to be made public. With assigned URL, you can control the type and duration of access. Here are some best practices for uploading data. If you use the XML HTTP request callbacks, do not close and reopen the connection if you detect that progress has stalled. Doing so will slow down the system. For upload traffic, it's recommended to set reasonably long timeouts. For example, you can set a client-side timer that updates the client status window with a message when your application hasn't received an XHR callback for a long time. You should use compute engine instances in the same location as your cloud storage buckets. This will help keep traffic localized to a geographic region. For resumable uploads, the resumable session should stay in the region in which it was created. This will improve the upload performance. You should avoid splitting uploads into smaller chunks. If possible, avoid uploading content that has both content encoding gzip and a content type that is compressed, as this may lead to unexpected behavior. In this video, I'm going to provide an overview of the Google Cloud Platform Cloud Datalab, and I will discuss creating and managing virtual machines. The Cloud Datalab is a powerful interactive tool created to explore, analyze, transform, and visualize data. You can manage your data using BigQuery, cloud storage, and Python. With the Cloud Datalab, you can go from data to deployed machine learning models ready for prediction. You can explore data, build, and optimize machine learning models using TensorFlow or the Cloud Machine Learning Engine. With the Cloud Datalab, you can query terabytes of data in BigQuery or run local analysis on sample data. And you can run training jobs on terabytes of data in the Cloud Machine Learning Engine. To manage your VM instances, you need to install the Cloud SDK, including the Datalab component. gCloud needs to be authenticated and configured to use your selected project and zone. So from within gCloud, to create an instance, you would type Datalab, create, and your instance name. You can add several flags. You can add the machine type flag if you want to create a machine that has non-standard options. You can add the no connect flag if you just want to create the instance and not connect to it. To connect to your instance, type Datalab, connect, and your instance name. And to stop your instance, you would type Datalab, stop, and your instance name again. Each notebook uses a Python kernel to run code in its own process. If you have n notebooks open, there are at least n processes corresponding to each notebook. Each kernel is single-threaded. If you're not running multiple notebooks at the same time, multiple cores may not provide significant benefit. You may be able to benefit significantly by selecting a machine with additional memory, depending on your usage pattern and the amount of data processed. Execution is cumulative. If you are running 3 cloud data notebook cells, this will result in the accumulation of corresponding state, including memory allocated for data structures used in those cells. Processing large amounts of data in memory will cause proportional memory allocation. Cloud Datalab utilizes disk-based swap files. Relying on a swap file will most likely slow down your processing. A better plan would be to estimate your memory needs and then pick a machine type with the estimated memory amount. Cloud Datalab instances are single-user environments, so therefore each team member will need their own instance. There are 2 ways to create VM instances for team members. A project owner can create an instance for each team member, or each team member can create their own instance. A best practice would be to include the user's name in the name of the instance, so that it can be easily associated with each user. To create an instance, you would use the Datalab create command. The project owner can use an additional for-user flag to specify the email address of the Cloud Datalab user. In order to connect to their instance, the Datalab user must have one of the following roles. This would include roles/compute.instanceadmin.v1 or roles/IAM.serviceAccountActor. If each team member is a project editor, they can create their own Cloud Datalab instances. In this video, I'm going to provide an introduction to BigQuery and define some of its concepts and its benefits. BigQuery is a fast, highly scalable, cost-effective, and fully managed enterprise data warehouse. BigQuery is fast and easy to use on data of any size, and you can scale seamlessly to store and analyze petabytes of data. BigQuery provides cost control mechanisms that enable you to cap your daily costs. Serverless data warehousing gives you resources you need when you need them. This means you can focus on your data and analysis. BigQuery supports the standard dialect of SQL, which is ANSI 2011 compliant. BigQuery provides free ODBC and JDBC drivers, so your applications can interact with BigQuery's powerful engine. BigQuery's high-speed streaming insertion API provides a powerful foundation for real-time analytics. Jobs are actions that BigQuery executes on your behalf to load data, export data, query data, and copy data. You can access BigQuery via the web UI or the command line interface. Jobs can take a long time to execute, so they are run asynchronously and can be pulled for their status. Shorter actions, such as listing resources or getting metadata, are not managed by a job resource. Jobs are associated with the project that you specify, and the billing account attached to the associated project is billed for any usage incurred by the job. To run a job, you must have the BigQuery.jobs.create permissions. The following BigQuery roles include the BigQuery.jobs.create permissions. This would include BigQuery.user, BigQuery.jobUser, and BigQuery.admin. When you load, export, query, or copy data, a job resource is automatically created, scheduled, and run. When a job is submitted, it can be in one of 3 states. It can be pending, running, or done. From your own code, you can call the jobs.insert method to create a new job. When you call this method, you would pass in your own unique job ID that is generated by your code. You can call the jobs.get method with the job ID that you created earlier to check the status.state value to learn the status of your job. If the job has a status.errorResult property, the job is failed. The status.errorResult property holds information describing what went wrong in the failed job. If the job is successful, then it does not have a status.errorResult property. Even if your job finished successfully, there might still be some non-fatal errors. You can find a list of non-fatal errors in the status.errors list. You can view job information by using either the web UI, the command line interface, or the API. To get the information of a specific job, you would call BigQuery.jobs.get. You must have the BigQuery.jobs.list permission. The following BigQuery roles include BigQuery.jobs.list permissions. This would include BigQuery.user and BigQuery.admin. BigQuery.jobUser is granted the BigQuery.jobs.list permission for self-created jobs. Using the web UI, you can view the job history and recent jobs along with the details of that job. Job history is stored for 6 months. Jobs can be viewed from the web console, the command line interface, or using an API. To view jobs, you would need to have the BigQuery.jobs.list permissions. This permission is part of BigQuery.user, BigQuery.admin, and for jobs that you create yourself for BigQuery.jobUser. And from the web UI, you can see the job history as well as any recent jobs. In this video, I'm going to use the Google Cloud Platform and REST-based web services to build and maintain datasets. I am currently logged in to the Google Cloud Platform, and I have a project called Skillsoft. I'm going to look at Google BigQuery. I'm going to create a new dataset. I'm going to click on Create New Dataset. I'm going to call this Skillsoft Dataset. The data location will be US. It will never expire, and I'll click OK. I'm going to look at the public data. I'm going to go down to Samples. There's a table called Natality. I'm going to copy the table. The destination project will be Skillsoft, and the destination dataset will be Skillsoft Dataset. The destination table will be Natality_copy. I'm going to create a new dataset. I'm going to call it Temp. Location is US. It'll never expire. Under the temp dataset, I'm going to create a new table. I'm going to say create an empty table. I'm going to call this temp table. There's no table type. I'm going to add some fields to my table. So I'm going to type ID. This will be a string, and it's going to be required. I'll leave all the options the same, and I'll click Create Table. So I've created a table called Temp Table. It has an ID value. You can see the details of it, and there's a preview. I'm going to open the OAuth 2.0 Playground. This website can be used to make Google API calls. I'm going to select BigQuery API v2. I will select the first option, and then click Authorize APIs. I'm going to log in using my authorization. I'm going to select Allow so I can manage my data in BigQuery. I'm going to exchange authorization codes. So now I can call REST-based web services to maintain and manage my datasets in BigQuery. I'm going to paste in the URL that I can use to get my list of datasets. I have to specify the project name. I'm going to do a GET, and I'll send my request. So in my response, I get a JSON object that shows that I have two datasets. I have one called Skillsoft Dataset and one called Temp. To get the details of the temp dataset, so I'm going to add temp, and I'll send my request once again. This time I have more details about the temp dataset. You can see information on the creation time, who has access to this dataset. There's also a self link. For my method, I'm going to select delete, and I'll send my request. You'll notice that I can't delete this dataset because it's currently in use. We'll go back and look at Google BigQuery, and you will notice that the temp dataset has a table called temp table. I'm going to delete this table. I'm going to go back to my playground. I'll try doing my delete again, and you can see my request and my response. In this video, I'm going to demonstrate the TensorFlow framework and machine learning. I am going to use TensorFlow code in Python on the Google Cloud Machine Learning Engine to train a neural network model by using the MNIST dataset. This is a dataset of handwritten digits and has a training set of 60,000 examples. I will use TensorBoard to visualize the training process and the Google Cloud Datalab to test predictions. So to start, I'm going to open the Cloud Shell, which I already have open. I'm going to reconnect. I'm going to check for a list of models, and I have 0 items, which is what I expected to have. I'm going to download the example files. I'm going to go to my example directory. I'll take a look at the directory, and you can see several files in this directory. I'm going to create a new cloud storage bucket for my files. I'll set my project ID, I'll set my bucket name, and I'll create my storage bucket. I'll take a look at my buckets. I'll refresh this page. So you can see I currently have a bucket, and there's nothing in it. I'll go back to my Cloud Shell. I'm going to download the MNIST data files. I'll run this Python script to do so. So the files are downloading. I'll copy the files to train my model to my bucket, and I'll copy the file to test my model. I'm going to create a new job to train the model on the Cloud Machine Learning Engine. I'll create my job name, and I'll create a new job. So I've submitted my job and it's queued. I'll go take a look at my jobs. I'll refresh this page. So my job is now running, and it's training. It's going to take a little bit of time to run this. I'll go back to my Cloud Shell. I'll copy this command to view my job. So I'll highlight this row, I'll copy, and I'll paste this code. So you can see it's currently queued. And like I said earlier, it'll take a little bit of time for this to run. I'll check the job again, and my job is finished running. I'm going to start TensorBoard so I can visualize the data. I'm going to preview TensorBoard. So I'll click on Preview on port 8080. Looking at our scalars, you can see the optimized loss decreased as more data was used to train the model. The accuracy also increased as more data was used to train our model. I'll go back to the Cloud Shell. I'm going to deploy the model. I'll set the model name. I'm going to create a new data model. I'll set my version as v1. I'll set my origin. I'll create my versions. I'm going to set the default model. I'm going to create a new Datalab. So I've got my model already created, and now we're going to test the model. So I get an error. I'll take a look at the list of authorized users. So I am authorized. It says the Cloud Source Repository API is not enabled. Please enable. I'll click on this link and go enable it. I'll click on enable. I'll go back to my Cloud Shell. I'll try typing my command in again to create my Datalab. So this time my repository is being created. I'll type yes. I won't put a passphrase. So Datalab is now running, and I'll try to open it. I'm going to create a new notebook. I'm going to paste in some code that we can use to test our data model. I'll click on Run. I'm going to refresh the page. I'm going to click Run again. I'm going to draw a number and see if our model can predict what it is. I'll try drawing a 4. I'll select down here, and I'll run this code. This will try to predict what this number is. So you can see a list of probabilities. These are the probabilities that this number was selected. The closer these probabilities are to 1 determines if the number was predicted or not. I'll select the last set of code here, and I'll run it. This should draw us a chart. And based on this chart, the data model predicted that I drew 4. I'll try this again. I'll try something else, maybe a 2. I'll run this code again, and I'll draw my bar chart. And once again, the model predicted that I drew the number 2. In this exercise, you will use Hadoop for machine learning and identify datasets with machine learning in GCP. Pause the video and try this exercise yourself. Let's take a look at how I would perform this exercise. I'm already logged into the Google Cloud Platform, so I'm going to create a new cluster. I'll go to Dataproc and Clusters. I'll click on Create Cluster. I'll leave the name the same. I can pick my region. I'll just say Global. I'll leave my zone the same. I'll select Standard, 1 master, and workers. I'll select 1 virtual CPU. For my worker nodes, I'll select 1 virtual CPU. I'll leave everything else the same, and I'll click Create. So my cluster is being created. I'm going to look at the cluster. I can see an overview. It has information on the CPU utilization, the disk bytes, disk operations, network bytes, and network packet. I'll look at my jobs. I'll look at my instances and my configuration. I'll go back to VM instances, and I'll click on SSH. I'm connecting to the virtual machine. I want to upload a file, so I'll click on Upload. I have a file called Shakespeare.txt. If you open this file, you'll see that it has all the works of William Shakespeare. We're going to use this file for our word count test. So I'm going to upload this file. So the file is uploading. I'll click on Close, and I'll take a look at my directory. So you can see my file has been uploaded. I'm going to make a new directory in the DFS. So I'm going to type Hadoop, DFS, mkdir, tmp/in. I'm going to copy the Shakespeare file to this new folder. So I'm going to type Hadoop, DFS, put Shakespeare .txt tmp/in. So the file has been copied. To make sure it's there, I'll type Hadoop dfs ls tmp/in, and you can see that the file is there. I'm going to paste in the code for doing the word count. It's going to take the Shakespeare file that's in the in folder, and it'll put the results in temp output. So my job's going to run. It's going to do the mapping first and then the reduce. So my job finished running. We'll take a look at the output. So I'll type hdfs dfs cat tmp/output. I'll try that again. I need to put a star. And you can see the word counts. So next, I'm going to identify datasets with machine learning in GCP. I'm going to create a new dataset. I'm going to click on Create New Dataset. I'm going to call this Skillsoft Dataset. The data location will be US. It will never expire, and I'll click OK. I'm going to look at the public data. I'm going to go down to Samples. There's a table called Natality. I'm going to copy the table. The destination project will be Skillsoft, and the destination dataset will be Skillsoft Dataset. The destination table will be Natality_copy. I'm going to create a new dataset. I'm going to call it Temp. Location is US. It'll never expire. Under the temp dataset, I'm going to create a new table. I'm going to say create an empty table. I'm going to call this temp table. There's no table type. I'm going to add some fields to my table. So I'm going to type ID. This will be a string, and it's going to be required. I'll leave all the options the same, and I'll click Create Table. So I've created a table called temp table. It has an ID value. You can see the details of it, and there's a preview. I'm going to open the OAuth 2.0 playground. This website can be used to make Google API calls. I'm going to select BigQuery API v2. I will select the first option, and then click Authorize APIs. I'm going to log in using my authorization. I'm going to select Allow so I can manage my data in BigQuery. I'm going to exchange authorization codes. So now I can call REST-based web services to maintain and manage my datasets in BigQuery. I'm going to paste in the URL that I can use to get my list of datasets. I have to specify the project name. I'm going to do a GET, and I'll send my request. So in my response, I get a JSON object that shows that I have two datasets. I have one called Skillsoft Dataset and one called Temp. To get the details of the Temp dataset, so I'm going to add Temp, and I'll send my request once again. This time I have more details about the Temp dataset. You can see information on the creation time, who has access to this dataset. There's also a self link. For my method, I'm going to select Delete, and I'll send my request. You'll notice that I can't delete this dataset because it's currently in use. We'll go back and look at Google BigQuery, and you will notice that the temp dataset has a table called temp table. I'm going to delete this table. I'm going to go back to my playground. I'll try doing my delete again, and you can see my request and my response. In this video, I'm going to identify the process in creating a network. Manually created subnets can use any valid RFC 1918 IP range. Ranges do not have to be contiguous between subnets. For example, some subnets can use ranges from 10.0.0.0 through 10.0.0.8, while others use ranges from 192.168.0.0 through 16. Ranges must be unique and non-overlapping within the network. The minimum subnet size that can be used is 29. Each subnet has the following reserved addresses. Network addresses. This is the first address in the CIDR range. A default gateway address, which is the second address in the CIDR range. Reserved addresses, which is the second to last address in the CIDR range. And broadcast addresses, which are the last addresses in the CIDR range. Each project starts with a default network. That is an auto mode VPC network. There is a quota of 5 networks per project, including the default network. You can keep the default network and create 4 more. When you create a VPC network, the following static routes are automatically associated with it. A default internet gateway route, which provides outgoing connectivity from instances in all of its subnets. This route lets instances send traffic to destinations outside of the VPC network, a virtual network route for each subnet. These allow for communication among instances or resources in different subnets of the network, subject to applicable firewall rules. Auto mode networks create a virtual network route for each of their automatically created subnets. Route names are automatically generated and will be different for each network. You can list the routes for a network by using gcloud. The command that you would type is gcloud compute routes list. Hybrid network solutions extend an on-premise network to a VPC network. For example, you might use Cloud VPN or a dedicated interconnect to create hybrid networks so that your on-premise host can reach instances in a VPC network. Each network has a set of firewall rules controlling access to and from instances in its subnets. All ingress traffic to instances, even from other instances, is blocked unless firewall rules are created to allow it. The default network has automatically created firewall rules. Manually created networks only have a default allow rule for outgoing traffic and a default deny rule for incoming traffic. Every VPC network has two implied firewall rules. There is the implied allow egress rule. The destination is 0.0.0.0, and the priority is the lowest possible, and lets any instance send traffic to any destination. Outbound access may be restricted by a higher priority firewall rule. Internet access is allowed if no other rules deny outbound traffic, and if the instance has an external IP address or uses a NAT instance. There is also the implied deny ingress rule. This is a rule whose action is deny. The source is 0.0.0.0, and the priority is the lowest possible, and protects all instances by blocking incoming traffic to them. Incoming access may be allowed by a higher priority rule. The implied rules cannot be removed, but they have the lowest possible priorities. Rules that you create can override them as long as your rules have a higher priority. The default network is pre-populated. With firewall rules, these rules can be deleted or modified as necessary. There is the default allow internal rule. This rule allows ingress connections for all protocols and ports among instances in the network. There is the default allow SSH rule. This rule allows ingress connections on TCP port 22 from any source to any instance in the network. There is also the default allow ICMP rule. This allows ingress ICMP traffic from any source to any instance in the network. This rule enables tools like ping. There is the default allow RDP rule. This allows ingress connections on port 3389 from any source to any instance in the network. This rule enables connections to instances running the Microsoft Remote Desktop Protocol, or RDP. A VPC network can have a maximum of 7,000 virtual machine instances. This number is not a quota and cannot be increased. In this video, I'm going to discuss using TensorFlow for machine learning and identify the process of using TensorFlow with GPU. TensorFlow is an open source software library for numerical computation using Dataflow graphs. TensorFlow was originally developed by researchers and engineers working on the Google Brain team for the purposes of conducting machine learning and deep neural network research. Nodes in the graph represent mathematical operations. The graph edges represent the multidimensional data arrays, or tensors, communicated between them. The flexible architecture allows you to deploy computation to one or more CPUs or GPUs in a desktop, server, or mobile device with a single API. GPU instances can be set up with the Google Cloud Web Interface. To start, you would create a new project in the Google Cloud Platform, navigate to the Compute Engine, and then create a new Compute Engine instance. When creating the instance, you can configure the number of cores, the memory, and you can select the option for GPU. When you select the GPU option, additional options appear. You can select the number of GPUs that you want to use in your project. For the operating system, select Ubuntu 16.04 and then click Create. In order to use the GPUs, you will need to install the correct drivers. All the Google Cloud GPUs are NVIDIA cards and need to have CUDA installed. As well, NVIDIA provides the cuDNN library to optimize neural network calculations on their cards. In order to get this library, you need to register for the NVIDIA Developer Program and then download the latest version of the cuDNN library. At this point, the GPU instance is running and the drivers have been installed. TensorFlow needs to be installed to utilize the GPUs. To install TensorFlow requires running 2 lines of code. The first line of code will install Python, and the second line of code will install TensorFlow GPU. Installing TensorFlow GPU ensures that it defaults to the GPU engine. You can still move operations to the CPU if required. The steps involved in using TensorFlow with GPU are as follows. First, you would create and configure a compute engine. Then you need to create a cloud storage bucket to store the training and testing data. You need to create and run TensorFlow code to train your model. You need to publish your model so that it can be used for predictions. Next, you will test your model with your test data to determine the accuracy of the model. And the final step is to clean up and delete your resources so that you will not be charged. In this video, I'm going to describe the various machine learning APIs and their usage. The Google Cloud Video Intelligence API makes videos searchable and discoverable. The easy-to-use REST API enables you to extract metadata from the video. It automatically analyzes video content to identify what entities are in your video from a massive library of 20,000 labels. Google Cloud Video Intelligence quickly annotates videos stored in Google Cloud Storage. It helps you identify key entities within your video. It also returns confidence levels for each entity identified. It can also separate signal from noise by retrieving relevant information within the entire video, and can be done shot by shot or per frame. You can identify the presence of a signal buried in noise by using shot detection to distinguish scene changes within a video. The Google Cloud Vision API enables you to understand the content of an image in an easy-to-use REST API. The Vision API improves over time as new concepts are introduced and accuracy is improved. It quickly classifies images into thousands of categories. It can easily detect broad sets of objects in your images, from flowers, animals, as well as thousands of other object categories commonly found within images. It can detect individual objects and faces within images. Vision API enables you to detect different types of inappropriate content, from adult to violent content, and it can also find and read printed words contained within images. Optical character recognition enables you to detect text within your images, along with automatic language identification. Vision API supports a broad set of languages. The Google Cloud Speech API enables you to convert audio to text by applying neural network models in an easy-to-use API. Speech API accuracy improves over time as Google improves the internal speech recognition technology. The API recognizes over 80 languages and variants to support your global user base. You can also filter inappropriate content in text results. The service can successfully handle noisy audio from a variety of environments. You can also enable command and control through voice. The Google Natural Language API reveals the structure and meaning of text. It offers powerful machine learning models in an easy-to-use REST API. You can extract information about people, places, events, and much more. You can also use it to understand sentiment about your product on social media. You can extract actionable insights on product reception or user experience from customer conversations in email, chat, or social media by using entity detection and sentiment analysis. You can parse intent from customer conversations happening in a call center or a messaging app. Multilingual support allows you to analyze text in multiple languages, including English, Spanish, Japanese, Chinese, French, German, Italian, Korean, and Portuguese. The Google Cloud Translation API provides a simple programmatic interface for translating an arbitrary string into any supported language using neural machine translation. The Translation API is an easy-to-use Google REST API and can seamlessly scale with almost any volume. Language detection is also available if the source language is unknown. The underlying technology pushes the boundary of machine translation and is updated all the time to seamlessly improve translations. In this video, I'm going to describe Dataflow and how it can be used to create data processing streams. Cloud Dataflow is a fully managed service for transforming and enriching data in stream, or real-time, and batch historical modes. With the serverless approach to resource provisioning and management, you have access to virtually limitless capacity to solve your biggest data processing challenges. The Google Cloud Platform's serverless approach removes operational overhead with performance, scaling, availability, security, and compliance handled automatically so users can focus on programming instead of managing server clusters. Cloud Dataflow integrates with Stackdriver, which is the Google Cloud Platform's unified logging and monitoring solution, and lets you monitor and troubleshoot your pipeline as they are running. Rich visualization, logging, and advanced alerting helps you identify and respond to potential issues. Cloud Dataflow is a convenient integration point for bringing predictive analytics to fraud detection, real-time personalization, and similar use cases by adding TensorFlow-based cloud machine learning models and APIs to your data processing pipelines. Cloud Dataflow unlocks transformational use cases across numerous industries. Cloud Dataflow can be used to check clickstream, point of sale, and segmentation analysis in retail. It can be used to check fraud detection in financial services. It can check personalized user experience in gaming, and it can check Internet of Things analytics in manufacturing, healthcare, and logistics. Cloud Dataflow seamlessly integrates with Google Cloud Platform services. Its Beam-based SDK lets developers build custom extensions and even choose alternative execution engines. Looking at this diagram, there's 3 steps. There's the ingestion, processing, and analysis. During the ingest phase, data can be received from Cloud Pub Sub, from Cloud Data Store, from Apache Avro, or Apache Kafka. The data can be a real-time stream or a batch process. Processing is done using Cloud Dataflow. The output from Cloud Dataflow can be stored in Cloud Bigtable, Cloud Machine Learning, or Cloud BigQuery, and can be analyzed using Data Studio or other analytic tools. Stream Analytics on the Google Cloud Platform simplifies ETL pipelines without compromising robustness, accuracy, or functionality. Cloud Dataflow supports fast pipeline development via expressive Java and Python APIs in the Apache Beam SDK, which provides a rich set of windowing and session analysis primitives, as well as an ecosystem of source and sync connectors. Data processing pipelines, written with the Beam-based Cloud Dataflow 2.x SDK, are portable across Cloud Dataflow, Apache Spark, and Apache Flink. Spark support is available via Cloud Dataproc for streaming and batch workloads. In this video, I will discuss the Pub and Sub message-oriented middleware and when to use them both. Google Cloud Pub Sub brings the scalability, flexibility, and reliability of enterprise message-oriented middleware to the cloud. Google Cloud Pub Sub allows for secure and highly available communication by providing many-to-many asynchronous messaging that decouples senders and receivers. Google Cloud Pub Sub delivers low-latency, durable messaging that integrates systems hosted on the Google Cloud Platform and externally. Messages are the combination of data and optional attributes that a publisher sends to a topic and is eventually delivered to subscribers. A topic is a name resource to which messages are sent by publishers. Subscriptions are a name resource representing the stream of messages from a single specific topic to be delivered to the subscribing application. A publisher application creates and sends messages to a topic. Subscriber applications create a subscription to a topic to receive messages from it. Communication can be one-to-many, many-to-one, and many-to-many. Here are some classic scenarios for using the Google Cloud Pub Sub. It can be used for balancing workloads in network clusters. A large queue of tasks can be efficiently distributed among multiple workers, such as Google Compute Engine instances. It can be used for data streaming from various processes or devices. A residential sensor can stream data to backend servers hosted in the cloud. It can be used for distributing event notifications. For example, a service that accepts user signups can send notifications whenever a new user registers. Downstream services can subscribe. It can be used for refreshing distributed caches. For example, an application can publish invalidation events to update the IDs of objects that have changed. It can be used for implementing asynchronous workflows. For example, an order processing application can place an order on a topic from which it can be processed by one or more workers. It can be used for logging to multiple systems. A Google Compute Engine instance can write logs to the monitoring system. It can also be used for reliability improvement. A single zone compute engine service can operate in additional zones by subscribing to a common topic. This will allow for recovery from failures in a zone or region. This diagram displays the steps in the publisher Subscriber process. A publisher application creates a topic in the Google Cloud PubSub service and sends messages to the topic. A message contains a payload and optional attributes that describe the payload content. Messages are persisted in a message store until they are delivered and acknowledged by subscribers. The PubSub service forwards messages from a topic to all of its subscriptions. Each subscription receives messages either by PubSub pushing them to the subscriber's chosen endpoint, or by the subscriber pulling them from the service. When a message is acknowledged by the subscriber, it is removed from the message queue. Publishers can be any application that can make HTTPS requests to googleapis.com. It can be an app engine, a web service hosted on the Google Compute Engine. Pull subscribers can be any application that can make HTTPS requests to googleapis.com. Push subscribers must be webhook endpoints that can accept post requests over HTTPS. In this video, I will define the various Google Cloud Platform pipelines for Dataflow processing. In the Dataflow SDKs, a pipeline represents a data processing job. You build a pipeline by writing a program using a Dataflow SDK. A pipeline consists of a set of operations that can read a source of input data, transform that data, and write out the resulting output. The data and transforms in a pipeline are unique to and owned by that pipeline. Your program can create multiple pipelines. However, those pipelines cannot share data or transforms. You can create pipelines with varying degrees of complexity. A pipeline can be relatively simple and linear. You can think of a pipeline as a directed graph of steps, rather than a simple linear sequence of steps. Your pipeline construction can create this directed graph by using conditionals, loops, and other common programming structures. A pipeline consists of two parts, data and transforms applied to that data. The Dataflow SDKs provide classes to represent both data and transforms. In the Dataflow SDKs, pipelines use a specialized collection class called PC Collection to represent their input, intermediate, and output data. PC collections can be used to represent data sets of virtually any size. PC collections are specifically designed to support parallelized processing. A pipeline must create a PC collection for any data that it needs to work on. You can read data from an external source into a PC collection. Each transform in your pipeline accepts one or more PC collections as input and produces one or more PC collections as output. A transform is a step in your pipeline. Each transform takes one or more PC collections as input, changes or otherwise manipulates the elements of that PC collection, and produces one or more new PC collections as output. The Dataflow SDKs contain a number of core transforms. A core transform is a generic operation that represents a basic or common processing operation that you perform on your pipeline data. Most core transforms provide a processing pattern and require you to create and supply the actual processing logic that gets applied to the input PC collection. The Dataflow SDKs support combining multiple transforms into larger composite transforms. In a composite transform, multiple transforms are applied to a dataset to perform a more complex data processing operation. Composite transforms are a good way to build modular, reusable combinations of transforms that do useful things. The Dataflow SDKs often use root transforms at the start of a pipeline to create an initial PC collection. Root transforms often involve reading data from an external data source. In this video, I'm going to demonstrate the process of creating Dataflow pipelines using the Google Cloud Platform. I'll start by looking at the Apache Beam webpage. On this page, you have Get Started, Documentation, SDKs, Runners, Contribute, and a blog. There is a link to download the Beam SDK, and a Quick Start page for Java and for Python. I'll take a look at the Java Quick Start page. On the Java Quick Start page, there's information on setting up your development environment. There's information on the word count pipeline and how to download it using Maven. There's information on using the word count beam and information on creating a series of example pipelines. They discuss how to run word count and how to inspect your results. I'm going to download and run this example using the Google Cloud Platform. I'm going to go to the console page. I'm going to click on the menu icon, and I'll scroll down to Dataflow. and I'll click on Dataflow. I'm going to open the Google Cloud shell. I'm going to download the word count example and run it locally. I'm going to run a simple example pipeline using Java. Data pipelines can be either batch or streaming. The example in this video is a batch pipeline that counts words in a collection of Shakespeare's works. I'm going to paste in code to download the example, and I'll run this code so the example is being run using Maven. I'm going to change my directory, so I'll type cd Dataflow -intro. I'll look at my directory. I'm going to create a storage bucket. So I'll paste in the code to do this. I'll go take a look at my storage buckets. I'll click on refresh. And my bucket has been created. I'll go back to Dataflow. I'm going to launch my pipeline on the Dataflow service. So I'll paste in the code that does this. And I'll start the service. So this is downloading and compiling files. So right now test files are being created and being copied to my storage bucket. So my job has been created and is running. You can see that a job has been added to Dataflow. It's called Dataflow-intro. So my job is going to run for a while. I'll click on my job. So from within here, you can see the different steps in my job. There's a step to read lines. There's a word count step. There's a step to map elements. And there's a step to write counts. As I click on this, you can see information on the different steps. I'll take a look at my logs. And you can see different information on my logs. I'll go back to this job. And you can see that the job is still running. So the job is cleaning up and stopping worker pools. I'll take a look at my browser storage again. I'll click on example. And I have 3 output files. If I click on that file, I can see all my word counts. I'll try a different file. And I'll try the last one. In this video, I will describe the differences between real-time and batch data processing. Batch data processing is an efficient way of processing high volumes of data and is where a group of transactions is collected over a period of time. Data is collected, entered, processed, and then the batch results are produced. For example, Hadoop is focused on batch data processing. Batch processing requires separate programs for input, process, and output. An example is a payroll and billing system. Real-time data processing involves a continuous input, process, and output of data. Data needs to be processed as quickly as possible and in a small time period, or near real time. An example of these kind of systems include radar systems, customer services, and bank ATMs. Operational intelligence uses real-time data processing to gain insight into operations by running query analysis against live feeds and event data. Near real-time analytics over operational data provides visibility over many data sources. The main objective is to obtain near real-time insight using continuous analytics to allow the organization to take immediate action. Real-time analysis of operational data has much greater value. Complex event processing combines data from multiple sources to detect patterns and attempts to identify either opportunities or threats. The goal is to identify significant events and to respond quickly. Examples include sales leads, orders, or customer service calls. Real-time operational intelligence is used in customer service centers for customer experience optimization. The goal is to analyze the total customer experience and recommend scripts or rules that guide the agent on the phone to provide an optimal customer interaction with the customer. This leads to more sales, efficient problem solving, and happy customers. Real-time data processing is used by point-of-sale systems to update inventory, provide inventory history, and sales of a particular item. This allows an organization to run payments in real time. Batch processing has these benefits. Job processing can be performed when the computing resources are less busy. It allows the system to use different priorities for interactive and non-interactive work. It is more efficient since the batch process will run the program only once for many transactions, which will reduce system overhead. Operational business intelligence looks like a simple expansion of business intelligence into operational areas of an organization. In reality, it requires a whole new way of thinking in terms of data modeling, report design, and implementation, based on its real-time collaborative nature. Historical data analysis refers to analyzing data over a period of time. In this exercise, you will create a virtual private cloud network on the Google Cloud Platform. You will view various machine learning APIs, demonstrate how to create a Google Cloud Dataflow from a template, and demonstrate how to create topics, messages, and subscriptions using the Google Cloud Pub Sub. So now, pause this video and try this exercise on your own. Let's take a look at how I would perform this exercise. I am already logged in to the Google Cloud Platform. I'm going to add a new virtual private cloud network. I'll scroll to VPC network, and I'll click on it. You can see I currently have a default network set up, and it's set up for different regions. And it's currently set up with these subnets for these different regions. I can have up to 5 VPC networks. I start with a default network, and I can add 4 more. I'm going to create a new VPC network. So I'll click Create VPC Network. For this, I'm just going to enter Skillsoft Network. I can create custom or automatic subnets. So for now, I'm going to select automatic. I can specify any firewall rules that I want to implement. For now, I want to select any of these. And I can select regional or global. And now I'll click Create. So my VPC network is being created. So my new VPC network has been created. So next, I'm going to look at the various machine learning APIs. I'll go to my menu options. I'll go to APIs and Services. I'll click on Library. I'll type in Machine Learning. And you can see we have the Google Cloud Machine Learning Engine. We have the Prediction API. We have the Google Cloud Translation API. We have the Google Cloud Speech API, which can be used for speech recognition. There's the Cloud Video Intelligence API. We have Dialogflow API, Google Cloud Natural Language API, which can be used to analyze natural language. We also have the Google Cloud Vision API, which can analyze video images. I'll take a look at the Google Cloud Translation API. And from this page, I can enable it, or I can try this API. You can enable all these APIs and try them on your own. So next, I will take a look at Dataflow. I'll click on my menu. I'll click on Dataflow. I had created a Dataflow job earlier, and it ran. I can create new Dataflow jobs from templates. I'm going to click on Create Job from Template. I'll call this Test Job. I want to run this on US Central. I can select my template. There is a word count template, which counts all the words in all the works of William Shakespeare. For now, I'll click on word count. You see my input file. I can create a bucket for my output files. I can specify the max number of workers. I can specify the zone, which is optional. I can specify a service count email. I can specify the machine type, and I can run my job. So next I'm going to create topics, messages, and subscriptions using the Google Cloud Pub Sub. I'll go to my menu. I'll click on Pub Sub. So to start, I'm going to create a topic. I'll call this My Topic. I'll click on Create. I'll highlight my topic. I can publish messages to my topic. And I can create subscriptions so people can receive messages from my topic. Create subscription. I'll call this My Subscription. The delivery type will be pull. And the deadline time will be 10 seconds. I'll create this. I'll go back to topics and I'll click on my topic. So now I'm going to publish a message. For my message, I'll type "this is a message." For my key, I'll type name. And for a value, I'll type test. And I'll click on publish. So anyone that was subscribed to receive messages will receive the message that I just published. In this video, I will define the Cloud Dataproc and some of the benefits of using Cloud Dataproc. Google Cloud Dataproc is a managed Spark and Hadoop service that lets you take advantage of open source data tools for batch processing, querying, streaming, and machine learning. Some of the services included with Dataproc include Apache Spark, which is a lightning-fast, unified analytics engine for big data and machine learning. Hadoop, which is a framework that supports the processing and storage of extremely large datasets in a distributed computing environment. Apache Pig, which is a high-level platform for creating programs that run on Apache Hadoop. And Apache Hive, which is a data warehouse software project built on top of Apache Hadoop for providing data summarization, query, and analysis. Cloud Dataproc automation helps you create clusters quickly, manage them easily, and save money by turning clusters off when you don't need them. Some of the key capabilities of Cloud Dataproc include batch processing, streaming, querying, and machine learning. Google Cloud Dataproc has a number of unique advantages for clusters of 3 to hundreds of nodes. Cloud Dataproc is priced at only 1 cent per virtual CPU in your cluster per hour, on top of the other cloud platform resources that you use. Cloud Dataproc clusters can also include preemptible instances that have lower compute prices to help reduce your cost even further. Instead of rounding your usage to the nearest hour, Cloud Dataproc charges you for only what you use, with second-by-second billing and a low 1-minute minimum billing period. Cloud Dataproc is also super fast. Without using the Cloud Dataproc, it could take you from 5 to 30 minutes to create a Spark and Hadoop clusters on your premises or through other providers. By comparison, Cloud Dataproc clusters are quick to start, scale, and shut down. Each of these operations take 90 seconds or less. This allows you to spend less time waiting for clusters and more time doing hands-on work. Google Cloud Dataprocs are easy to manage. You can use Spark and Hadoop clusters without the assistance of an administrator or any special software. You can easily interact with clusters and Spark or Hadoop jobs through the Google Cloud Platform Console, the Google Cloud SDK, or the Cloud Dataproc REST API. Google Cloud Dataproc has built-in integration with other cloud platform services, such as BigQuery Cloud, Storage, Cloud Bigtable, Stackdriver, Logging, and Stackdriver Monitoring. And Google Cloud Dataproc is simple and familiar. You don't need to learn new tools or APIs to use Cloud Dataproc. Google Cloud Dataproc uses image versions to bundle operating systems, big data components, and the Google Cloud Platform connectors into one package that is deployed on a cluster. The following versions are supported in Cloud Dataproc clusters: Apache Spark 2.2.0, Apache Hadoop 2.8.2, Apache Pig 0.16.0, Apache Hive 2.1.1, BigQuery Connector 0.10.2-Hadoop 2, and GCS Connector 1.6.1 Hadoop 2. In this video, I will describe various ways to access Cloud Dataproc. This includes using the Dataproc API REST-based web service, the RPC service, and using the Google Cloud SDK and the Google Cloud Dataproc UI. The first method for managing the Google Cloud Dataproc is using a REST-based web API. This API can be used to manage Hadoop-based clusters and jobs on the Google Cloud Platform. The URI for the REST-based web service is at dataproc.googleapis.com. And for workflow templates, we can do a create. This is used to create a new workflow template. We can do a delete. We can use this to delete a workflow template. We can do a get, which is used to retrieve the latest workflow template. We can do an instantiate command. This is used to instantiate a template and begin execution. We can do a list command. This will list workflows that match the specified filter in the request. And we can do an update. Doing an update replaces a workflow template. Doing an update updates an existing workflow template. Another method for managing the Google Cloud Dataproc is to use the RPC or Remote Procedure Call API to remotely call procedures. The RPC service name is available at dataproc.googleapis.com. Using the RPC API, we can manage clusters and we can manage jobs. The Cluster Controller service provides methods to manage clusters of the compute engine. There is a create cluster method, which can be used to create a cluster in a project. There is a delete cluster method, which can be used to delete clusters in a project. There is the diagnose cluster method, which can be used to get diagnostic information on a cluster. There is the get cluster method, which can be used to get the resource representation for a cluster in a project. There is the list clusters method. This method can list all the clusters in a project. And there's also the update cluster method, which can be used to update a cluster in a project. All of these methods will require a project ID and a region. The job controller provides methods to manage jobs. There is the cancel job method, which is used to create a job cancellation request. There is the delete job method, which can be used to delete a job from a project. There is the get job method. This can be used to get the resource representation for a job in a project. There is also the list jobs method. This method can be used to list jobs in a project. There is also the submit job method. This method can be used to submit a job to a cluster. And there is also the update job method, which can be used to update a job in a project. All of these methods require a project ID and a region, and may also require a job ID. Google Cloud Dataproc can also be accessed by the Google Cloud SDK or by using the Google Cloud Dataproc UI. To use the Google Cloud SDK, you will need to download and install it. Once the Google Cloud SDK is installed and running, you will need to type gcloud space init. You will need to accept the option to log in using your Google user account, and then select the compute engine. Some of the core gcloud commands include gcloud offlist, which is used to list the accounts whose credentials are stored on the local system. gcloud config list, which is used to list the properties in your active SDK configuration. gcloud info, which is used to view information on your Cloud SDK installation and the active SDK configuration. And gcloud help, which provides information about gcloud commands and other topics from the command line. You can also use the Google Cloud Dataproc UI. From the UI, you can use command line commands. You can type commands in the command line prompt, or use the Google Cloud Platform console. In this video, I'm going to create a new project and describe the various areas of the dashboard. So to start, I need to create a new project. I'll click on Create Project. I'll call this Project Skillsoft. And I'll click Create. My project is now being created. So on the dashboard, I have project info that has information on my project. There's information on the APIs. There's information on the Google Cloud Platform status, and on billing, error reporting. There's information on resources, and there's trace information, which can be added using the Stackdriver Trace API. There's information on getting started. There's some news and there's documentation. I'll take a look at the billing information. So I'll click on View Detailed Charges. There's no charges yet because we just created this project. I'll click on Go to Billing. And you can see that I have some credits left. And I have these credits for 307 more days. I'll go back to the Google Cloud Platform. I'm going to look at my APIs. So I'll click on Go to APIs Overview. You can see all the APIs that I have enabled. If I want to disable them, I could click on Disable, which I'm not going to do right now because I may want to use these in my projects. I'll look at library. So in the library, you have different APIs that you can enable. I'll take a look at the machine learning APIs. I'll click on View All. So we could enable any of these APIs. For example, you have the Cloud Natural Language API, the Cloud Video Intelligence API, Dialogflow API, the Google Cloud Machine Learning Engine, the Google Cloud Speech API, Google Cloud Translation API, the Google Cloud Vision API, and the Prediction API. You can also find the APIs from the drop-down menu on the left-hand side. I'll click on the icon in the top left-hand corner, and I can see I have billing, and I have APIs. In this video, I'm going to demonstrate the process of creating a cluster in Cloud Dataproc. To start, I'm going to click on the menu in the upper left-hand corner. I'll go to Dataproc. I'll click on Clusters, and I want to enable this API. Cloud Dataproc can be used to run Apache Hadoop clusters. So next, I'm going to create a new cluster. I'll click on Create Cluster. I'll leave the default name. For my region, I'll select Global. For my zone, I'll select US East 1B. For my cluster node, I'll keep it as standard. I want to have 4 vCPUs. The memory allocated will be 15 gigabytes. I will leave the default settings for my worker nodes. And my worker nodes will have 500 gigabytes of disk size. I'm going to have 2 nodes. And this cluster is configured to have 8 yarn cores, and the yarn memory will be 24 gigabytes. I'll take a look at the other options available. I'm not going to add any other nodes. So I'm going to click on Create. And my cluster is being provisioned. So my cluster is finished provisioning. We'll take a look at the cluster. I'll take a look at the jobs. So I have no jobs running. I'll look at my instances. So I have 1 master, and I have 2 worker nodes. I can actually connect my node using SSH. I'll click on Open in Browser window. I'll check my folder. I want to get it back out of here. And now I'm going to go back to the dashboard. So this time you can see that I have 3 compute engines running, and now I have a cloud storage bucket. In this video, I will use the Google Cloud Platform to configure and delete Dataproc clusters. We'll take a look at the cluster. I'll take a look at the jobs. So I have no jobs running. I'll look at my instances. So I have 1 master, and I have 2 worker nodes. I will open the Google Cloud Shell, and I'll open this up in a new window. I'm going to type gcloud Dataproc clusters, and this will show me all my available commands. So I can do a create, a delete, a describe, a diagnose, list, and an update. I will type gcloud Dataproc clusters list, and this will show me all my available clusters. I'm going to change my command, and I will type describe, and I will type cluster hyphen ABC5, and this will show me information on my cluster. There's also different ways that I can delete my cluster. From the Cloud Shell, I'll change my command, and so for my command, I could have gcloud Dataproc clusters delete, and the name of the cluster. I will go back to the Cloud UI. I'll click on clusters. So if I want to do a delete from here, I can select my cluster and I can click on delete. Or if I'm inside my cluster again, I can click delete here. And I get a message, do you want to delete your cluster? I'm going to click on OK. And my cluster is being deleted. Once it's done, the status will update and I will receive a message. I'll go back to my Cloud Shell. I'll type list and I will hit enter. And you can see that the cluster is gone. In this video, I will define master and worker nodes in Dataproc. So I have one existing cluster and I have no jobs. I will go back and take a look at my clusters. So I'll click on my cluster. I can see an overview. If I click on equivalent rest, I can see my equivalent rest response. I'll close this window. I'll click on my jobs. So I currently have no jobs. I'll click on equivalent rest. So once again, I see the equivalent rest response. I'll close this window. I'll click on VM instances. You can see the virtual machines that were displayed in the resource window. I have a master and I have two worker nodes. I will click on equivalent rest again. And you can see my equivalent rest response. I'll click close. Next, I'll take a look at my configuration. I'll click on edit and take a look at some of the options that I have available. So things that I can change are my number of worker nodes. I'll change this to 1. And I am told that I must have at least 2 worker nodes. I'll put that back to 2. I could have preemptible worker nodes. I'll try adding 2 of those. You can see the cloud storage bucket that I'm using. I'll open my storage bucket in a new tab. And we'll take a look at it. And I'll look at my storage bucket. So right now I have one bucket. And it has a folder. I'm going to close my storage buckets. I can change my cluster name, my UUID, and my location. For now, I'm going to click Cancel. I can also manage my clusters from the Google Cloud Shell. I'm going to activate it, and I will have it open in a new window. I'm going to type gcloud, Dataproc, clusters, and this will show me all my available commands. So I can do a create, a delete, a describe, a diagnose, list, and an update. I will type gcloud, Dataproc, clusters, list, and this will show me all my available clusters. I'm going to change my command, and I will type describe, and I will type cluster hyphen ABC5, and this will show me information on my cluster. In this video, I'm going to describe custom machine types and preemptible worker nodes. A machine type specifies a particular collection of virtualized hardware resources available to a virtual machine. This includes memory size, virtual CPU count, and the maximum persistent disk capability. Machine types define the virtualized hardware resources available to an instance. The compute engine offers both predefined machine types and custom machine types. Predefined machine types have a fixed collection of resources. Cloud Dataproc clusters can use both standard and custom types for both master and/or worker nodes. Custom machine types are ideal for the following scenarios: workloads that are not a good fit for the predefined machine types that are available to you, for workloads that require more processing power or more memory, but don't need all of the upgrades that are provided by the next larger predefined machine type. Custom machine type pricing varies based on the resources used in a custom machine. Dataproc pricing is added to the cost of compute resources you use, and is based on the total number of virtual CPUs used in a cluster. Only machine types with one vCPU or an even number of vCPUs can be created. Memory must be between 0.9 gigabytes up to 6.5 gigabytes per vCPU. The total memory of the instance must be a multiple of 256 megabytes. The maximum number of vCPUs depends on the zone. Zones supporting Haswell and Broadwell processors can support machine types up to 64 vCPUs. Ivy Bridge processors can support machine types with up to 32 vCPUs. Zones with Sandy Bridge processors can support machine types with up to 16 vCPUs. Cloud Dataproc clusters can use preemptible VM instances, which are also known as preemptible VMs. Preemptible instances lower per cost compute costs. All preemptible instances added to a cluster use the machine type of the cluster's non-preemptible worker nodes. Preemptible instances are reclaimed if they are required for other tasks. Cloud Dataproc adds preemptible instances as secondary workers in a special managed group. The following rules will apply when you use preemptible workers with the Cloud Dataproc cluster. Since preemptibles can be reclaimed at any time, preemptible workers do not store data. There are no clusters that contain only preemptibles. To ensure clusters do not lose all of their workers, Cloud Dataproc cannot create preemptible-only clusters. Preemptible workers have a persistent disk size. This space is used for local caching of data and is not available through HDFS. In this video, I'm going to review Identity and Access Management and review the roles for Dataproc. I'm going to click on the menu in the upper left-hand corner. I'll select Identity and Access Management, and I will click on Roles. You can see that there's already roles defined. I'm going to create a new role. I'm going to call this Dataproc Custom. I'm going to click on Add Permissions. Dataproc has permissions for clusters, jobs, operations, and workflow templates. So to start, I'm going to take a look at Dataproc jobs. So these permissions can be used for Dataproc jobs. There's a permission to cancel jobs, to create a job, to delete a job, to get a job, to list the jobs, or to update a job. I'm going to select all of these permissions, and I'll click Add. And you can see that they've been added. I'll click on Add Permissions again, and in my filter, this time I'm going to type Dataproc.clusters, and you can see all the permissions for clusters. There's a permission to create a cluster, to delete, to get a cluster, to get the Identity Access Management policy, to get a list of clusters, to set the Identity Access Management policy, to update a cluster, and to use a cluster. I'll select all of these permissions, and I'll click Add. I'll click Add Permissions again, and in my filter, this time I'm going to type Dataproc.operations, and I see all the permissions that are related to operations. I can cancel an operation, I can delete an operation, I can get an operation, or I can get the list of operations. Once again, I'll select all of these options, and I'll click Add. I'll click on Add Permissions again. In the filter, this time I'm going to type Dataproc.workflow templates and hit Enter. So this time I see all the permissions that relate to workflow templates. I can create a workflow template. I can delete one. I can get a workflow template. I can instantiate it. I can instantiate it inline. I can list it. And I can update it. So once again, I will select all the permissions and I will click Add. I'm going to click on Create. I will filter this, so I will type Dataproc. And you can see that I have a new custom role called Dataproc Custom. In this exercise, you will recognize the process in creating a cluster in Cloud Dataproc. You will manage the Cloud Dataproc cluster and recognize the process in deleting a cluster. So now, pause the video and try this exercise yourself. To start, I'm going to click on the menu in the upper left-hand corner. I'll go to Dataproc. I'll click on Clusters, and I want to enable this API. Cloud Dataproc can be used to run Apache Hadoop clusters. So next, I'm going to create a new cluster. I'll click on Create Cluster. I'll leave the default name. For my region, I'll select Global. For my zone, I'll select US East 1B. For my cluster node, I'll keep it as standard. I want to have 4 vCPUs. The memory allocated will be 15 gigabytes. I will leave the default settings for my worker nodes. And my worker nodes will have 500 gigabytes of disk size. I'm going to have 2 nodes. And this cluster is configured to have 8 yarn cores. And the yarn memory will be 24 gigabytes. I'll take a look at the other options available. I'm not going to add any other nodes. So I'm going to click on Create. And my cluster is being provisioned. So my cluster is finished provisioning. We'll take a look at the cluster. So I'll click on my cluster. I can see an overview. If I click on Equivalent REST, I can see my equivalent REST response. I'll close this window. I'll click on my jobs. So I currently have no jobs. I'll click on Equivalent REST. So once again, I see the equivalent REST response. I'll close this window. I'll click on VM Instances. You can see the virtual machines that were displayed in the resource window. I have a master and I have 2 worker nodes. I will click on Equivalent REST again. And you can see my equivalent REST response. I'll click Close. Next, I'll take a look at my configuration. I'll click on Edit and take a look at some of the options that I have available. So things that I can change are my number of worker nodes. I'll change this to 1. And I am told that I must have at least 2 worker nodes. I'll put that back to 2. I could have preemptible worker nodes. I'll try adding 2 of those. You can see the cloud storage bucket that I'm using. I'll open my storage bucket in a new tab. And we'll take a look at it. And I'll look at my storage bucket. So right now I have 1 bucket. And it has a folder. I'm going to close my storage buckets. I can change my cluster name, my UUID, and my location. For now, I'm going to click Cancel. I can also manage my clusters from the Google Cloud Shell. I'm going to activate it, and I will have it open in a new window. I'm going to type gcloud, Dataproc, clusters, and this will show me all my available commands. So I can do a create, a delete, a describe, a diagnose, list, and an update. I will type gcloud, Dataproc, clusters, list, and this will show me all my available clusters. I'm going to change my command, and I will type describe, and I will type cluster hyphen ABC5, and this will show me information on my cluster. There's also different ways that I can delete my cluster. From the Cloud shell, I'll change my command, and so for my command, I could have gcloud Dataproc clusters delete, and the name of the cluster. I will go back to the Cloud UI. I'll click on clusters. So if I want to do a delete from here, I can select my cluster and I can click on delete. Or if I'm inside my cluster again, I can click delete here. And I get a message, do you want to delete your cluster? I'm going to click on OK. And my cluster is being deleted. Once it's done, the status will update and I will receive a message. In this video, I will discuss using the Dataproc REST API. The Google Cloud Dataproc REST API manages Hadoop-based clusters and jobs on the Google Cloud Platform. The Cloud Dataproc Workflow Templates API provides a flexible and easy-to-use mechanism for managing and executing workflows. A workflow template can be defined with the following values: with a template ID, the resource name of the template, and the optional version number. The create time and update time are output-only values. Optional labels can be used to associate this template. The placement is the required scheduling information. There is also a directed acyclic graph of jobs to submit. The workflow template placement specifies the workflow execution target. This can be a managed cluster, which is a cluster that is managed by the workflow, or a cluster selector, which chooses target clusters for jobs based on metadata. Cluster names within a project must be unique. An ordered job is a job executed by the workflow. Some of the required values include the step ID, labels can be associated with the job scheduling can be configured and is optional, and the job type can be one of the following: Hadoop job, Spark job, PySpark job, Hive job, and Pig job. The projects.regions.clusters REST resource describes the identifying information, configuration, and status of a cluster of compute engine instances. Some of the values in the JSON representation include the Google Cloud Platform Project ID, the cluster name, which is unique within a project, the cluster configuration, labels to associate with this cluster, the cluster status is output only, the previous cluster status is also output only, and a cluster UUID, and there can also be cluster metrics. The cluster status is the status of a cluster and its instances. The values for state include unknown, creating, running, error, deleting, and updating. The substate can be unspecified, unhealthy, or stale status. And cluster metrics contains cluster daemon metrics such as HDFS and yarn stats. Projects.regions.jobs is the JSON representation for jobs in a region. Some of the values in this resource include the reference. This is the fully qualified reference to the job. The placement is job information, including how, when, and where to run the job. Status is an output-only value, which contains information on the job status. Status history contains the previous job statuses. Yarn applications is the collection of yarn applications spun up by this job. Labels can be associated with this job. Scheduling contains job scheduling configuration information. The job types can be a Hadoop job, Spark job, and Hive job. The job reference contains a project ID and a job ID. Job placement contains the cluster name and the cluster UUID. Job status contains the state and details that pertain to the job. The long-running operation resource represents a long-running operation that is the result of a network API call. The projects.regions.operations JSON representation contains the name, metadata associated with the operation, a done Boolean value. If the value is false, then the operation is still in progress. If true, then the operation is completed. Error contains the error result of the operation. Response contains the normal response of the operation in case of success. In this video, I will describe the various Dataproc architecture types in the Google Cloud Platform and common use cases. This diagram displays a high-level overview of the real-time streaming architecture. Devices are physical devices that interact with the world and collect data. Ingestion or data import is the process of sending information from devices to the Cloud Platform services. Pipelines manage data after it arrives in a cloud platform. Storage is where data is being stored. Data from the physical world comes in various shapes and sizes. The Google Cloud Platform offers a wide range of storage solutions. Analytics is where you extract the information from the raw or processed data. Application and presentation is where you present your formatted results using an engine. Devices are physical objects that interact with the world and collect data. They can be classified into two groups. Devices can be either constrained or standard. Constrained devices can be very small and have very few resources. Standard devices more likely resemble small computers. For data import, we can use Cloud Pub Sub. Cloud Pub Sub is a messaging system that can act like a shock absorber, both for incoming data streams as well as changes to application architecture. Stack driver monitoring and stack driver logging are used for gathering information on the health of a system. Pipelines manage data after it arrives on the Google Cloud Platform. Pipelines can perform the following tasks. They can be used for transforming data. You can convert data from one format into another. Pipelines can be used to aggregate and compute data. Calculations can be performed in the pipeline. They can be used to enrich data, and you can use it for moving data. Processed data can be stored in one or more storage locations. The Google Cloud Platform offers a range of storage solutions such as Cloud Storage, Cloud Data Store, and Cloud Bigtable. Analytics is where you extract the information value from the raw or processed data. BigQuery is a fully managed data warehouse. Cloud Dataflow supports both batch and streaming flow modes. Cloud Datalab is an interactive data workbench to explore datasets. And Cloud Dataproc is a fully managed cluster solution for running Hadoop and Spark. You can use a variety of services for hosting applications on the cloud platform. The Kubernetes engine can be used for container-based applications. App Engine can be used for standard and flexible environments as managed platforms for scalable applications. And Compute Engine offers high-performance virtual machines for maximum flexibility. Some common use cases for using Google Cloud Services includes creating mobile applications that scale as your user base increases. Development and testing can be done cost-effectively by using only the resources that you need when you need them. Web applications and websites can be delivered on fast, scalable virtual machines over Google's fiber network. Retail services can serve a global base with industry-leading scale and analytics to personalize the user experience. The Google Cloud Platform allows you to analyze big data at the scale of the entire web. Media can be managed using the Google infrastructure to manage rendering, media archival, and transcoding. Gaming can be managed for a global player base using Google's Cloud Fiber Network. And financial services can scale to a massive transactional volume on a cloud platform designed for security and reliability. In this video, I will define Dataproc machine types and their use. A machine type specifies a particular collection of virtualized hardware resources. These resources include memory size, virtual CPU count, and maximum persistent disk capability. Predefined machine types have a fixed collection of resources and are managed by the Google Compute Engine. You can also define your own custom machine type. To view a list of all available machine types, From the Google Cloud Platform SDK, type gcloud compute machine types list. A standard machine type has a balanced CPU to memory ratio. The maximum PD size is 64 terabytes. The amount of virtual CPUs available are from 1 to 96. The maximum number of persistent disks is 16. And the available memory starts at 3.75 gigabytes and goes up to 360 gigabytes. The names of the virtual machines start with N1-standard, and the last number is the number of virtual CPUs. High memory machine types are ideal for tasks that require more memory relative to virtual CPUs. High memory machine types have 6.5 gigabytes of system memory per virtual CPU. The max total persistent disk size is 64 terabytes. The number of virtual CPUs range from 2 to 96. The max number of persistent disks is 16. And the memory per machine ranges from 13 gigabytes up to 624 gigabytes. The last number in the machine type name refers to the number of virtual CPUs. So for example, N1 high mem-2 refers to a machine type that has 2 virtual CPUs. High CPU machine types are ideal for tasks that require more virtual CPUs relative to memory. High CPU machine types have 0.9 gigabytes of system memory per virtual CPU. They have a higher CPU to memory ratio. The max total persistent disk size is 64 terabytes. The number of virtual CPUs range from 2 to 96. The max number of persistent disks is 16. And the memory available ranges from 1.8 gigabytes to 86.4 gigabytes. The machine type names are N1 high CPU-2 all the way up to -96. The last number indicates the number of virtual CPUs. Shared core machine types provide one virtual CPU that is allowed to run for a portion of the time on a single hardware hyperthread. Shared core instances can be more cost-effective for running small, non-resource intensive applications than standard or high CPU machine types. F1 micro machine types offer bursting capabilities that allow instances to use additional physical CPU for short periods of time. You can use either a F1 micro or a G1 small machine. Mega memory machine types are ideal for tasks that require intensive use of memory with higher memory to virtual CPU ratios than high memory machine types. These machine types are perfectly suited for in-memory databases and in-memory analytics. Mega memory machine types have 15 gigabytes of system memory per virtual CPU. The name of the machine type is N1 megamem-96. It has 15 gigabytes of RAM. It has 96 virtual CPUs with 15 gigabytes of RAM per virtual CPU. The total memory is 1,433.6 gigabytes of RAM. The max number of persistent disks is 16, and the max total PD size is 64 terabytes. Mega memory machine types are available in the following regions: US Central 1, US West 1, Asia East 1, Europe West 1, and Europe West 3. You can also define a custom machine type. With a custom machine type, you can specify the number of vCPUs and the amount of memory for your instance. Custom machine types are ideal for workloads that are not a good fit for the predefined machine types that are available to you. Custom machine types cost more than a predefined machine type, and there are limitations in the amount of memory and vCPUs you can select. In this video, I'm going to configure and create a custom machine type. So to start, I'm going to create a new cluster. I'll go to my menu in the upper left-hand corner. I'll click on Dataproc. I'm going to click on Create Cluster. I'm going to create a customized cluster. I will leave the cluster name the same. For my region, I will leave it as global. For my zone, I will select US East 1B. For my cluster mode, I will leave this as standard. For my master node, I will select Customize. In this view, I can select the number of cores and the amount of memory. So I'll drag this down to 1, and you'll notice that memory has changed. Or I can increase the number of cores all the way up to 8, and my memory has changed again. And every time I change my number of cores, the amount of memory changes as well. Go down to 6, 4, 2, and 1. I can also extend my memory. So I'll click on Extend Memory. This option will add extra memory. I can still add extra memory here, but you'll notice that it turns yellow if I go over 6.5. I'll put this back down to 3.5, and I will get rid of Extend Memory. For my disk size, I will have 500 gigabytes. I can have a minimum of 10 gigabytes. For my worker nodes, I will select Customize. I can select the number of cores and the amount of memory for each worker node. I can select 1, 2, 4, 6, or 8. When I change the number of cores, the amount of memory changes as well. For now, I'll put this down to 1 core. I will decrease the memory as well to 1 gigabyte. I can extend memory if I wanted to, but I'm not going to. For my disk size, I will have 500 gigabytes. Number of nodes will be 2. If I wanted to, I could select a solid-state drive. For my number of yarn cores, I will select 2. And for yarn memory, I will leave this as 1.6 gigabytes. At this point, to create my cluster, I could click on the Create button. Or I could look at the equivalent REST or the command line options. I will click on Command Line. This is the command that I would use from gcloud to create this cluster with the selected parameters. I'm going to go select all this code. I'm going to copy this command and then go to the Cloud Shell. I'm going to paste the command on the command line and I will hit Enter. So I get an error that I need to add more memory. I'll modify the amount of memory that I'm going to use. I will change this to 3584 and I will hit Enter again. So now that I fixed my memory issue, my cluster is being created. And I will wait for my cluster to be created. So my cluster is created. I will go back to my console. And you can see that the cluster has been created. In this video, I'm going to demonstrate how to create a Dataproc job using the gcloud command line and the console. So for this demo, I've already created a cluster called Cluster Test. I'll take a look at my cluster. So here's an overview of my cluster. I will take a look at the jobs for this cluster. And there are currently no jobs. I'll look at my VM instances and my configuration. I'll go back to jobs. I'll take a look at jobs down here as well. And you can see that there are no jobs running. I'm going to go to the Cloud Shell. I'm going to paste in a Spark example that will calculate pi using the Monte Carlo method. So the command is gcloud, Dataproc, jobs, submit, Spark. We're going to submit this job to cluster test. The class is org.apache.spark.examples.sparkpi. The jar file can be found at the specified file path. And for a parameter, we're going to enter 1000. I will start the Spark job. So this is going to run. I'm going to go back and look at my jobs. And I'll click refresh. And my job ran and succeeded. I'll go back to the Cloud Shell. I'll scroll up a little bit. And you can see that the value of pi was calculated. I'm going to submit the same job using the console. So I will click on Submit Job. My region will be global. My cluster is Cluster Test. This will be a Spark job. The main class is org.apache.spark.examples.sparkpi. The argument is 1000. And the file path is user lib spark examples jars sparkexamples.jar. I'm going to submit my job. And my job is now running. I'll click on the job and I can view the output. So you can see that the value is being calculated. To see my results, I need to click on line wrapping. So you can see the actual calculations being performed. And you can see that the value of pi has been calculated. I'll go back to look at my jobs. And you can see that both jobs have run. I will take a look at the job that I created earlier. And I'll click on line wrapping. And you can see the same results. In this video, I'm going to use Hadoop in the Google Cloud Platform. I'm already logged into the Google Cloud Platform. I'm going to look at the cluster. I can see an overview. It has information on the CPU utilization, the disk bytes, disk operations, network bytes, and network packets. I'll look at my jobs. I'll look at my instances and my configuration. I'll go back to VM instances and I'll click on SSH. I'm connecting to the virtual machine. I want to upload a file. So I'll click on upload. I have a file called shakespeare.txt. If you open this file, you'll see that it has all the works of William Shakespeare. We're going to use this file for our word count test. So I'm going to upload this file. So the file is uploading. I'll click on close and I'll take a look at my directory. So you can see my file has been uploaded. I'm going to make a new directory in the DFS. So I'm going to type Hadoop, DFS, mkdir, tmp/in. I'm going to copy the Shakespeare file to this new folder. So I'm going to type Hadoop, DFS, put Shakespeare.txt, tmp/in. So the file has been copied. To make sure it's there, I'll type Hadoop, DFS, ls, tmp/in. And you can see that the file is there. I'm going to paste in the code for doing the word count. It's going to take the Shakespeare file that's in the in folder, and it'll put the results in temp output. So my job's going to run. It's going to do the mapping first and then the reduce. So my job finished running. We'll take a look at the output. So I'll type hdfs, dfs, cat, tmp/output. I'll try that again. I need to put a star. And you can see the word counts. In this video, I will describe the use of Apache Pig and Apache Hive. Apache Hive is a data warehouse software project built on top of Apache Hadoop for providing data summarization, query, and analysis. Hive gives an SQL interface to query data stored in various databases and file systems that integrate with Hadoop. Processing a dataset using Hive on Google Cloud Dataproc requires the following main steps. The first step is to enable the Google Cloud Compute Engine API. Next, we need to create a storage bucket. Then we need to load the data into the storage bucket. Next, we need to create and deploy a Google Cloud Dataproc cluster. We then need to connect to the master node using a secure shell. We then need to run the beeline command line interface to Hive and issue SQL statements. And then the final step is to shut down the cluster. The beeline shell is a command line interface to the Hive processing system. Run the beeline shell using the JDBC Hive interface. Hive runs on localhost at port 10,000. At the SSH command line, type beeline-u JDBC, Hive2, localhost 10,000/default. For the username, specify the username and the master node hostname. And for the driver, we're going to use org.apache.hive.jdbc.hive_driver. There are two main ways of working with data under Hive. Use createTable to move the data from the HDFS into the Hive file system as a table. Once the data is moved into the Hive table, the file is removed from the regular HDFS. Or you can use createExternalTable. This will leave the source data file in the HDFS. With this approach, the data stays where it is, but the table can be manipulated using the same SQL statements. For example, we can create an external table with a given column structure that will use the existing data file. Pig is a high-level scripting language that is used with Apache Hadoop. The simple SQL-like scripting language is called Pig Latin and is similar to SQL. To submit a Pig job to a Dataproc cluster, from the Cloud command line, you would type gcloud beta Dataproc jobs submit Pig. For cluster, you would specify the cluster name. For execute, you would specify a Pig query to execute as part of the job. For file, you would specify the HCFS URI of the file containing the Pig script to execute as part of the job. Some of the optional flags include async, which means not to wait for the job while it's running, bucket, which is the cloud storage bucket to stage files in, continue on failure, which means to continue if a single query fails, driver log levels. This specifies the detail of logging that you want to occur. Labels is a list of key value pairs. Max failures per hour specifies the maximum number of times a job can be restarted. Params is a list of key value pairs to set variables in the Pig queries. And region specifies the Cloud Dataproc region to use. In this video, I will work with Apache Hive using a Dataproc cluster. I'm going to create a new storage bucket where I will upload a CSV file. So I'm going to click on Create Bucket. For the bucket name, I will type Skillsoft Test Bucket. And I will click Create. I'm going to create a folder called Data. I'm going to create a folder called Output. And I will create a folder called Logs. I will click on the Data folder. I'm going to look at my clusters. So I currently have a cluster running. I'll take a look at my cluster. I'll go to my VM instances. And for my master cluster, I will start SSH. I'm going to see if there's any files in the folder that I just created. So I'm going to paste in some code to look at my folder. And there are no files in this folder. I'm going to use curl to copy a file that has sample trade information. So I'll paste in the command and hit enter. And the file is downloading. I'll look at my file. This file is available locally, but it's not in my storage bucket. So I'll take a look at my storage bucket again. So you can see that the file is not in the storage bucket. So I need to copy the file from the local folder to the storage bucket. I'm going to use gsutil with a copy command to copy the file to the storage bucket. So the file is being copied. I'll take a look at my storage bucket again. And the file is there. The reason I'm putting the files in the storage bucket is because Hive needs to have the files there to use them. I'm going to start Hive by using the beeline command. I'm going to load the trades_sample.csv file into Hive. And I will hit enter. I will look at my table, so I will type describe trades_sample, semicolon. The information for this table is displayed. I want to see how many rows I have in this database table, so I will type select count star from trades underscore sample. And the number of rows is displayed. Next, I'm going to try to retrieve a list of trades that happened during the first minute of a trade at 9:30 a.m. in the morning. I will paste in some code to do this query. And I can see the results of my database query. Next, I will find the total trading volume for each stock before 12 noon. I'll paste in some more SQL code and hit enter. And the results are shown. In this video, you will create a cluster and configure a custom machine, execute Dataproc jobs, and recognize connections between Apache Hadoop, HDFS, and cloud storage. So now, pause the video and try this exercise on your own. Let's take a look at how I would perform this exercise. I'm going to click on Create Cluster. I'm going to create a customized cluster. I will leave the cluster name the same. For my region, I will leave it as global. For my zone, I will select US East 1B. For my cluster mode, I will leave this as standard. For my master node, I will select Customize. In this view, I can select the number of cores and the amount of memory. So I'll drag this down to 1, and you'll notice that memory has changed. Or I can increase the number of cores all the way up to 8, and my memory has changed again. And every time I change my number of cores, the amount of memory changes as well. Go down to 6, 4, 2, and 1. I can also extend my memory. So I'll click on Extend Memory. This option will add extra memory. I can still add extra memory here, but you'll notice that it turns yellow if I go over 6.5. I'll put this back down to 3.5, and I will get rid of Extend Memory. For my disk size, I will have 500 gigabytes. I can have a minimum of 10 gigabytes. For my worker nodes, I will select Customize. I can select the number of cores and the amount of memory for each worker node. I can select 1, 2, 4, 6, or 8. When I change the number of cores, the amount of memory changes as well. For now, I'll put this down to 1 core. I will decrease the memory as well to 1 gigabyte. I can extend memory if I wanted to, but I'm not going to. For my disk size, I will have 500 gigabytes. Number of nodes will be 2. If I wanted to, I could select a solid-state drive. For my number of yarn cores, I will select 2. And for yarn memory, I will leave this as 1.6 gigabytes. At this point, to create my cluster, I could click on the Create button. Or I could look at the equivalent REST or the command line options. I will click on Command Line. This is the command that I would use from gcloud to create this cluster with the selected parameters. I'm going to go select all this code. I'm going to copy this command and then go to the Cloud Shell. I'm going to paste the command on the command line and I will hit enter. So I get an error that I need to add more memory. I'll modify the amount of memory that I'm going to use. I will change this to 3584 and I will hit enter again. So now that I fixed my memory issue, my cluster is being created. And I will wait for my cluster to be created. So my cluster is created. I will go back to my console. And you can see that the cluster has been created. I'll take a look at my cluster. So here's an overview of my cluster. I will take a look at the jobs for this cluster. And there are currently no jobs. I'll look at my VM instances and my configuration. I'll go back to jobs. I'll take a look at jobs down here as well. And you can see that there are no jobs running. I'm going to go to the Cloud Shell. I'm going to paste in a Spark example that will calculate pi using the Monte Carlo method. So the command is gcloud dataproc jobs submit Spark. We're going to submit this job to cluster test. The class is org.apache.spark.examples.sparkpi. The jar file can be found at the specified file path. And for a parameter, we're going to enter 1000. I will start the Spark job. So this is going to run. I'm going to go back and look at my jobs. And I'll click refresh. And my job ran and succeeded. I'll go back to the Cloud Shell. I'll scroll up a little bit. And you can see that the value of pi was calculated. I'm going to see if there's any files in the folder that I just created. So I'm going to paste in some code to look at my folder. And there are no files in this folder. I'm going to use curl to copy a file that has sample trade information. So I'll paste in the command and hit enter. And the file is downloading. I'll look at my file. This file is available locally, but it's not in my storage bucket. So I'll take a look at my storage bucket again. So you can see that the file is not in the storage bucket. So I need to copy the file from the local folder to the storage bucket. I'm going to use gsutil with a copy command to copy the file to the storage bucket. So the file is being copied. I'll take a look at my storage bucket again. And the file is there. The reason I'm putting the files in the storage bucket is because Hive needs to have the files there to use them. I'm going to start Hive by using the beeline command. I'm going to load the trades_sample.csv file into Hive. And I will hit enter. I will look at my table, so I will type describe trades_sample, semicolon. The information for this table is displayed. I want to see how many rows I have in this database table, so I will type select count star from trades_sample. And the number of rows is displayed. Next, I'm going to try to retrieve a list of trades that happened during the first minute of a trade at 9:30 a.m. in the morning. I will paste in some code to do this query. And I can see the results of my database query. Next, I will find the total trading volume for each stock before 12 noon. I'll paste in some more SQL code and hit enter. And the results are shown.
In this video, I'll recognize the benefits of compute and storage separation with Dataproc. As I mentioned in the previous video, Google Dataproc compute and storage resources are separate in the Cloud Dataproc architecture, with Google Compute virtual machines providing compute resources and Google Cloud file storage resources being used to store files instead of the standard Hadoop HDFS file system. In standard Hadoop, before Google Dataproc was created, a cluster was required to be up and running before big data jobs such as MapReduce operations could be submitted to it. With Dataproc, clusters boot up very quickly and billing is done on a per-minute basis. Due to this advancement, Dataproc reverses the order of operations and actually allows a cluster to be deployed on demand to complete a specific job. With these improvements, management of a cluster becomes much easier, as jobs don't need to contend for resources with each other, and they are isolated to their own cluster, which is custom-sized in terms of memory and CPU specifications to meet the job's requirements. There is also no need to prioritize jobs on a single cluster through Yarn or another resource manager, as each job has its own cluster, which allows for more simple cluster management. Since the jobs run on separate clusters, they are isolated, and troubleshooting jobs becomes easier as there are no resource contention issues, so the root cause of the issue can be found more quickly. Dataproc bills on a per-minute basis, so that clusters can be shut down whenever a job is complete, and if a cluster is to be run longer, there are no contracts or monthly payments required. Since the VMs deployed to complete a job are completely customizable in terms of CPU and memory requirements, there is no reason to have extra costs incurred for unused resources. For longer running clusters that actually do need to use HDFS storage, Dataproc offers local SSD storage, which is extremely quick, and this is similar to RAM speeds and reasonably priced. And when you shut off a cluster, all of that gets saved to the Google Cloud storage, and that state is saved if you want to rerun cluster with the same data. So those are some of the main advantages of Dataproc and the separation of storage and compute. In this video, I'll recognize the process of monitoring and logging Dataproc jobs. Dataproc jobs can be monitored through the Google Stackdriver monitoring utility. Stackdriver monitoring is a Google monitoring tool which takes in information and displays it in easy-to-understand formats such as dashboards, alerts, and charts for various cloud-powered applications. Stackdriver metrics are displayed in visual format on various web dashboards, charts, and additional Stackdriver services also include log tracing, alerting, and reporting capabilities. Stackdriver is integrated by default into Amazon Web Services, Google Cloud Platform or GCS, which Dataproc is a part of, as you all know, and with various mainstream open source applications. With Google Dataproc, Stackdriver takes in and stores analytics such as metadata, metrics, and events for Google Compute Engine virtual machines, which are the backbone of Cloud Dataproc clusters. These analytics that Stackdriver has collected can then be transformed into easy-to-read performance data via the web dashboards, charts, and alerts in order to more easily view the health, performance, and uptime of Google Cloud virtual machines and Dataproc clusters as a whole. Stackdriver also allows you to set alerts and to integrate these performance alerts with collaborative tools such as PagerDuty, Slack, and HipChat so you could get them across for the whole team. So now I'm actually going to talk about how you could turn Stackdriver on and use it with Dataproc. So the first step in order to turn it on is that we actually have to note that it is included with Dataproc, but it's not enabled. So we could go ahead and we could actually enable Stackdriver with Dataproc by using the gcloud Dataproc command line tools from the Google Cloud SDK, and we could specify a properties flag, as you could see down here, -- properties. We have Dataproc : Dataproc.monitoring.stackdriver.enable, and we'll set it to true. So this can be done when we're actually creating our Cloud Dataproc cluster, and if we set that, it'll ensure that Stackdriver is turned on. Now, just a note that since Stackdriver is a separate service from Cloud Dataproc, it does get billed on top of the Cloud Dataproc usage as an additional service if it is turned on for a Dataproc cluster. So that could be a surprise to some people, but just know that since it is an additional service, it is billed separately, and you will probably get more billing and it'll cost more to use Stackdriver. So after Stackdriver is enabled for a Dataproc cluster using the gcloud command line tools, as I showed you down here, the next step would be to create a new monitoring group for the cluster. So the monitoring group name must share a prefix with the Cloud Dataproc cluster name. So one easy way to make sure the name is appropriate is to simply name the monitoring group to the same name as the Cloud Dataproc cluster name. After the monitoring group is set up, data is sent from the Dataproc cluster VMs to Stackdriver, and no further configuration of Stackdriver is necessary. So any new instances or virtual machines in the Dataproc cluster automatically start sending data into Stackdriver when they are created if they are in a cluster that's being monitored by Stackdriver. If you actually want to view the information, you could log into the Stackdriver web dashboard, and from here you could view different dashboards, charts, you could set alerts, and by doing that, you could look at different Dataproc metrics such as health, performance, and uptime of the cluster, and you could kind of get a better sense of the data. So that's how we could go about monitor and logging jobs by using the Stackdriver Google utility through Cloud Dataproc. In this demo, I'll demonstrate the process to SSH into master and worker nodes in a cluster, as well as talking about how to access web interfaces for Google Cloud Dataproc. The main pieces of Google Cloud Dataproc, such as Hadoop and Spark, provide web interfaces to manage cluster components such as MapReduce, Yarn, and HDFS. The best way to connect to these interfaces is through SSH and can be done in a two-step process. The first step is to use an SSH client to open a new SSH tunnel. After this is done, the SOCKS protocol can be used to route data to the Dataproc cluster using the newly created SSH tunnel. Alternatively, what I'll be demonstrating is there's an easier way to do this. You could create a firewall rule through the Google Cloud Platform web dashboard, and then the Dataproc cluster's public IP address can be used to access the web interfaces for Hadoop and HDFS. So first of all, I'll start off talking about SSHing to master and worker nodes. So SSH to a Dataproc master or worker node can be done either through the Dataproc web dashboard or by using the Google Cloud SDK command prompt gcloud compute SSH command, specifying the zone and the node name. So here you could see I'm in my browser, I'm in Chrome, and under Google Cloud Platform, I selected Dataproc, and I have a cluster called cluster-boris test. If I click on the cluster, I could see that I actually have one master node and two worker nodes. If I click on VM instances, I could click on cluster-boris test-m, which is my master node. And if I go into it, I could actually see it's in the zone US East 1-B. So I'll go ahead and open up my Google SDK command prompt. And the first thing I want to do is I want to make sure I use the gcloud config set project to the node-js-chat form, which is the current project I have my cluster in. So I'm going to run this gcloud config command. After that's done, I'm going to go ahead and I'm going to run gcloud compute SSH, and I'm going to specify the zone. So it's US-East 1-B, which we saw from the instance in the web dashboard, and then cluster-boris test-m. So I'm going to basically SSH into the master node. If I hit enter, it's going to open up PuTTY in this case because I'm using Windows and I have PuTTY installed for my SSH client. And I could just make sure, for example, I have Hive installed, which is a Hadoop component. Once I'm SSH'd in successfully, I could see I have Hive and other Hadoop components installed by checking the version. So I could see I have Hive 2.1.1 installed. Now let's SSH into a worker node. So going back into our web dashboard here, I'll go back to my VM instances. And if I click on VM instances, notice that I have the option to SSH into master right from here. If I click on a worker, I could click on my cluster-boris test-w-0 for my first worker. I'll hit on SSH to SSH into this worker. This will actually open up an SSH command window inside my Google Chrome browser, and I'll be able to enter some commands similarly as I did by using gcloud to SSH into my master node. Okay, so I could see I'm in here now. I could once again see if I have Hive installed. And I'll just make sure that I get the version number. So you could see I am SSH'd into my worker node. And I did this simply by clicking SSH from the instances page from within my Google Cloud web dashboard for Dataproc. So now I'm actually going to move along and I'm going to talk about the web dashboard. So once again, we could access the Hadoop and HDFS web dashboards. So one easy way to do this is to set the firewall settings. So what I'm going to do is here in the web, in the Google Cloud Platform web dashboard, I'll scroll down and I'm actually going to go to my VPC networks under networking and I'll click on firewall rules. I want to configure a new firewall rule, so I already have one configured, but I'll just go over what I did. It's called default-allow-Dataproc access. If I open that up, what I did was I basically specified the IP address range of my local computer, so 209.171.88.129-32. Network as default, priority as 1000, direction ingress, action on match allow. So I'm basically allowing all from the protocols and ports, so TCP 8088, which is the port that's used for Hadoop, and TCP 9870, which is the port that is used for HDFS, and I'm also including TCP 8080. So now that I've done this, I could actually go back in my menu back to Dataproc at the bottom here. If I click on Dataproc, and I could go back to my master node, And I want to use the master node public IP address. So under VM instances, I'll click on cluster-bors test-m, my master node. And I'll want to get the IP address. So the external IP address is 35.231.102.255. And let's try to go into Hadoop. So I'll just paste this address and enter port 8088, and I'll get my cluster Hadoop web dashboard. I could take a look at it. I could see I have 2 active nodes. I could click on that to see more details. I could see I have my worker 0, my worker 1 node. I could see the memory available, and so on. I could also query my HDFS dashboard. So that's with 9870. If I enter my external IP address of the master :9870, I'll get the HDFS dashboard, and I'll be able to see my HDFS usage and so on, and go through my menu, look at my data nodes, my snapshots, my startup progress, my utilities, and so on. So that's how we could go about actually interfacing or actually accessing these web interfaces by simply setting a simple firewall rule which allows our IP address to connect to the Hadoop and the HDFS web interface dashboards. In this video, I'll define the Spark Python API, or PySpark, read, evaluate, print loop, or REPL, and its use in Linux. Apache Spark, as most of you know, is an integral part of Google Dataproc along with Hadoop. It is used for big data processing, graph processing, streaming, and machine learning. Spark supports various programming languages such as Python, R, Scala, and Java. Although Python for Spark is slower than Scala, it has a number of advantages, including the fact that it is easier to learn and flexible and dynamically typed and is better for prototyping experiments. The PySpark REPL interfaces with the Spark programming model and exposes it to Python by using Python scripts to control Spark. PySpark requires that Python version 2.6 or higher is installed alongside with Spark being installed. PySpark can be installed through the pip package management tool. Spark requires that Java is installed before it can be installed. All PySpark dependencies are automatically imported as they are all bundled as part of PySpark. To run PySpark for a standalone application, the /bin/PySpark script can be started in a console window by typing PySpark, and Java and Python environments will automatically be configured. For PySpark to start up successfully, it is important that the Spark_home environment variable contain the Spark installation directory, as well as having updated path environment variables for the installation location of Python. We will also want to ensure that the p4yj package path is in the system path, as this package is required for the Python interpreter to dynamically access Java objects, which is needed for PySpark to interface with the Java virtual machine of Spark. The p4yj package should be in the system path when PySpark is installed by default. It is also required to ensure that the Spark context or SC is initialized, which should be done by PySpark by default. If this is not done, to initialize the Spark context, the shell.py script located within the Python PySpark directory can be executed in order to instantiate a new Spark instance. Once PySpark is configured, it can interface with Spark in order to start jobs, control a Spark instance, and to run transformations. To submit a new PySpark job to a Spark cluster using Google Dataproc, the gcloud beta Dataproc jobs submit PySpark -- cluster and then the cluster name and then the script name ending with py command can be used. PySpark can also be run with the Jupyter Notebook, which allows you to share, run, and modify Python code in a web view, making it easier to test Python programs and get a better visual of what's going on. You can configure the PySpark environment variables in the .bashrc file in Linux in the home directory to use Jupyter Notebook to execute Python scripts in a graphical web environment when using PySpark, and this will make it easier to view the script results. In this video, I'll describe the process of compute and storage and benefits of its separation. As I mentioned in a previous video, in Google Cloud Dataproc, compute and storage are separated, and this has a number of advantages in terms of cost savings, performance, and ease of management. Decoupling of compute and storage is the new way that Hadoop clusters are deployed and is the essence of Google Cloud Dataproc. With VM technology advances and network speed increases over the past few years, virtual machines can now be used as the backbone of a Hadoop cluster. These VMs in a Hadoop cluster are connected across the internet with high-speed links that can transmit data at over 10 gigabytes per second. The data is stored on persistent cloud storage. For this case, if we're using Cloud Dataproc, it would be GCS or Google Cloud Storage. With this type of architecture in use, we can now offer Hadoop as an IaaS distribution. And this is going to simplify management, improve performance, and reduce costs compared to bare metal Hadoop clusters. And that's what we saw with Google Cloud Dataproc. So in traditional bare metal Hadoop clusters, upgrading storage, which was in terms of IO ops or capacity, had to be done linearly with upgrading compute resources such as RAM and CPU. So this often resulted in overpaying, as an increase of storage was not always required for an increase in compute performance. And an increase in compute performance was not always required when we needed more storage. So if you look at the first graph, we see a linear relationship. As we increase compute, we have to increase storage. And this is an example of a bare metal Hadoop distribution. Now we'll look at the one on the right. So by using VMs and separating compute from storage in a virtualized environment, compute resources can now grow separate from storage resources, depending on cluster requirements and vice versa, which results in cost savings for the customer. So if we take a look at this, we see that as storage goes up, compute only has to go up to a certain point. And let's say we have enough compute resources at this point. The cost for compute resources remains the same, whereas the cost for storage keeps going up. So you could see the obvious cost savings on compute resources by having this virtualized deployment of Hadoop, because storage and compute are now decoupled. So I'll just talk about a few more key benefits of having a virtualized distribution of Hadoop. So with IaaS deployments of Hadoop in virtualized environments, data is better protected as security monitoring system updates are done by the cloud provider and are not required by the customer. This saves the customer costs and time for maintaining and updating the clusters, as all updates are kept up to date automatically by the cloud service provider. Real-time security threats and analysis can also be incorporated with IaaS Hadoop deployments, which can help security analysts detect and correct problems as soon as they occur. When storage and compute are decoupled and real-time log analytics are in use, sending data between one application and another becomes easier and faster and more secure, as does gathering data from different data sources and analyzing it in a real-time fashion to get a better picture of what the data has to show. Scale also becomes easier, as compute and storage can scale independently to meet the workload or per job requirements, which can increase performance and reduce costs. Another advantage is that data does not have to be replicated across multiple environments, as the same storage backend can be used for more than one environment with cloud storage. Getting started on a project also becomes easier and more quick, because resources are available on demand and can be deployed rapidly and cheaply compared to setting up a bare metal Hadoop cluster with real hardware. Scaling also becomes easier with independent job-specific scaling of compute and storage resources, and auto-scaling options available to reduce the cost when the compute and storage resources are no longer required. In this video, I'll define BigQuery and its benefits for large-scale analytics. BigQuery is a serverless, logical, big data enterprise data warehouse provided by the Google Cloud Platform. Its focus is on data analysis on large datasets, and it supports SQL queries to analyze data. BigQuery is a cloud infrastructure as a service, or IaaS offering, and it integrates with Google Cloud Storage, or GCS. BigQuery can also be integrated with Google Cloud Dataproc to provide a full big data analytics platform, or other data sources such as spreadsheets in Google Drive and transactional cloud Bigtable databases. Insights obtained from BigQuery can be represented as spreadsheets, reports, and queries over very large datasets. Since BigQuery is serverless and storage and compute resources are decoupled, it is highly scalable and can use its compute engine to scale to tens of thousands of cores over the course of a few seconds in order to analyze queries in a parallel fashion over datasets that are gigabytes or petabytes in size. This is done by using the Google auto-scaling capabilities alongside high-performance data streaming ingestion from Google Cloud Storage in order to provide real-time analysis of data. BigQuery is also highly durable as it provides completely free data and compute mirroring across multiple geographic locations. The pricing plan for BigQuery is fixed for storage, with the first 10 gigabytes a month free and 2 cents a gigabyte per month over that. For queries, the first 1 terabyte per month is free, and then it costs $5 per terabyte per month over that. So some of the other capabilities of BigQuery include that it's fully managed. So because BigQuery is serverless, there is no need to set up VMs, storage, or clusters. All that is required to get going is to load data and to start running SQL statements. Due to this reason, the setup of BigQuery is extremely quick and all the resources are automatically deployed and scaled with no user input required. Low-level database administration is not required, as all of it is taken care under the hood by BigQuery. Since BigQuery auto-scales and incorporates high-performance streaming in order to ingest data from Google Cloud Storage or other sources, SQL queries across datasets gigabytes or petabytes in size can happen in near real time. BigQuery also supports a data transfer service to import external datasets from SaaS services such as YouTube and AdWords on a predefined and scheduled basis. Data from database management systems can also be easily accessed with the support of the ODBC and JDBC drivers in BigQuery. Since BigQuery is a cloud-based auto-scaling data warehouse, data is executed in parallel across multiple auto-scaled compute nodes in the cloud. Compute and storage resources are also decoupled, which offers the best performance and cost savings for a specific query. Some of the options for storage aside from the default Google Cloud Storage include Cloud Bigtables, Google Sheets, and Google Drive. Several ETL tools such as Informatica and Talend are supported in order to clean up data and make it easier to use within BigQuery. Business intelligence tools such as Tableau and Looker are also supported to allow business analysts to create reports and graphical dashboards using BigQuery analysis data. BigQuery is very secure, encrypting data both at rest and in transit, and data is auto-replicated across multiple geographical regions at no extra cost. And this is in order to improve availability and match the service level agreement of BigQuery, which is 99.9%. In this video, I'll describe the MapReduce programming model. MapReduce is a central part of Hadoop. It enables thousands of servers within a Hadoop cluster to scale and to process data in a parallel and distributed fashion. The use of MapReduce is perfect for long-running jobs or tasks such as transforming data into different formats, log analysis, and a combination of data from various external input sources. MapReduce is available in Python and Java versions and is open source, being maintained on GitHub. MapReduce is built on top of App Engine services for Google Cloud Platform, and it must be downloaded and then included in an application in order to use it. There are no costs for using MapReduce. The only costs are the standard ones for resource usage that an application would regularly incur, such as instance hours, Google Cloud storage usage, and network usage. As I mentioned in the previous slide, MapReduce is best used for long-running tasks, which may be too long for an individual task. These tasks can include log analysis, data transformations, data aggregation, and data export. With log file analysis, log files are constantly growing and can be gigabytes in size for a single web server. These files are too big to store in a relational database like MySQL. Instead, the log files can be stored in Hadoop HDFS storage or GCS or Google Cloud Storage for Google Cloud Dataproc. The log files can then be processed in parallel using MapReduce to gather important insights on the data. With data transformations, it is often a challenge to write programs which will take inputs from various sources and properly split the data into chunks and distribute or map data to servers across the cluster for analysis in a parallel fashion. With MapReduce, parallel processing, error checking, and distribution logic is hidden within the library so that mapping operations and parallel programming for data transformations becomes much easier. Similar to data transformations, large datasets can be quickly aggregated or reduced in a parallel fashion by MapReduce. An example of this may be the average cost of a share over the course of a month, or the maximum cost and the minimum cost of that share over the course of the month, and this could be calculated from daily stock price data. This reduced data from MapReduce could then be stored in HDFS or Google Cloud Storage. Since MapReduce jobs break up or map data into chunks across multiple nodes and then reduce or simplify the data for analysis, it becomes quick to export data back to a relational database, such as an SQL database. Analyzed data is exported in parallel by MapReduce, which speeds up the process. And this is done by actually exporting it in parallel and in different chunks of data, so it's all running in parallel and the export happens very quickly. So as I mentioned, in order to use MapReduce, a job needs to be created. There are two types of jobs: single-stage map jobs and multi-stage MapReduce jobs. A map job is the simpler of the two. It is composed of only one stage and can be used to process large data sets in parallel. Common use cases of map jobs are to delete data, migrate data, or backup data. There only needs to be one function defined for a map job, which takes an input and provides some sort of operation on the input in order to provide an output. The more complicated three-stage MapReduce job consists of map, shuffle, and reduce stages, which must be run in a serial fashion, meaning that one stage has to complete before the next can begin. The first map stage takes data in and transforms it into key-value pairs. The key-value pairs are then sorted in the shuffle stage with similar keys being paired. Finally, in the reduce stage, all items with the same key are processed in parallel at the same time in order for analysis. Computed data from one stage is stored temporarily in intermediate storage between each of the three stages. MapReduce jobs are very useful as they can compute all the values that use a common key, even in the case that direct access to the values is not possible because the key still hasn't been calculated. Both map and MapReduce jobs use sharding and slicing in order to allow parallel operations over large sets of data. Sharding, just as it sounds, takes input data and divides it into chunks or shards to be processed in parallel. This speeds up the amount of time it takes to finish a stage. All shard operations in a single stage must complete before the next stage can begin for a MapReduce job. In the map stage, a separate instance of the mapper class is responsible for each shard with its own reader for the input. In the reduce stage, a separate instance of the reducer class is responsible for its own shard of data with a separate writer for the output. Depending on the implementation of the output and input classes, the number of shards per stage can be different. Slicing is the actual data processing operations such as map, shuffle, and reduce done on a shard of data. Once data is in a shard, it is processed in sequence using the App Engine task queue at a rate of one task at a time for a given shard. In order to run a task, data is actually read from the shard and the map, shuffle, or reduce operations are then run on data. The data which is part of a task is referred to as a slice. The actual quantity of data within a slice can change depending on the speed that a function processes the input given to it. After a slice is processed, another task gets added to the queue in order to process another slice of data from the shard. These operations continue one at a time until the whole shard is processed. All tasks for all shards are put into a single task queue, and App Engine dynamically starts and stops instances of modules such as map, shuffle, and reduce in order to accommodate for the varying task loads present. With slicing, there is also increased fault tolerance because if an error occurs on a slice, only that slice needs to be rerun until it completes instead of having to rerun the entire shard of data. In this demo, I'll demonstrate the process of submitting multiple jobs with Dataproc. There are 4 ways to submit jobs to a Dataproc cluster. The first way is by using the Dataproc REST API job.submit request. The second way is by using Google Cloud SDK command line tools with the gcloud Dataproc job submit command. The third way is to log into the Google Cloud Platform Dataproc web dashboard and to submit jobs from there. The fourth and final way is by using SSH to get into a node in the cluster and then running a job on that node. So I'll start off by talking about the gcloud command and how we could use that to submit a job. So I'll open up my Google SDK command prompt. And I have a simple script in Python called hello-pyspark.py. So at the top here, I'm just importing PySpark. I'm getting the Spark context as SC, and I'm parallelizing IAM PySpark and just printing it out. So to submit this job to my Hadoop cluster, which I have running, if we take a look at it, you could see it's just a standard cluster. It has one master node and 2 worker nodes, and it's located in the region US East 1, and the cluster name is cluster-boris test. So if I open up my command prompt once again, I could use the gcloud dataproc job submit command, specifying the type of job, so it's PySpark, so I'll specify that, specifying the region with 2 dashes in front as US-East 1. If you don't specify it, it defaults to global, and if your cluster isn't in the global region, you could have issues. And then you want to specify -- cluster, so you want to specify the cluster name, which is cluster-boris test, and the name of the job you're submitting, so hello-pyspark.py. So I'll just hit enter to submit this job to the cluster, and I should be able to see in my command window the status of the job, and I'm expecting IAM PySpark to display before the job completes successfully, which will show that it's submitted and it's completed successfully. So we could see the status from yarn submitted application to the cluster. We see the stages going on down here, and we see IAM PySpark. So that's what we expected. It seems to be working. And if we scroll down, we could see that the state is done, and so on. Now we could also see the status of this job if we go back to our web dashboard under Dataproc jobs. We should be able to see all the jobs that executed, including the ones we started with gcloud. So we could see that this job succeeded. So now if I want to actually submit a job using the Google Cloud Platform, I could do this by clicking Submit Job up here. I'm going to want to specify my region, so I'll specify US East 1, my cluster as cluster-boris test. My job type, so I'll do a Spark job this time. I'll specify my class, so I'll just be using some demo Spark PI class, which is going to actually calculate the value of pi given the number of samples. So that's located by default in org.apache.spark.examples.spark.pi. So I'll just specify that as the main class. I'll specify arguments, so I want some number of samples. I could specify 1,000, for example, which is going to give me a sufficient number of examples to actually calculate pi very accurately. Next, I want to specify the jar file. So for the jar file, in this case, this is also installed by default when you install your Dataproc cluster on the main cluster node, and that's just under file : and then we have the 3 forward slashes for Hadoop, user lib spark example jars spark-examples.jar. So this is the jar that we need. We'll enter that as the jar files. Under the optional category here, we want to make sure we have the arguments, the main cluster jar defined. We don't have to specify any properties or labels, and max restarts per hour will just leave 1 to 10 and click submit. This is actually going to submit our job to the Dataproc cluster. We could see our job here and we could click on it. And if we specify line wrapping, it's going to wrap the lines, and under output, we'll be able to see the output of the job and whether or not it completed successfully. We should also be able to see the value of pi from our 1,000 samples once the job completes successfully. So we could see the stages running here. And once it's all done, we should be able to see pi, and we do get pi is roughly 3.14 and so on, which is pretty accurate, and it says job output is complete. We could also click on configuration to view the configuration of the job that we just ran to ensure that we had the right configuration. We could clone the job, which is a nice feature which basically just copies all the data into a new job, so it's easier to run a new job without having to re-enter all the data again. And if we go back to our jobs tabs, we see we now have 2 completed and succeeded jobs. Finally, the last way that I'm going to be talking about how to run a job on a Dataproc cluster is to SSH into the master node, and then we could run a job on that node. So if I go back to clusters, remember there's 2 ways to SSH. We could either SSH through gcloud, or we could do it through the web dashboard, which I'll do. I'll click on my cluster. I'll click on VM instances. I'll click on my cluster-boris test-m or my master node, and I'll click SSH here. So once I'm SSH'd into my node, I could actually launch the Spark command line, and I could do some jobs from there. So it's just connecting now. And once it's done, I'll be in the node and I'll be able to start. So here I am, I'm in my cluster-boris test-m, which is my master node. Next, what I'm going to be doing is I'm going to be entering the Spark shell with the spark-shell command. And then once I'm inside the Spark shell, I'm going to be running basically a command that's going to get a publicly accessible file, which is just called hello-world.py. It's a very simple hello world program for PySpark. And then I'm going to be running collect, and for each line, I'll be printing the line. So basically, I'll just be printing all the lines in that file. It's a very simple Spark job, and I'll be doing that directly on the master node. So I'll just copy that job over. And once I'm into the Spark command line, I could see Spark, welcome to Spark version 2.2.0. And under the scale up prompt, I'll just copy and paste my job here and hit enter, and I could see my stages. And once it's complete, I actually see the contents of that hello-world.py file. So just importing PySpark and simply just writing hello world and printing the words. So it's a very basic job, but that just gives you an idea how you could SSH onto the master node in a Dataproc cluster and actually execute a job in Spark. So that's it for this demo. In this demo, I just went over how to submit jobs to a Dataproc cluster. Now that we are all done our lessons, it is time to do some practice. In this exercise, you will describe the various Spark and Hadoop processes that can be performed with Dataproc, recognize the process of monitoring and logging Dataproc jobs, SSH into master and worker nodes in the Dataproc cluster, describe the process of compute and storage and benefits of its separation, define BigQuery and its benefits for large-scale analytics, and submit jobs with Google Cloud SDK command line tools. Now pause the video and perform the exercise, and I'll get back to my solution. So first of all, I'll start by describing the various Spark and Hadoop processes that can be performed with Dataproc. Since Dataproc is a managed Spark and Hadoop offering, it supports the usage of various open source tools for data processing, querying, streaming, and machine learning. Various job types can be submitted to Dataproc, including Hadoop, Spark, PySpark, Hive, SparkSQL, and Pig. Hadoop and Pig jobs can be used to process large data sets. Spark jobs can be used for streaming data, machine learning with the mlib library, and structured data processing jobs can be done with the Spark SQL job type. PySpark jobs can be written in Python to expose the Spark programming model to Python. Hive jobs provide data warehousing capabilities, which can be used to provide data summaries, analysis, and queries on large data sets. So next up, I'm going to recognize the process of monitoring and logging Dataproc jobs. So Dataproc jobs can be monitored through the Google Stackdriver monitoring utility. Stackdriver monitoring is a Google monitoring tool which takes in information and displays it in easy-to-understand formats such as dashboards, alerts, and charts for various cloud-powered applications. With Google Cloud Dataproc, Stackdriver takes in and stores analytics such as metadata, metrics, and events, which can then be analyzed to monitor the health, performance, and uptime of Google Cloud virtual machines in Dataproc clusters. When creating a Dataproc cluster by using the Google Cloud SDK gcloud Dataproc command, it is possible to enable Stackdriver by editing the properties. So what you want to do is you want to enable it because it's not enabled by default with the -- properties dataproc:/dataproc.monitoring.stackdriver.enable equals true. After Stackdriver is enabled for a Dataproc cluster, the next step would be to set up the monitoring group for that Dataproc cluster. The monitoring group name must share a prefix with the Cloud Dataproc cluster name. One easy way to make sure the name is appropriate is to name the monitoring group to the same name as the Cloud Dataproc cluster name. After the monitoring group is set up, data is sent from the Dataproc cluster VMs to Stackdriver and no further configuration is necessary. By logging into the Stackdriver web dashboard, it is possible to view various metrics such as health, performance, and uptime of the Dataproc cluster. So the next thing I'm going to do is I'm going to SSH into master and worker nodes in the Dataproc cluster. So I'll be doing this by using the Google Cloud SDK tools. So in the command prompt, I'm first going to SSH to my master. So just to show you what I have here, I have a cluster defined with 2 worker nodes and 1 master node. If I click on the cluster, I could go to VM instances and cluster-boris-test-m is my master node. I could click on that. And I could get the zone, which is US East 1B, and I know the name cluster-boris-test-m. So if I open up my command prompt here, I could use the gcloud compute ssh -- zone and enter US East 1 -B and enter the cluster as cluster - Boris test M. If I hit enter, it's going to launch my SSH client. So since in Windows 10 I'm using PuTTY, it's going to launch PuTTY and it's going to SSH into my master node. I could do a similar thing into the master node from the actual web dashboard, or I could SSH into a worker node. So if I go to my first worker node, which is called cluster - Boris test - W - 0, I could click on that node and I could click on SSH here under that instance, and it's actually going to SSH to the VM of the worker node, and I'll be able to access it from the web dashboard just like I did from the gcloud command prompt, which I installed through the Google SDK tools. So here it is. We are now SSH successfully into our worker 0 node. So the next thing I'm going to do is I'm going to go back to the slides and I'm going to talk about the process of compute and storage and the separation and the benefits of separating compute and storage. So Dataproc compute and storage resources are separate in the cloud Dataproc architecture, with Google Compute virtual machines providing compute resources and Google Cloud file storage resources being used to store files instead of the standard Hadoop HDFS file system. Due to the speed increases, Dataproc allows clusters to be deployed on demand to complete a single job. This also makes management and troubleshooting easier, as there is only one job per cluster and no resource contention is experienced. So in traditional bare metal Hadoop clusters, upgrading storage, which is IOPS or capacity, had to be done linearly with upgrading compute resources such as RAM and CPU. So this often resulted in overpaying because you didn't always have to increase storage when you increased compute resources. And that's what we could see with the first graph. It's going linear because whenever we're increasing compute, we're also increasing storage. So by using VMs and separating compute from storage in a virtualized environment, compute resources can now grow independently from storage resources, depending on the cluster requirements, and this results in cost savings. So if we look at the graph to the right, as storage goes up, compute goes up to a certain point, but then when it gets to $2 signs, we see, oh, we have enough compute resources. We need more storage, but compute is staying where it is, and that results in cost savings to the customer. So now I'm going to define BigQuery and its benefits for large-scale analytics. So BigQuery is a serverless, logical, big data enterprise data warehouse provided by the Google Cloud Platform. Its focus is on data analysis on large data sets, and it supports SQL queries to analyze data. Insights obtained from BigQuery can be represented as spreadsheets, reports, and queries over very large data sets. BigQuery is serverless and is highly scalable and can use its compute engine to scale to tens of thousands of cores in a few seconds in order to analyze data which is up to gigabytes or petabytes in size in a real-time fashion. The pricing plan for BigQuery is fixed for storage, with the first 10 gigabytes a month free and then 2 cents per gigabyte per month over that. For queries, the first 1 terabyte per month is free, and then it costs $5 per terabyte per month over that. So some are the other capabilities of BigQuery. It's fully managed because BigQuery is serverless. There's no need to set up VM storage or clusters. It sets up very rapidly. And like I mentioned, the SQL queries are extremely fast because of the way it's designed and the way it scales almost instantaneously. It also supports ODBC and JDBC drivers, which could be used to integrate to other relational databases. Like I said, limitless scalability, and it has parallel execution because it's all virtualized. And since compute and storage are separate, we have some performance optimizations as well. And we do have flexible storage options. So aside from the default Google Cloud Storage, we also support Cloud Bigtables, Google Sheets, and Google Drive. And several ETL tools such as Informatica and Talend are supported as well. And business intelligence tools such as Tableau and Looker are also supported. It is also very highly available and very fault tolerant, so it's very secure because BigQuery encrypts data both at rest and in transit, and it also replicates data across multiple geographical regions. So finally, the last thing I'm going to talk about is submitting jobs with Google Cloud SDK command line tools. So as I mentioned in a previous video, the Google Cloud SDK command line tools, gcloud Dataproc job submit command can be used to submit jobs to Dataproc. So let's go open up just the command prompt here. And what I'm going to be doing is I'm going to be submitting a command. So I actually have a script called hello PySpark.py. And we could just take a look at it. It's a simple, basically hello world script that just says I am PySpark. It's written in PySpark, which interfaces with the Spark programming model with Python. So what I could do is I could actually run the gcloud dataproc job submit PySpark. I'll specify the region as the region of my cluster, US East 1, and the cluster name as cluster Boris test, and I'll send in the job as hello PySpark.py. So it's a type PySpark job, and I'm specifying that. And actually, when I run it, I'll be able to see the results in the command window, but I'll also be able to open up my Google Cloud dashboard and actually see the job and make sure it executed properly. So we could see the state is done. And if we scroll up here, we see I am PySpark. So the job executed successfully. Just to take another look at it, we could actually go back to our cluster. If we go under Google Cloud Platform and we click on Dataproc, we could click on jobs and we should be able to see the job update. So it just ran now at 5:29 p.m. It lasted 33 seconds. I could click on the job and I could look at the output and I could see I am PySpark appears here as well. So that's another way we could take a look at the jobs. So that's it for our exercise. Just to go over what we talked about in this one. We just covered describing the various Spark and Hadoop processes that can be performed with Dataproc. Then we recognize this the process of monitoring, logging Dataproc jobs. And then we SSH'd into master and worker nodes in the Dataproc cluster. Then we described the process of compute and storage and benefits of its separation. We defined BigQuery and its benefits for large-scale analytics. And finally, we submitted jobs with Google Cloud SDK command line tools to a Dataproc cluster. In this video, I'll describe the use of functions, operators, and data types with BigQuery. The first thing I'll talk about is BigQuery operators. An operator is an arithmetic function that takes in at least two, but often more inputs or operands in order to manipulate them and return a desired output or result. Operators in BigQuery do not use a function call for their operations. They are instead grouped with special symbols and keywords such as a plus sign for addition and not for logical not operation. Operators in BigQuery will output null if any of the operand inputs are null. If an arithmetic operation overflows, an error will be returned instead of displaying a false result. By default, an error is returned if an operator computes infinity. Infinity may only be returned by an operator if one of the operands is infinity. Arrays and structs are supported data structures in BigQuery. An array is accessed with an integer index inserted between the brackets, which acts as an offset to access the array element. Struct member elements can be accessed by the use of a dot. The standard symbols for arithmetic, which are plus, minus, division, and multiplication, are all available in BigQuery. Logical operators supported in BigQuery consist of not, and or. Bitwise operators are also supported, such as the bitwise not, or, XOR, and, as well as bitwise left and right shift. Or, XOR, and bitwise operators only work on operands with the same number of bits. Comparable data types can be compared using equal, less than, greater than or equal to, less than or equal to. And there's two ways of doing not equal. You could either do A is exclamation mark equals sign not equal to B, or A, and then you could use the opposite arrows for not equal to B. There's two others. We'll talk about the in operator. So the in operator returns a Boolean value of true or false and can be used to compare whether a certain value is in an array or list of values. It can also be used with a not to see if a value is not in a list of values. The is operator can be used to see if a value is null, true, or false, or a certain value. It returns a Boolean of true or false, just like the in operator, depending on if the comparison succeeds or fails. Next, I will talk about BigQuery functions. BigQuery functions have call rules which are applied to all functions. The first rule is that if one operand is of the floating point type and the other is some other numerical type, both operands get changed to a float64 type for the function to execute. The second rule is that except for the case with the is operator, if one of the operands is null, the function result is always null. And the third rule is if no time zone is set in a time-sensitive function, the default time zone is UTC or Coordinated Universal Time. With operand conversions, casting is explicit in BigQuery, and that means that we have to use the cast function whenever we cast a value explicitly. So here we could say cast a equal to 0 as bool. Coercion, on the other hand, happens automatically in BigQuery. So an example of this may be if a float64 type is required as a function operand and an int64 type is computed, then BigQuery will automatically use coercion to pass a float64 type instead of an int64 type as the function operand for the function to execute. So the following data types are supported in BigQuery. So we have int64, float64, string, bytes, bool, date, time, struct, and array, as we talked about for the data structures. There are various aggregate functions supported in BigQuery, and here they are listed here. So for example, any value returns any value from a list of inputs and null if no inputs are given. This value can change every time the function is invoked. Average and sum return the sum and average of a list of numbers. COUNTIF displays the number of values that are true from a certain input condition. There could be, for example, a list of numbers, and if we only wanted the number of numbers in that list above 10, we could use COUNTIF, in brackets put x is greater than 10, and then we'd get the number like 5. Numbers in the list are greater than 10. Max and min return the maximum and minimum of a list of numbers. Logical AND runs on a list of non-null inputs and returns a Boolean result of the aggregate of ANDing all the expressions together. So we could have like true, false, true, and if we ANDed all of that together, we would still get false as the result. We also have some statistical functions, and they could be used to find the standard deviation and variance of a list of numbers. We could also find correlation, which is between -1 and 1 from a list of number pairs by using the core function and passing in the list of number pairs. So we have analytical functions which can be used to calculate the aggregate value of each individual row in a group of rows, and mathematical functions that can be used to find the log, square root, absolute value, random value, and so on. Hashing functions are also supported, and the types include MD5, SHA1, SHA256, and SHA512. Date functions are also available, and the date and datetime functions can be used to construct either date or datetime objects. The current time function returns a time object which displays the current time. There are many string functions available, some of which include char_length, which shows the length of a string using characters. The format function to format strings in a C printf-like fashion, replace to replace parts of a string, and repeat to repeat a value multiple times in a string. There are also several array functions available, including generate array to create and display an array using a start value, end value, and step size, and array length to display the number of elements within an array. In this demo, I'll define the steps to install a storage connector. The Google Cloud Storage Connector is by default installed on all new Dataproc clusters. Its main job is to allow Hadoop and Spark jobs to run directly on data stored in Google Cloud Storage, which has several benefits such as speed and data replication, accessibility, and availability compared to using data stored in traditional on-premise Hadoop distributed file storage or HDFS. Along with Hadoop, the Google Cloud Storage Connector is usable with both Spark and PySpark operating environments. Data stored in Google Cloud Storage can be accessed with the gs:// prefix from Spark, PySpark, or Hadoop. It can also be accessed from the Google Cloud Platform Online Storage Console, the Hadoop shell, and from the gsutil rsync and cp commands. In this demo, I'll be going over how to install the storage connector. So some of the use cases for this is if you have an on-premise Hadoop cluster with HDFS storage and you want to move your data to the cloud. The steps of the installation are to download the Cloud Storage Connector, to set up the Google Service Account key credentials, and then to update the conf/core-site.xml file on the master node and all the worker nodes. So let's get started. Here in the Google Cloud Platform, I currently have just one cluster called cluster-borsttest, and it just has one master node initialized. I'm going to go to Linux, and as you could see, I've actually logged in to my Boris test master node. And the first step is to actually go ahead and download the Cloud Storage Connector from the Google Cloud Platform steps to install the Cloud Storage Connector webpage. So since I have Hadoop 2 installed, I could download the jar file by clicking on this link. Now I've already downloaded it and uploaded it to my cluster. And what you're going to want to do is you're going to want to upload it to a directory that contains all your Hadoop jar files, and this is in my user lib Hadoop lib directory. So if I do an ls and I do a grep on connector, I should see that I have my GCS connector latest hadoop2.jar. So that's as expected. Next, I actually want to go ahead and I want to update some of my environment variables. So that's in the etc Hadoop conf directory. And in this directory, I want to open up the file called hadoop-env.sh. So within this file, I'm going to want to update the environment variable for the Hadoop class path. So I'm going to update it with the location of the GCS connector dash latest file, so I could see it's in the user lib Hadoop lib. And then I have GCS dash connector dash latest dash hadoop2.jar. So once that's updated, I could write it and exit that file. And now we could move on to step 2 to set up the service account key file authentication. So that's done through the Google Cloud Platform. Under credentials, I could click on create credentials. And I'm going to want to click on service account key. And once those options come up, I'm going to want to select the service account as the compute engine default service account and the key type as JSON and hit create. I'm going to want to save my key, and then I'm going to want to upload it to all the nodes in my cluster. So I've already went ahead and done this, and I'm just going to go back to my master node now. So within my master node, I could actually go ahead and take a look in my conf directory, and I'm going to have a key here, which I copied from my home directory. So let's take a look at the home directory first. If I look at my home directory, I have a Boris test project key, and it ends with .json. So that's for my current project. Because my project's called Boris test project, that's how the key was named. And I've copied that key and renamed it to gcskey.json inside my etc Hadoop config directory. So now what I'm going to want to do is I'm going to want to edit a file, which is called the core-site.xml, and I'm going to want to do this on all my nodes in my cluster. Now, since my master node is my only node, it's the only node that I'll have to worry about. So I'm going to open up that file. And within that file, there's 3 things I want to edit. So the first thing I'm going to want to do is I'm going to want to add a property, and the name of the property is google.cloud.auths.service.account.json.keyfile. And I'm going to want to specify the full path of that file. So once again, it's in the etc Hadoop/conf directory, and it's called gcskey.json. So once that's done, the next thing I'm going to want to do is I'm going to want to specify my project and my GCS location. So if I scroll down, I'm going to want to find my bucket. So I'm going to want to see that I have a system bucket, and I have a default bucket configured for this Dataproc project. So it's called fs.gs.system.bucket is the name of the property. And the actual bucket is called Dataproc-5c and so on. So I'm going to want to copy this bucket name because I could actually do a query on it once this is all set up to make sure it's working. Now, once that's done, the last thing I'm going to want to do inside this config file is I'm going to want to make sure that my project is set. So I'm just going to search for project here. And I want to set the property fs.gs.project.id, and I want to make sure it's set to the project that my cluster is going to be using for my GCS bucket, which it is in this case, it's boris-test-project as the value. So once that's all done, I could write the file, exit, and now I could go ahead and I could actually test what I did. So in order to test it, what I'm going to do is I'm just going to run a command here with the Hadoop fs-ls, and I'll specify this bucket that I specified inside my config file. So that's the Dataproc-5c and so on bucket. To access any buckets in Google Cloud Storage, I'm going to want to specify gs://. So if I go ahead and I execute that command, I should see the contents of that bucket. And if I do, that means that I successfully initialized the storage connector. So let's see what it says. So I see that I have an image, and I could see the image as a JPEG. And I could also see I have two directories. I have a directory called meta info and I have a directory called notebooks, all within that bucket. So it looks like it's working. It looks like I have initialized the connector correctly from my Dataproc master node. Now, once again, I didn't have to do this for Dataproc because it's initialized by default. This would be more helpful if I was actually doing it on a bare metal on-premise HDFS-based Hadoop cluster and I wanted to move my data to the cloud. In this demo, I'll identify steps to load data with BigQuery. In a lot of cases, it is possible to use BigQuery to query data without the need to load it. Examples of this is when using public, shared, or external datasets or Stackdriver log files. For other cases, it is imperative to load data before it can be used for queries in BigQuery. Data can be loaded from a number of sources, including Google Cloud Storage, local machine files, Google Drive, and the Google Cloud Bigtable URI. Currently, the loading of data from Google Drive is not quite yet supported. However, it is possible to query Google Drive data by using an external table in BigQuery. The schema used when loading a table into BigQuery can either be specified or automatic, in which case it is auto-detected. You can either add data to an existing table or create a completely new table when loading data. The default format of loadable data is BigQuery is CSV. The acceptable formats of loadable data include CSV, JSON, Avro, Parquet, and Google Cloud Storage Cloud Data Store backups. The encoding format supported by default is UTF-8, although ISO-8859-1 is also supported for flat data-only CSV files. For compressed files, the Avro format is the recommended file type for loading. That being said, BigQuery works better with the loading of non-compressed files as they can be loaded in a parallel fashion. So let's get started. Here I am in the BigQuery dashboard under https://bigquery.cloud.google.com. I could see I'm in my Boris test project, which also happens to be the project I have in my Google Cloud platform. What I'm going to want to do beside Boris test project is click the downwards arrow and click on create new dataset. I'll give this dataset a name, my first data set 1. And I'm going to pick the data location as unspecified and data expiration as never and hit OK to create the dataset. Now you can see we also have some public data and we have public data sets. For example, if we click on this NYC-TLC green, we could click on trips 2014 and that'll actually bring up a table, which I believe is just some taxi trips from New York cabs. And it's quite a big table and it's a public data set. However, if we actually want to import our own data, for example, from a Google Cloud Storage bucket or from our local computer, we could do that by clicking the plus sign beside my first dataset 1 to create a new table. I'm going to pick the source data. There's two options, create empty table or create from source. I'll pick create from source because I want to import some data into BigQuery. I'm going to select the location as Google Cloud Storage, and I'm going to specify a Google Cloud Storage bucket. Remember, it always starts with // and my bucket, I'll go to all my buckets here in my storage browser in the Google Cloud Platform dashboard. I could see I have a bucket called testdata-boris. I'll click on that. And inside that, I have a file called test.csv, which I want to import into BigQuery. So let's specify testdata-boris and then /test.csv for the file. So once that's specified, we're going to leave the default file format as CSV. We could also select JSON, Avro, Parquet, or Cloud Data Store Backup, but I'll just leave it as CSV. The table name, I'll call it schedules. It'll be a native table, and I'll auto-detect the schema by selecting automatically detect, and I'll hit create table to create the table. Now we'll get taken to a window where we actually look at the jobs, where we're actually loading the data. Once the check mark appears, it means that it's loaded successfully. I could see my schedules tables created. I could click on it, and under preview, I could take a look at what the table contains. And basically what it is it's just a bunch of baseball schedules and the different dates, attendances, statuses, and so on for the baseball schedules. So I could go ahead, if I click here, I could delete the table. And now what I'm going to do is I'm going to be creating the same table, but just from locally imported data. So what I'm going to do is, once again, I'll hit on new table with the plus sign beside my first data set 1. I'll select create from source for source data. The location I'll select as file upload and I'll click choose file. Under downloads, I'll select test.csv. and it shows me the size, file format CSV. I'll just call it schedules once again. Schema, I'll select auto detect and I'll hit create table. Now this should import it and upload it from my local computer into BigQuery. I could see the load. Once the load is complete, I could click on schedules and I could take a look. It should be the same table as Google Cloud Storage, but now I just uploaded from my local computer. So that's how you could go about loading data with BigQuery. In this demo, I will identify the steps to export and update data with BigQuery. Updating and deleting data in tables in BigQuery can be done through DML or the data manipulation language. DML query statements written in BigQuery are written in standard SQL. The first step before a table can be updated is to import the data and to create a new table, as I demoed in the previous video. Data can also be exported from BigQuery to Google Cloud Storage. Up to 1 GB of data can be exported per each individual file stored in Google Cloud Storage. Data sets larger than 1 GB can be exported into multiple files to Google Cloud Storage bucket by using a wildcard option when exporting. The export operation can be started either from the BigQuery web user interface, command line, or REST API. The proper reader permissions need to be available for the BigQuery data, and the proper writer permissions need to be set on Google Cloud Storage buckets for the export operation to work. Some limitations with exporting include that you can only export a single table at a time, you can't export nested CSV data, and that integer data is stored in the JSON format string when exported. The formats supported for export are CSV, JSON, and Avro. gzip compression is also available for BigQuery data exports, although the default is to export with no compression, and the Avro format does not allow compression. So let's get started. The first thing I'm going to talk about is updating. So here I am in my BigQuery web dashboard. I have a table in my dataset called my first dataset, and the table is called schedule. And it basically contains data that I used in the previous demo containing various baseball games and the times and the teams and so on. I'm going to click on compose a query to compose a query against that table. I'm going to click on show options first and uncheck use legacy SQL because we want to use standard SQL for DML statements. So what I'm going to be doing is I'm going to be inserting a row into my table. And I'm just going to copy that over. So insert, I'm going to specify my dataset, my first dataset 1.schedule for my table. I'll pass in all the different columns I want to update: game ID, game number, season ID, year, day, night, and duration, and my values. If I click on run query, I'm actually going to run the query, and I should see a green check mark when it's done. And once the query is done, I could actually close this, go back to my table, and hit preview. And if I go to my last page of my table, I should see my new row appears at the bottom, which it does. So I'm going to compose another query. So every time you open this, you have to uncheck the use legacy SQL. And this query is just going to update a column in the table. So I'm going to be changing all the places where the home team name is set to Mets to Blue Jays. And basically, once again, I'm just going to specify update the data set, the table name, and then set home team name equal replace home team name Mets and Blue Jays where true. So if I run this query, I could run it, and then I could run a select statement to make sure that there are no Mets left inside my table. So I'm just going to select from my table, I'll select everything, and I'm going to query for Mets. And I should see that there are no Mets for the home team name. So if I run this query, and I should get the green check mark once it passes, and if I go down here, it says query returns 0 records. Okay, so let's do another operation. So now I'm going to delete from the table. So I'm going to delete basically any row where the home team name is Blue Jays or the home team name is Cubs. So I'll just copy that over and paste it in, and I'll run the query. And once that's done, I could do a select statement, and I'll just make sure that I have no home team names that contain Cubs or Blue Jays. So I'm selecting everything from the dataset.schedule, where home team name is equal to Blue Jays or home team name is equal to Cubs, and that should return an empty query because I just deleted all the rows that contain Cubs and Blue Jays, and it does say query returned 0 records. So that's as expected. So let's say now we want to export the table. So if I go to the schedule table and I right click on this downwards arrow and I click on export table, I could export it to Google Cloud Storage. The default export format is CSV. I'll leave that. We could also select JSON or Avro. And gzip is off by default. If I want to select it, I could click on gzip, but I'll select it to none. So have no compression at the moment. So the export format is CSV. We're not using any compression. The next thing we want to find is the Google Cloud Storage URI. So I'll open up my Google Cloud Platform web dashboard, and I have a bucket called test data -Boris. So I'll be using that bucket. And I'll call my file schedule.csv. And I'll be saving it in the test data -Boris bucket. I'll hit OK to export it. And I should see it if I go into my test data Boris bucket. I should see that I have schedule.csv exported, and it is there. So that's how we could go about an export from the BigQuery web dashboard. In this demo, I will describe the various processes using Google Notebooks with Datalab. Google Cloud Datalab is built on top of Jupyter Notebook, and it is a Google Cloud Platform service that can be used to analyze and transform data, as well as to construct machine learning models. Datalab also adds some extra features to Jupyter Notebook, such as integration with BigQuery, SQL queries, as well as quick operations with Google Cloud Storage. To install Datalab, we could use the gcloud space component space install space Datalab command, which will install Datalab and the required libraries. To create a Datalab instance, we want to type Datalab space create space VM instance name. In order to do this, we must also enable the Cloud Source Repository API for the project in use in the Google Cloud Platform web dashboard. Once the instance is created, a remote Cloud Source Git repository gets created from the repository located in the VM container containing the Cloud Datalab instance. The Datalab VM local repository can be managed by either using SSH to get into the Datalab Cloud VM and command line git, or by using un-git from the web browser. Once a notebook is added or updated to the local repository, it can be pushed to the remote Cloud Source Git repository using either git or un-git. To connect from the Google Cloud Shell terminal, you can use the command datalab space connect space VM instance name. You then want to click the web preview icon and change the port to 8081 to open up a new tab containing Datalab. So the first thing we could do is we would install Datalab. So from our Google Cloud SDK shell, we would run the gcloud space component space install space Datalab. No, I've already went ahead and done this. It does take about 10 minutes. So just for the sake of time, I'm going to move on to the actual part where I create a notebook or a Datalab instance. So what I'm going to be doing is that I'll be using the Datalab command, Datalab space create, and then I'm going to give the VM instance name. So I'm going to call it test instance and space. Now this is also going to take a few minutes because it's first going to create the remote repository and then instantiate the storage, and then it's going to launch a VM with the Google Compute Engine to actually run our instance. So now that our Datalab instance is created, we could issue the Datalab list command. And that command is simply going to tell us all the Datalab VMs that have been spun up, and we should see the one that we just launched in that list. And then we could go to our Google Cloud Platform web dashboard and actually connect to it. So we could see we have two Datalab instances. We have our test instance at the bottom, the one we launched, and we see the machine type, the IP addresses, and the status if it's running or not. So let's go to our Google Cloud Platform web dashboard, and under the repositories tab, we could see we have our Datalab notebooks. So this is that repository I was telling you about, that remote Cloud Source Git repository that got created when we created the notebook. So now we're going to want to actually connect to our test instance. So we could issue the Datalab connect test instance command, and this is once again under our Cloud Shell, which is available by pressing this button here at the top with the arrow and the terminal. So that would launch the terminal in our web browser. We could issue the Datalab connect space test -instance command. And if we hit enter, it's actually going to connect. And what we're going to have to do is we're going to have to change the port settings in order to use port 8081, and then we could actually connect to Datalab in the new tab in the web dashboard. So it's saying waiting for Datalab to be reachable at HTTP localhost 8081. So now we want to hit web preview, and we want to change the port, and we want to put port number 8081 and change in preview, and that's going to open up a new tab with Google Cloud Datalab. Now we want to create a notebook, so we could go under our notebooks directory, and we do have some sample notebooks as well, but if we want to create a new one and push it to the remote repository, we'll create a new notebook by hitting the plus sign to add a new notebook under our Datalab notebooks directory. Inside this notebook, I'll just have a very simple, basically hello world program. So print hello, this is notebook 1. And we could give it a different name. So I'm going to call it notebook 1 and hit OK. And then we could actually execute the notebook by hitting run up here. We could see what happens. Once the notebook is run, we should just get that statement. So hello, this is notebook 1. Now we could click down on the notebook arrow and we could click save and checkpoint. And once that's done, we could go to UN-Git by pressing this branch button at the top here. And that's going to open UN-Git on the notebooks repository. So I'll click that and open it up. And once again, we could also do this by SSHing into the instance and actually using Git from the command line. But UN-Git is the way we could do it from the browser. So now we want to enter a commit for our notebook 1. I'll call it first notebook. And the body, I'll just call it first notebook. And I'll hit commit. And once that's committed, I could actually click on the master branch and I could push it to my remote repository. And once it's pushed in the remote repository, I could go back to my Google Cloud Platform under my repositories and I could click on Datalab Notebooks. And inside there, I should see that I have my notebook 1 first notebook. I could click on it and take a look at it. And we could see that I have my text here. Hello, this is notebook 1. So that's how we could go ahead and actually install Datalab, start a new instance, create a notebook, and push it to a remote repository. In this demo, I'll describe the steps to use Jupyter Notebooks with Google Cloud Dataproc. In the previous demo, I went over how you can use Google Cloud Datalab, which is a data analysis tool based on the Jupyter Notebook. In the case that we would like to use a notebook that more easily works with Apache Spark, it is more efficient to use Jupyter Notebook deployed with Google Cloud Dataproc. The setup process can be completed in 4 steps. The first step is to launch a new Dataproc cluster with initialization actions to install Jupyter. The second step is to connect to the Jupyter Notebook via an SSH tunnel. And the third step is to add a new notebook and set up the libraries to download for the Jupyter Notebook. And finally, the fourth step is to run queries and view the results. So let's get started. Here in the Google Cloud Platform web dashboard, if I click Create a Cluster, I could give the cluster a name, a region, and so on. And as I showed in a previous demo, if I click on this tab here that says Preemptible Workers, Buckets, Network, Version, Initialization, and Access Options, I could scroll down and under Initialization Actions, I would add the Jupyter install script. So that's located in the Google Cloud Storage. It's a public script, so gs:// Dataproc initialization actions /Jupyter/Jupyter.sh. So this script, if we actually created the cluster, I already did it for the sake of time, would basically install Jupyter on our Dataproc cluster. Now, once Jupyter is installed, it's time to go to step 2. So I'm going to open up my Ubuntu installation. And what I did was I used the gcloud compute SSH command, and I specified the zone as US-West1-C, which is the zone my Dataproc cluster is in, and the cluster name, cluster-bors test. And I specified the --D port 1080 for the SOCKS 5 protocol for the proxy, and then I specified -N and -N. Then in another command prompt, what I did was I ran the command user /bin /Firefox to get the Firefox executable. I did --proxy-server socks5 ://localhost 1080. So I'm basically saying that anything that comes in to localhost 1080 is going through the SOCKS5 protocol, and I'm excluding localhost, and I'm opening up a new window by specifying an empty directory for the user -data-dir. So that's how we could create an SSH tunnel, and a new Firefox browser will open and we'll have the SOCKS5 proxy active. Once that Firefox portal is opened, I could go to cluster-boris-test-m, which is the master node of my cluster that I just deployed. And I could specify :8123 for the port, and that's going to get me to Jupyter Notebook. So what I want to do now is Jupyter Notebook should be installed by default because we did specify that initialization script. So now what I could do is I could click New, and I want to select PySpark to create a new Jupyter Notebook. And then what I'm going to be doing is the first thing is I'll be going into the cell and I'll just be importing some of the libraries that I want. So if I open up my libraries here, I'm going to use pip install, and I'm going to upgrade, basically install and upgrade all these libraries. So pandas, the Google-API-Python-client, Seaborn, and pandas GBQ, which we'll be using to load data in from Google BigQuery for analysis of taxi data. So if we paste that in and then we just run the cell, the next thing we're going to want to do after all the libraries get installed is that we're actually going to want to go in and we're going to want to import all of these libraries. So I'm going to be importing pandas as PD, importing Seaborn as SNS. I'm going to be importing matplotlib.pyplot as plot because I'll be plotting the taxi data. I'll be plotting the taxi costs versus the time of day. I'll be importing numpy as MP and importing pandas GBQ as GBQ. So I'll paste this into another cell in my Jupyter Notebook that I just created. And I'll execute this cell as well by hitting run. After that, I'm going to want to set my project. So I want to set a project that has access to BigQuery because once again, I'll be getting the taxi data from the New York City Taxi Department, which is publicly available in BigQuery. So I'm going to set the project ID to a project ID that has access to BigQuery, which is Boris-test-project in my case. So I'm going to paste that into another cell and run that. Now, once that's executed, I could actually go ahead and get to the bread and butter. So I'll be selecting a formula. I'll be creating a formula, and I'll be selecting data from the taxi data in BigQuery. And I'll basically be calculating different quantiles. So let's take a look at it. So I have quantiles equals select. So I'm selecting the pickup hour. I'm dividing it into the quantiles of 50th, 75th, and 90th percentiles. I'm selecting the pickup hour, and I'm approximating the quantiles for the fare amount. So basically, I'm going to be comparing the pickup hour to when the passenger was picked up to the fare they paid, and I'm going to divide it into the three quantiles, 50%, 75%, and 90%. And I'm getting that from the New York City-tlc.yellow.trips, which is a publicly available table in BigQuery, and I'm grouping by pickup hour. And here you could see trips equals gbq.read_gbq. So I'm actually reading from BigQuery. I'm querying the quantiles dialect standard, and I'm specifying my project ID, which has access to BigQuery. And then I'm just going to write the first few trips here, trips.head. So if I run this, it's actually going to run and retrieve 24 rows. And I could see that I have my pickup hour, my 50th, my 75th, and my 90th percentile quantile. So now what I could do is I could scroll down in here, and I'm actually going to plot this as a line chart just to take a look at it. So I'm going to paste this in, and what I'm going to be doing is matplotlib inline plot.figure. The data is going to be trips.set_index. I'm setting it by pickup hour. It's a line plot and it's not stacked. So I should be able to see the three different quantiles versus the pickup hour if I do run on this cell. here in my Jupyter notebook, I could see that, for example, at 5 a.m., the price spiked, so my 98 quantile went all the way up to $30, whereas I could see I have a low around probably around 6 or 7 p.m. where it was only about $17 or $18, so I could compare my data in my Jupyter notebook, and that's just how we could use the Jupyter notebook with Spark and import data from Google BigQuery. In this video, I'll identify the proper storage options with Google Cloud Storage. There are various Google Storage products available to meet different storage needs. Storage options such as Bigtable, BigQuery, Cloud SQL, and Cloud Data Store, as well as Cloud Spammer, are available for structured data. Google Cloud Storage is available for unstructured data. Cloud Storage for Firebase is available for mobile data. Structured data storage options can be further broken down. If you need low latency analytics storage, you would use Bigtable storage. For analytics that don't require such a low latency, BigQuery would be a good choice. For relational structured data that requires horizontal global scalability, Cloud Spanner would be a good storage option. For MySQL or PostgreSQL data, Cloud SQL would be the option to choose. Cloud Data Store would be used for storing partially structured NoSQL data. So the first storage option I'm going to talk about is Google Cloud Storage. This is the default fully managed storage type for unstructured data such as blobs, pictures, videos, and objects which are stored in cloud storage containers called buckets. Cloud storage is highly reliable and scalable and is geo-replicated across multiple data centers around the world. Because of this, availability for Google Cloud Storage is 99.95% for multi-regional storage and 99.9% for regional storage options. Due to its pay-per-use structure, there is no base cost to get started, and you only pay for the data that you actually store on a monthly basis. Google Cloud Storage is best for workloads involving storing and streaming multimedia such as video files, backup and disaster recovery, as well as customs analytics data storage. Next, I'll talk about Google Cloud Data Store. Google Cloud Data Store is a fully managed and very scalable NoSQL data store used to store partially structured non-relational mobile and web data, such as user profiles or saving the game state when the game is paused. Sharding and data replication is automatically implemented so that scalability can occur on its own and extremely quickly to match any load level required, and availability will still remain high. Data Store provides a REST API for easier interactions with data across various compute engine VM instances. Data is stored in a key value format, and there is a capable query engine which allows querying over multiple properties and sorting data with ease. Just like Google Cloud Storage, there is no baseline cost. You only pay on a per month basis on the data you store and the reads, writes, and deletes you do on the data. Next up, I'll talk about Google Cloud SQL. So Google Cloud SQL is a fully managed MySQL and PostgreSQL storage solution for storing structured relational data such as website and blog data, content management system data such as WordPress and e-commerce websites, business intelligence data, and geospatial data. Cloud SQL provides database services for applications across the internet at a high availability of at least 99.95%. Scalability is done automatically, and an instance can scale up to 10 terabytes of storage, 416 gigabytes of RAM, or 40,000 I/O ops to handle high loads. Due to this reason, performance is very high, and Cloud SQL is perfect for OLTP transactions and queries using various web frameworks. Cloud SQL billing is similar to Google Compute Engine billing, with no upfront costs, and occurs on a second-by-second basis for the Cloud SQL instance as well as the storage space used. Next up, I'll talk about Google BigQuery. Google BigQuery is a fully managed data warehouse that supports SQL queries that can be used for big data processing and analytics, as well as complex big data insights and integration with AI and machine learning tools, which is also available. BigQuery is serverless and extremely fast because it uses automatic compute scaling and fast streaming ingestion for data in order to load huge datasets up to petabits in size in just a few seconds. BigQuery integration is easy due to the JDBC and ODBC driver support, as well as the support of standard SQL for queries. Data can also be loaded from various sources such as Google Cloud Storage, Google Drive, and Google Bigtable. BigQuery is extremely secure, and it encrypts all data, whether it's at rest or moving between different data stores, and it provides an SLA of 99.9%. BigQuery is priced monthly with 10 gigabytes of storage and 1 terabyte of queries per month provided at no cost. So some other types of storage options, we have persistent disk or block storage, which can be used for virtual machine disks, containers, and VM snapshots. Google Cloud Spanner, so this is used for high reliability applications, such as financial transactions with global scale and high availability requirements that happen in real time. Google Cloud Bigtable, which is a NoSQL database for high throughput, low latency, real-time big data analysis. Google Drive for storing, sharing, editing various documents, and backing up photos and videos. And we also have Firebase storage, which Google provides cloud storage capabilities for mobile apps, photos, videos, and more. Firebase provides a highly secure and robust storage API for various Android, iOS, or web applications that can transfer files over slow or unreliable connections to Google Cloud Storage, which can then scale to petabytes of data in matters of seconds. Firebase also connects with Google Analytics, and it helps to analyze app usage and potential app improvements. In this demo, I will query data using Google Bigtable. Google Cloud BigQuery, which I went over in previous videos, can be used to query data which is located in Google Bigtable. Bigtable is Google's NoSQL database which can hold petabytes and billions of rows of data. It is low latency and is very good for use with MapReduce. Bigtable provides an Apache HBase client library and is very similar in its data structure to HBase. In order to query data from Bigtable, currently only the US Central 1B, US Central 1C, Europe West 1B, and Europe West 1C zones are supported. To query Bigtable data, reader permissions are needed for the dataset, and BigQuery.user permissions are required to execute queries on the project that contains the dataset. There are two ways to query Bigtable data from BigQuery. You can either create a permanent table in BigQuery from Bigtable, which can then be shared, or you can create a temporary table in BigQuery from Bigtable, which is not shared. Temporary tables are useful if you only need to do a single query on Bigtable data. So let's get started. The first step is we're going to want to go to the Google Cloud Platform. And under Bigtable for our project, we're going to want to click Create Instance. Here we're going to want to give the instance a name. We're going to want to give the instance an ID. And we're going to want to select Production or Development for the instance. Give the cluster ID and the zone. So for the zone, you either want to pick the US Central or the Europe West zones because those are the ones that currently support querying. The nodes, the storage type, and so on, and then you click Create to create the Bigtable cluster. Now, I've already created my Bigtable cluster, so I could click on Boris Test, and I see I have my Boris Test cluster in the US Central 1B zone. So now what I want to do is I actually want to go ahead and I want to import a table, an external table into Google BigQuery. So if I go into BigQuery, I could click on the plus beside my first data set one to import a new table. I'm going to want to select the source data. I'll pick create from source. The location, I'll pick Google Cloud Bigtable. And now I have to enter a URI. So I'm going to enter the URI as follows: https://googleapis.com/bigtable/projects/ and this is the project you created your Bigtable instance in. So for me, it's boris-test-project/instances/ your Bigtable instance ID. So this is Boris Test, tables, and then / hello Bigtable, which is the name of the table that I created in Boris Test. So I'll copy that over and paste it. And then I want to make sure the file format is Cloud Bigtable. The table name, I'll call it hello. And the table type, I'll make sure it's external table. For the column families, I could actually get that. I could go into Linux, and if I run the command cbt ls hello Bigtable, it's going to show me the different families for the columns. And I see I only have one family called CF1. So I'm going to enter this CF1 family. And the type I'll enter as string, and the encoding will be text. Options I'll leave as default, and I'll hit create table to create the table. Now I could see my table is created. I could query the table by clicking query table. And I'm going to want to change this here. So I'm going to want to select from my first dataset1.hello. And I'm just going to select everything from it. And if I run the query, I'm going to want to change the query type as well, uncheck use legacy SQL, and run the query, and I should get all my rows in the table. And I could see that in my table, I have some greetings. It says hello world, and then it says hello cloud, Bigtable, hello HBase. So it's a very simple table. Now what I could do is I could actually move on and I could query a table that I won't actually import into BigQuery. And the way I'll do this is I'll go into Linux, and there's a few steps I have to do. So the first thing I have to do is I have to define a file, and I'll call this file hello_def.txt. So in this file, I have to specify which table I'm querying, the project, and so on, as well as the column families. And it's so I could take a look at the file format. It's in JSON format. So I have source format is Bigtable, source URIs. I'm just entering the same thing that I entered when I was importing the external table. So I just have the HTTPS, Google APIs, Bigtable, projects, Boris test project instances, Boris test tables, hello Bigtable. The Bigtable options, I'm just going to enter the column families. So I have my family ID as CF1, type string, and encoding as text. Now, once that's done, I could actually go ahead and I could run using the gcloud command prompt BQ command to query Bigtable. I could run a query, BQ query. And then just to note that if we are actually doing the query on data that we're not importing into BigQuery, we do have to run the query right away. We can't import it and then run the query because obviously we're not saving the table in the BigQuery dataset. So we'll run BQ space query space use and then use underscore legacy SQL false and then space dash dash external underscore table underscore definition. So that's the file I talked about. We'll call it hello, and we'll specify the path. It's in my home directory. So home Boris hello underscore def.txt, and I'm just going to run select star from hello. So same as I did when I imported the whole external table into BigQuery, I'm just doing it now without importing it, and I should get all the rows from the table. So I could see I have the same thing, hello HBase, and then I have hello cloud Bigtable and hello world. So those are the two ways that we could query data with Google Bigtable using Google BigQuery. In this video, I will identify the various Google Cloud APIs. Google provides REST APIs which can either be called directly or through one of the client libraries Google offers for various programming languages in order to integrate cloud applications with the Google Cloud Platform. Additionally, Cloud APIs can be reached through the Google Cloud Platform web dashboard, gCloud SDK command line tools, or through the Firebase mobile SDKs for mobile applications. Aside from having a REST interface, some of Google's newer Cloud APIs also expose a RPC interface, which can be used with gRPC to interface with the API in order to increase performance. There are 8 types of Google Cloud Platform APIs available. These are compute, storage and database, networking, big data, machine learning, management tools, identity and security, and managed infrastructure APIs. I will start by talking about the compute, storage, and database APIs. Compute APIs deal with creating, managing, and provisioning App Engine, Kubernetes clusters, and Google Cloud Platform virtual machines. The Cloud User Account API is used to manage user access to Google Compute Engine VMs. The Compute Engine API is used to set up and deploy VMs to Google Cloud Platform. The App Engine API is used to deploy App Engine applications. The Kubernetes API is used for setting up clusters for container-based applications using Kubernetes. Storage and database APIs deal with accessing, managing, transferring data, and configuring different Google Cloud Platform applications, such as Cloud Bigtables, Cloud SQL, Cloud Data Store, and Cloud Storage. Some examples are the Cloud Data Store API, which allows for semi-structured NoSQL application data to be stored in Google Cloud Data Store. Another example is the Google Cloud Bigtable Admin API, used to manage Cloud Bigtable clusters, instances, and tables, as well as the Storage Transfer API, which can be used to transfer either to a Google Cloud Storage bucket from an external input or between storage buckets in the Google Cloud Storage. So next I'll talk about machine learning and big data APIs. Various machine learning APIs are also available, such as the Cloud Vision API for face and text recognition, And it could also be used, for example, to detect non-child content, which should be banned from an application, a natural language API for text analysis, speech APIs for the translation of audio to text or from a written file to text in many different languages, and a translation API to translate between languages. Big data APIs include BigQuery, which is an enterprise-level data warehouse that can be used to analyze data which are petabytes in size, Dataproc, which I went over in previous demos, and that is a Hadoop and Spark platform as a service offering by Google, Cloud Dataflow for streaming and batch data processing, and Cloud PubSub for reliable messaging between applications. So next I'll talk about management and security APIs. Management APIs achieve a variety of tasks such as cloud billing APIs for the billing status of Google Cloud projects, the Container Builder API in order to develop container images in the Google Cloud Platform, as well as Stackdriver APIs for debugging, error reporting, tracing, monitoring, and logging running applications in the cloud. There are two security APIs. The first is the Resource Manager, which provides ways of dealing with the metadata of your project. The second is the Identity and Access Management API, which can be used to authenticate with Google Cloud Platform when it's necessary to make API calls, as well as to control access to various Google Cloud Platform resources. Finally, the last two APIs, the Networking and Managed Infrastructure APIs. So the one network API Google Cloud offers is the Cloud DNS API. The Cloud DNS API provides low latency, high quality DNS record lookups for high volume applications. Managed Infrastructure APIs include the Service Management API, which offers the opportunity for service providers to publish their services on the Google Cloud Platform for potential users to see, as well as the Service Control API, which provides status checks, logging, and monitoring of published services, and the Service Consumer Management API, which offers utilities for the service publishers on the Google Cloud Platform to interact with their service users or consumers. Now that we are all done our lessons, it's time to do some practice. In this exercise, you will identify the steps to use initialization actions when creating Cloud Dataproc clusters, describe the use of functions, operators, and data types with BigQuery, identify the steps to export and update data with BigQuery, identify the proper storage options with Google Cloud Storage, query data using Google Bigtable, and identify the various Google APIs. Now pause the video and perform the exercise, and I'll get back to my solution. So the first thing we're going to do is talk about initialization actions. So initialization actions are either scripts or executables that are run on all member nodes of a Dataproc cluster just after a cluster is deployed. So there's sample initialization actions on GitHub in a shared Google Storage bucket. So let's go to Create Cluster under Cloud Dataproc in our web dashboard. We're going to give the cluster a name, and we're just going to leave all the standard options in there. And then to add initialization actions, we're going to click on the preemptible workers, bucket, network, version, initialization, and access options. Scroll down to initialization actions and click the plus sign to add initialization action. Then we're going to have to enter the bucket in the folder. So I'm going to install Jupyter Notebook. So that's in the gs:// in the public bucket, Dataproc initialization actions, jupyter.sh. If we copy and paste it, we should see that we get a check mark show up, which means it's a valid path, and we could hit create, which is going to deploy our Dataproc cluster, install Jupyter, and we could SSH to our master node and make sure Jupyter Notebook is installed. Okay, moving on, I'm going to talk about describing the use of functions, operators, and data types with BigQuery. So back to the slides. Operators in BigQuery do not use a function call for their operations. They are instead grouped with special symbols and keywords such as the plus sign for addition and not for a logical NOT operation. Operators in BigQuery will output null if any of the operand inputs are null. If an arithmetic operation overflows, an error will be returned instead of displaying a false result. So talking about BigQuery functions. So BigQuery functions have call rules which are applied to all functions. The first rule is that if one operand is of the floating point type and the other is some other numerical type, both operands get changed to a float64 type for the function to execute. Except for the case with the is operator, if one of the operands is null, the function is always null. If no time zone is selected for time-sensitive functions, the default time zone is UTC. With operand conversions, casting is explicit in BigQuery, meaning that the cast function needs to be called. Implicit conversion is called coercion and happens automatically in BigQuery. An example of this may be if a float64 type is required as a function operand and an int64 type is provided, then BigQuery will automatically use coercion to pass a float64 type as the function operand. So there's some data types that are supported in BigQuery: int64, float64 string, bytes, bool, date, time, struct, and array. Next, I'm going to identify the steps to export and update data with BigQuery. So back to our browser, and if I go into BigQuery, I could see that I have a table called schedule, and it's just a schedule of all the Major League Baseball games, the away team, the home team, the score, the attendance, and so on. To create a query, I'll hit the red Compose Query button, and then I'm going to want to click on Show Options and uncheck Use Legacy SQL to use Standard SQL. What I'm going to be doing is I'm going to be selecting from the table all the teams, basically where the home team is Mets, so that'll be select star from my first dataset one.schedule where home team name equals Mets. And if I run the query, I should be able to see that I get a few results. Now what I'm going to be doing is I'm going to be updating the table with the update my first dataset one.schedule set home team name equal replace home team name Mets with Blue Jays. So I'll be replacing all the places where the home team name is Mets with Blue Jays where true. So this should mean that when I rerun that first query, I'm not going to get any home team names with Mets. Okay, so the query just executed. I'll go back and run my initial query. And if I run this query, I should see that I don't have anything with Mets. And yeah, I have query return 0 records. Now, if I actually want to export this schedule table, what I could do is I have to create a bucket in Google Cloud Storage. So if I go to Google Cloud Platform Storage Browser, I have a bucket called boris-test-bucket, and it currently has no objects inside it. So what I'm going to do is back in Google BigQuery, I'm going to click the downward arrow beside my schedule table and click on Export Table. I'm going to export in the default format CSV with no compression. You could already see I have gs:// to specify Google Storage Bucket. I'll have to put in my bucket, so boris-test-bucket. And then I'm going to want to do / the name, so I'll call it schedule.csv. If I hit export, it's actually going, if I hit OK, it's going to export, and I could go back to my bucket and reload it, and I could see that I have my schedule CSV and the size, so I've exported my table from Google BigQuery. So the next thing I'm going to do is I'm going to identify the proper storage options with Google Cloud Storage. So back to the slides. So there are various Google Storage products available to meet different storage needs. Storage options such as Bigtable, BigQuery, Cloud SQL, and Cloud Data Store and Cloud Spanner are available for structured data. Google Cloud Storage is available for unstructured data. Cloud Storage for Firebase is available for mobile data. Structured data storage options can be further broken down. If you need low latency analytics storage, you would use Bigtable. For analytics that don't require low latency, BigQuery would be a good choice. For relational structured data that requires horizontal global scalability, Cloud Spanner would be a good storage option. For MySQL or PostgreSQL data, Cloud SQL would be the option to choose. Cloud Data Store would be used for storing partially structured NoSQL data. So next I'm going to query data using Google Cloud Bigtable. So Bigtable is Google's NoSQL database which can hold petabytes and billions of rows of data. It is low latency and is very good to use with MapReduce. Bigtable provides an Apache HBase client library and is very similar in its data structure model to HBase. There are two types of ways to query Bigtable data from BigQuery. You can either create a permanent table in BigQuery from Bigtable data, which can then be shared, or you can create a temporary table in BigQuery from Bigtable data, which is not shared. So let's go back to our browser, and I'm going to go inside Bigtable. I have an instance called Boris Test in my Boris Test project. So now in BigQuery, in order to import this table, I'm going to hit plus beside my first data set. I'm going to have to exit query view first. So if I hit the plus, I'm going to want to pick the data, create from source. I'm going to click on the location and pick Google Cloud Bigtable. Next, I'm going to want to enter the URI. So the Bigtable URI is https://googleapis.com Bigtable projects. I'm going to want to enter the project that my Bigtable instances in. So Boris-test.project instances. Boris test is the name of my Bigtable instance tables, and hello Bigtable, which is a table I have inside my Boris test instance. So I'm just going to paste this URI. I'm going to make sure that the file format is called Bigtable. I'm going to give this table a name, so hello table. And for the column families, I have to actually find these by using the command prompt. So what I'm going to do is I'm going to switch to Linux, and I'm going to use the CBT command prompt tools for Bigtable. So if I run the CBT space ls space the name of the table, hello Bigtable, within my project, so Boris test project, I should see the family name, and then I could use that family name to enter in BigQuery when I'm actually importing the different families. So I see my family name is CF1. I could go back to BigQuery. I could call the family CF1. The type, let's just say string, and encoding text. The options I'm going to leave blank, and I'm going to click create table, and that's actually going to import my table and create it inside BigQuery. So that's how we could go ahead and do that. So after that, I'm going to identify the various Google APIs. So back to the slides for this one. So Google provides REST APIs which can be either called directly or through one of the client libraries Google offers for various programming languages in order to integrate cloud applications with the Google Cloud Platform. So additionally, cloud APIs can be reached through the Google Cloud Platform web dashboard, G-Cloud SDK command line tools, or through the Firebase mobile SDK for mobile applications. Aside from having a REST interface, some of Google's newer cloud APIs also expose an RPC interface, which can be used with gRPC to interface with the API in order to increase performance. There are 8 types of Google Cloud Platform APIs available. These are compute, storage and database, machine learning, big data, management, security, networking, and managed infrastructure. So that's it for our exercises. Just to go over what we talked about. First, we identified the steps to use initialization actions when creating Cloud Dataproc clusters from the web dashboard. Then we described use of functions, operators, and data types with BigQuery. Then we identified the steps to export and update data with BigQuery. Then we identified the proper storage options with Google Cloud Storage. Then I showed you how to import data into Google BigQuery from Google Bigtable, which you could then query from Google BigQuery. And then we went over how to identify the various Google APIs.